Hello. Welcome
Good.
back, Virginia.
Good morning. Thank you. I am in the
Was that,
hot seat now.
yeah, was that 2 minutes of downtime with the stream enough to finish your talk?
Yeah.
Amazing. That's all you need.
Oh my gosh. Yes, I am ready to do my talk, but I know you need to orient people here first,
I
right?
do need to orient people here first. Thank you. I mean, you're the pro of hosting now. I'm just kind of waking up from a weird little fever dream nap I took between 7. No, not 7. It's 7 now.
Yeah,
When
I
was I
think
even
I
sleeping?
think you mean attending Spencer's presentation, right?
Yeah, I was there, sort of. So me and Darcy here will give everybody a little chance to check in, understand what's happening. You've made it to the Weather and Climate live stream, where we have been streaming for 67 hours straight since May 28th. We're trying to get to 100 hours. We've got more than 200 climate and meteorologists here to tell you all about the incredible work that they're doing every single day. And some of them are sleeping, which is amazing. And why are we doing this? Well, we're doing this because, unfortunately, we've already seen these huge cuts to science around the US. And what we're doing in these scientific institutions, if you've been paying attention at all for even a few minutes of the stream, is incredible work. It's the foundations of our forecasts. It protects us and keeps us safe when there's hurricanes and there's floods. It's what all of these people are dedicating their lives to, and a lot of it is under threat. So we've set up a really easy way for you to call your representatives. If you head to wclivestream.com/act, that'll take you to a 5-call script. Makes it super easy. Probably if you call now, you're still going to get voicemails if you're kind of nervous about the phone call thing. But I promise it's not that scary. Once you've done it a couple times, you start to have a rapport with the staffers. You know what you're up to. It's great. So I highly encourage you to tell them about anything you've learned in this stream, why it's so important, why it's really imperative to keep funding for all of these national agencies where they are. And with that, Virginia, are you ready?
Thank you.
Okay. I can keep vamping. I keep talking about how wonderful weather and climate services are.
No, that's okay. I have had no time to test my sharing backstage, so we are just going to see how this goes. I believe that I'm sharing a portion of my screen, and it is showing my slides. So I think, Mark, I'm ready to be fully on stage with my presentation.
Sorry. So, Virginia, just really quickly, before you press slideshow in the Google Drive, you click the down arrow next to slideshow, and you'll click presentation display options.
Okay.
And then you'll select full screen.
Full screen. Got it.
Let's see if that updates. Okay, great. Thank you. I'll hang up.
Okay. Thank you so much. So everyone, I am now presenting in full screen, which means I can't see the chat, which is bizarre because I know somebody said it in the chat already, but I've been hosting this time slot from 5 to 7 a.m. Eastern. This is my 3rd day. I'll also be here tomorrow. And for the first time, I'm on the live stream and I can't see what you're commenting. So I'm excited, and it feels so strange to be on the other side of this, to be showing you my work and talking to you about my stuff. And so please do ask me your questions. I want this to be a very casual and interactive kind of time. I've honestly just put together a bunch of pictures that should serve as the starting point for a conversation with you about my kind of stuff. So I'm calling this Serving Science by Serving People because I'm going to tell you my story and my career journey, but I'm a little bit adjacent to science research at the moment. So I'll just start by saying I want to save the world. I always have. I decided to be a scientist when I was in the 3rd grade, and I read a book by Madeleine L'Engle called Ring of Endless Light. And the heroine in that book saves sick dolphins by talking to them with her mind. And I was like, that's the job for me. I'm going to do dolphin telepathy. It's going to be my thing. I'm so excited about it. And then I realized that dolphin telepathy is not a thing yet. So I was already hooked on the ocean at that point, and I went to marine biology summer camp. And I remember growing up, this is me. I was the first kid in the pool on every hotel stay that we had, and I was the last one out. My parents had to drag me out. I grew up here. That's my house in the background. I'm in a canoe. This pond that you see me in, we could swim there, and we had cats and dogs that were all strays. I grew up in Kentucky, and so anytime an animal wandered up, my parents would just take them in. So there was this cat one time that would go canoeing with me all the time, and I was definitely the kind of high schooler who, when I felt sad, I would go out in the rain and wander through the woods without a rain jacket on, because I was just in my feelings, having a good time, being like a woman of the woods. So I was that kind of person. Once I decided that I couldn't be raised by wolves or rescued by a pod of whales from my like troubles in the middle of the sea, I just always knew I was going to do something. And I really got activated towards science as a real career choice instead of all this imaginary stuff about being one with the woods. When I was in high school and I was required for a political science class to do a project about some environmental issue, and I chose mountaintop removal because I'm from Eastern Kentucky and mountaintop removal is a thing there. And I remember researching mountaintop removal and then diving deep into the Alaska National Wildlife Refuge stuff was happening then. People were debating whether to open it up for drilling and to get energy out. And I remember at the same time that I was doing these projects, there was a politician somewhere down south that was saying, we don't want wind turbines because they are so ugly. And it was a moment for me because I was like, but have you seen mountaintop removal? And I realized that it's not just about like protecting certain areas. It's about humans relating to the environment, living in the world while having a planet that is good for us, that supports us, because we depend on the planet for literally everything, right? And I realized too, with that comment about the look of wind turbines versus the look of mountaintop removal, that not everyone gets to see everything. And it's just, how do we all know what's the right thing to do? So I decided that saving the world meant saving animals. And the first thing that I tried as a kind of career thing was volunteering at a wildlife sanctuary. This is me in Australia. The animals there in the bottom left, that's a kookaburra, and the right side, that's a dingo. And then the top left is a greater sugar glider. It's the softest thing I've ever touched in my entire life. The sugar glider is blind. It has no eyes. The dingo was rescued from a wildfire something or other, and the kookaburra has part of its beak missing. And we did these training things with the animals to, for enrichment, but also so the veterinarians could interact with them in ways that helped them. And I realized during this experience that saving the world was great by saving animals, but I didn't want them to need to be rescued in the first place. And so how do we know then what's happening with the animals so that they don't need to come into a wildlife rescue facility? So then I went into solid research back to the ocean, and I did a semester in Mexico in Baja Peninsula. I was studying whales. We were doing whale photo ID, which is the bottom right picture. These gray whales, you can take pictures of them, and they migrate from Alaska down to Mexico and then back every year. And you can see all the spots and markings they have on them. A person who takes a picture in Mexico, if they could share it with people in Alaska, you can compare which whales have been where and over how many seasons. And it is so funny to look back. I was doing whale research, but my specific research project was building a website so that people in Alaska could talk better to people in Canada and the United States and Mexico, so they could all talk to each other and compare findings and learn better that way. So I was already leaning into the communications part of science and away from just strictly doing research. My next summer, I spent deciding that I didn't want to be in the open ocean anymore because I knew I wanted to eventually have a family. And how do you manage being for months at sea when you have kids at home and stuff like that? So I tried coastal research. This is me in Panama at the Smithsonian Tropical Research Institute. The top right picture, I'm actually cleaning fiddler crab fossils. Crab fossils and fossils of invertebrates are extremely rare because they're so soft that when they get buried in a mudslide event or similar that would usually squish something and harden it into a fossil, it just squishes them into oblivion instead. So there's a mudflat in Panama where you can find fiddler crab fossils, and it is it was a huge find for us to hear from locals that they, wanted us to do something with these fossils, and to document them was such an opportunity. In the bottom right, you can see this was my research project. I created that. It's a bird on a stick with bird feet. I made them out of cutting straws and then taping everything together, and I would run the wheel across the sand, and then I was timing how long it would take the crabs to come back up, and I was testing predator threat responses. And then on the left, I'm holding one of the tiny fiddler crabs I was working with. So I really liked the coastal work because it let me go out and do my work with the ocean, and then I came home to my family or whatever at night, and it was a workable model. I got involved in a research lab at my undergrad. I went to school in UNC Chapel Hill, North Carolina. And that research looked like scuba diving. For the first time I was doing research scuba diving. I have those pink snippers. I'm imitating the damage to a coral from a fish, because we wanted to see if fish that were biting diseased corals and then biting healthy coral were spreading the disease. So this is my career path as a scientist, to figure out exactly what it meant to save the world and exactly where my passion lay and how I would have a sustainable career. I tried all these different things. They were all supported by different funding mechanisms and in partnership with different people and different labs in different places. Once I got my bachelor's degree and then got into grad school, I got my PhD. I'd self-funded my PhD research, which is not always what people do. So I got to choose what research I was doing. And this is me in Taiwan. I would crawl through these mud flats. You can see I have some cages there. I was studying how invasive mangroves, so those mangroves right there are invasive, how invasive grasses from the US are invading these mangrove forests and what it's doing to the food web there. I have a notebook. I'm so dirty. That was such fun work. That was project one. I was also in Puerto Rico doing stuff with mangrove trees there. I really enjoy the tropics. I feel like my natural habitat is the tropics. Here, I was adding fertilizer to the soil and testing what happened to the trees, because people often plant mangroves around the Caribbean and say, look, they're growing better when there's pollution and they're filtering out the pollution. This is great. But in combination with this work in Panama, but underwater this time, I showed that when there is fertilizer growing the trees, they grow less into the water, and you get less of this kind of ecosystem where there are sponges and corals and algae and oysters living on the mangrove roots as they grow into the water. And I really liked those two projects together because they showed that we could do a great job conserving mangrove trees around the Caribbean, but if we didn't pay attention to the details, to the type of conservation we were doing, which means planting trees that have roots in the water, that consistently grow roots and not just get fertilized by pollution and grow those upward leaf branches, we would lose the function that these underwater roots serve. And these underwater roots are the nursery grounds of the tropics. This is where the food webs that you see, people extraction from coral reefs. So the food webs that involve not just what's underwater, but people being fed in the tropics by fishing on coral reefs. The nursery grounds are here. So things grow up in the mangroves. They are teenagers and seagrasses. Then they go out to the coral reefs as adults. So I had this work that I'd done to get my PhD. And it had said, there's this common way that people preserve mangrove trees, but preserving them that way forever and only that way will lose both an ecosystem that we love, which is coral reefs. It will damage coral reefs because there won't be the nursery fish moving out to coral reefs later. But also it will hurt humans because humans depend on those fish that are growing up in the mangroves and then moving to the coral reefs. And I realized that after I published this research, it was going to go into a scientific journal. And I didn't know if anybody directing conservation around the Caribbean would actually read it or take any action based on it. So I thought to myself, well, that's a whole nother job to travel around the Caribbean and build trust with conservation communities and then, get people to use my work. And I thought, well, then let's do that job. So I switched from science research into science communication. That was the beginning of the whole thing. And now I'm a science communicator. I have been for a little over a decade. I get to talk to people and connect them with science that makes life better. And I am so happy. Again, looking backwards, it's always where I was meant to be. I spent the 2 years before I graduated entering video competitions and speaking competitions instead of writing my dissertation. So this was always where I was meant to be and where I'm happy. But it just took me a little while to see it. I also am really happy to be a mom. This is something I talk about on my personal social media a lot. If you follow me, it's hardly any science. And what I'm trying to do is if I can talk to people about being a mom and then surprise, here's an occasional story about the things that I'm seeing that are fact checked and based on evidence, then maybe if I build trust first, then I could be a different kind of like mom influencer where it's not just about partnering with companies so I can get by. It's about helping people have a better life based on the perspective that I have as a scientist first. So the things that I do now are I draw things. This is from a trip I took to Antarctica, and I published a magazine piece about it in a research journal at University of Georgia. I was talking about what it took basically to get through Antarctica, and I solicited some diary style pieces from the people that were near me. So I go on research expeditions and document what it's like to be a scientist out there making science happen. This is from a fossil dig site in South Montana. You can see I have this giant camera here. I am the media person collecting what we need to turn a fossil dig into a virtual field course for high schoolers, because in the United States, you are not required to learn about geology after 8th grade. So a lot of people who learn about geology and specifically paleontology as a career path stumble across it because they take some elective in college because they like dinosaurs. And then they're like, oh, no, wait, I actually really like this. I want to do it as a career. So if we can make this, the fossil dig site into a field course for high schoolers, they can interact with this as a possible career path and learn some stuff about geology and paleontology along the way. So I'm the media person for that. That's another grant that I got written into to be the person who does the media things for scientists. And then this is me. I'm also doing some research, but it's not science research anymore. It's science education and science communication research. So the research team behind me, we are all together trying to figure out how we can help train scientists when they're in graduate school to be great science communicators, because our current system doesn't allow for a lot of science communication classes. So we're trying to figure out how we can get great science communication classes for grad students across the country. Those are all the pictures I had for you, and I have this take-home message. Federal funding has affected my career at absolutely every step. It supported my training because, if you will remember, I'm looking back through my notes. What did I do for my PhD? I went to Taiwan. That was on federal training. I went to Puerto Rico through a NOAA grant, so that was federal money. I did my research in Panama at the Smithsonian Tropical Research Institute on STRI money. That was federal money. But more than that, even when I had my other funding to do the research in Puerto Rico as an undergrad, to go to Mexico and Panama when I was an undergrad exploring my job options, I was housed at research stations that were supported by federal money. So the entire system doesn't work unless we have significant investment in the infrastructure of science. I've been talking to people a lot lately about the engine that drives science in the United States. It's not just that the research, you have dollars and that buys supplies to do research. It's that all the things that together make research possible are so heavily supported by federal funding in this country. It also gave me stability so that I could search and explore and find my place within the sciences and just be a person. I showed that picture of me with my kids. I was supported in my grad career by an NSF, that's National Science Foundation Graduate Research Fellowship. And that, I remember the morning that I got the email saying that I'd gotten the GRFP, I called my husband, who was across campus in a different building, doing his science PhD as well. And I just said, I got it, because we both knew the day that the emails would come out. I just said, I got it. And we hung up and we ran and met each other between our buildings. And I remember hugging him and crying. And I just said over and over, we're going to be okay. We're going to be okay. Because we didn't know how we would make money as scientists. We weren't making a lot as grad students. And the fellowship was 3 years of salary for me. So I knew then that I could pursue the projects that I liked, that I would have enough to take care of my basic needs. So I could just do good science instead of trying to figure out how I was going to make the whole thing work. My husband also was supported off of federal dollars. He had an EPA, Environmental Protection Agency fellowship, to do his work. It was a similar thing where it gave him salary for a couple of years. So we were able to start a family, to be together, to do these careers because federal funding gives funding to scientists at a level that is not replicated by smaller grants coming from a lot of different sources. And then my current job, the Dino Dig research is a federal grant. Going to Antarctica was a federal grant. I do so many other things. I'm the co-founder of a startup, and we are seeking federal money to get our startup really going. We've been just bootstrapping it so far, and we're really excited about the idea. It's to make better ocean data, and we'd like to work in partnership, not just be funded by federal grants, but we'd like to work in partnership with agencies like NOAA so that we can ultimately build this new data network and then give away our data for free, like NOAA does. And make it useful for people to keep themselves safe and have a nice life with the ocean. So Dino Dig, startup, going to Antarctica and doing expeditions like that. The research that I'm doing on how to get scientists trained in science communication so they can get good jobs and we can keep getting support for science, that's a federal grant. So I am here to tell you that there are many people who are not scientists who support the science infrastructure and science engine in this country. And we are all supported by federal funding, which just provides a function that cannot be replicated in other spaces or hasn't been so far. That is the end of my presentation. I'm so excited to be brought back to the chat and to see what y'all are saying about all this. And I'd love to answer your questions and talk with y'all about any of this that interests you.
Oh, I'm so excited because I've seen you do this dozens of times, but I want you to look in the chat and see how excited and inspired all of these viewers are by your story. Starting right at the top when you were petting whales. I think someone said that that's probably the closest you could get to, dolphin telepathy, just petting those whales right there.
I've never thought of
that. You just went on this incredible journey, and thank you so much for taking the time to share it with all of us. I think we've seen a lot of sort of the more traditional science path here, and as a chronic career changer myself, I think it's really great to kind of share that amongst the, more regular, postdoc to academic professor pipeline. Mm-hmm. It's very inspiring. But there's also questions. People weren't just gushing. They did want to get down to the nitty gritty, including what's the absolute favorite place you've been?
Listen, I love everywhere that I've ever been, and you cannot make me choose a favorite. However, I am best suited to be on the tourism board for Panama because I have spent so many I've spent years living there, and it is just a place where anyone can get to the spaces I was. In Mexico, you kind of have to find your way out in the middle of nowhere to get to the whales. In Puerto Rico, I was outside the cities, and you have to know what you're doing and maybe take a kayak or a boat out to where I was. But in Panama, you can take a plane into the town I was living in. It's called Bocas del Toro. You can book any private boat or any snorkel tour, and they will take you snorkeling in the mangroves. And I know most of the nature documentaries we see are people kind of cruising over coral reefs, looking down through the camera as they dive. In the mangroves, it's like you are brushing the reef aside if you swim through these roots. It is terrifying at night. Don't make a scientific study that requires you to be there at night because things will be touching you that you can't see and you don't know where they're coming from. But Panama is accessible. It is a lovely country full of lovely people, and you can get to exactly where I was if you visit Bocas del Toro.
Good to know. Yeah, I guess you should be on the tourism board.
Listen, if anybody wants to, I know we're all about sponsorships on social media these days. If anybody wants to throw some dollars my way, I'll just say that over and over.
Kind of like leaning in now, getting back from the wild travels you've been in, but it looks like Lila Kulotz is asking, if someone is considering this sort of career like you have, what sort of qualities do you need to have? Should you work on improving in yourself? Anything that you find hard that you had to take some time to get to?
Yeah, so I think the biggest thing for deciding if you want science communication as a career is to look at where you are now and what science communication as a career would be like. There are a lot of scientists who think they will do science communication on the side, and you can do that, but it takes a lot of time to build the skill set, but also to find your audience. And if you're trying to build your own audience, you have to be there consistently putting in the work for a long time, and it takes a lot more time than people might expect. At the same time, this kind of work is often considered service work for academics. And so you can't count it toward your career advancement like you can publishing another paper or getting another grant. So there's this tension within the academy of like, where are the limits of a scientist's job? You know, we want you to do science communication, but don't take the time to do it too much. And also you can't claim too much of it toward advancing your career. So I think finding the spot where you can actually consistently invest means finding what means something personally to you, what is fun and exciting, what jams with your skill set. And for anybody out there who's looking to do science communication as a career, if you visit my website, I offer free monthly coaching. And the next one, I'm going to set one on Monday that's about having a job in science communication. So if you want to chat with me about that topic specifically, just contact me through my website or look at the Science Communication Office Hours page and you'll have a registration link there.
Amazing. We love free information. That's kind of our whole shtick here. And I guess kind of I've followed your career for a while, but I didn't know you were doing the art stuff as well, like the hand-drawn things. So Fish, a chronic commenter asking all these great questions, is asking, how does art fit into science communication?
I take a very broad view of science communication. I remember early on in my career, someone classified people doing science on YouTube as scientists, science institutions, and amateurs. And I was like, what? Because the amateurs are the people that you know of who have millions of followers and talk about science all the time. And I realized then that to me, science communication is really just discussing science from a specialist to a non-specialist. And that's so broad that you might argue that it's unuseful, and fine, but words are only useful when you make them useful. And so I think art absolutely has a huge place in science communication. And Fish, if you're looking for prehistoric creature community specifically, look up, there's a SciArt, hashtag SciArt community on Blue Sky. You may already be a part of that. I don't know, but just in case you're not, hashtag SciArt on Blue Sky. There's a whole Blue Sky feed of science artists. And the person who made the SciArt feed, I believe their handle is Flying Trilobite. And so you can tell by the trilobite in the handle that there is a whole community of prehistoric science artists that talk to each other on Blue Sky. I know there are also science art communities. And again, I'm going to reference my website. I maintain a list of where you can find science communication communities on my website. So if you click the SciComm tab, there's a spot for communities. I think I have a few for science art listed there as well. If you're looking to find community, you can find it there.
How wonderful. It's 7:30 now. We're halfway through the hour. I know that you're going to be back tomorrow, same time, same place?
Yes, 5 to 7
right.
Eastern. And I think it's going to be more of a loose chat than talks during my time, at least some of it.
Amazing. All right. So everyone should just stay watching the whole time and come right back for that. Thank you so much for sharing your journey with us.
Thanks for having me. Have a good
All right. Amazing. Okay. So real quick, before I bring on our next incredible speaker, let me just do a quick reminder of why we're here. This is the Weather and Climate live stream. Thanks so much for getting here, finding us, however you came here. If it was Tumblr or Blue Sky or YouTube was just like, you'll like this. We're so glad to have you. We've got nonstop programming for 100 hours. We started on Wednesday. We're going through Sunday. 100 hours, turns out, is a lot of days. I know I kind of understood that intellectually before we started this, but now it's kind of catching up to me with the sleep-deprived state. But part of what we're doing here is we're having all these climate and weather scientists share their science to show you just how important all of this is to our daily lives, to the infrastructure of the entire country, to everything in between. I think there's a lot of stuff in between there. And we've heard so many cool talks, and so many of those, as our speakers are pointing out, are funded by the federal government. And right now, we are looking at a possibility of so many things getting cut on top of the things that have already been cut. I know Virginia mentioned that she was funded by the GRFP. That's one of the things that is currently in the presidential budget looking like it's going to get zeroed out. And ideally, that wouldn't happen. So we've made a handy little link that you can follow in the bar scrolling across your screen. So take some time, call your representative, tell them a little bit about the science you're hearing today and why it's so important to you. And also, if you want to also take a second after you do that, share the live stream with your friends and your family. And then keep watching, keep commenting, and ask us questions. I am so sleep deprived. I'm so sorry, everyone. All right. With that, I'm going to bring on Tony Broccoli, who is from Rutgers University, And I believe, oh yeah, thank you. I don't have to go to the tab. Is going to talk to us about coastal storms and storm surge flooding along the U.S. East Coast. Tony, take it away.
Well, thanks, Miriam. Good morning. At least it's morning here on the East Coast where I am. So I'm going to talk a little bit about coastal storms and storm surge flooding, and tell you a little bit about how we can learn more about these phenomena. So to begin, storm surge is a major coastal hazard. I think most of us know that. It's a coastal hazard in many different ways. In this image, you see battering waves, damaging houses, damaging structures. But there are also more subtle and insidious ways in which storm surge can be hazardous. There are many places that might not be directly on an ocean coastline that are still close to sea level and vulnerable to storm surge flooding. And in fact, in some of the big storm surge events, a lot of the damage is produced by flooding in areas where there aren't battering waves, the kind of photogenic damage that sometimes gets emphasized in the media. Now, looking at the history of storm surge flooding in the northeastern United States, one of the events that comes to mind immediately is Hurricane Sandy. It's now been almost 13 years since Hurricane Sandy hit the New Jersey coast, a very unusual storm, a hybrid storm that started out as a hurricane, but started to lose some of its tropical characteristics as it approached the coast, but a very intense storm that produced storm surge flooding of almost 3 meters at the Battery at the southern tip of Manhattan Island in New York City. You see an image there of the floodwaters entering the Brooklyn Battery Tunnel. And Hurricane Sandy made landfall in New Jersey, a little more than 100 kilometers south of where I'm sitting now, and produced the highest storm surge on record for New York City. But there have been other big storm surge events, some of them further back in time, like the Great Appalachian Storm of November 1950. This was a winter storm. And it took an unusual track, a little bit like Sandy, in the sense that it developed out over the ocean and then moved in a more northwestward direction. And this storm is fascinating. It produced 3 to 4 feet of snow in parts of Ohio and West Virginia, but it also produced some of the strongest winds ever on record in the New York City area. And you see a flooded LaGuardia Airport down in the lower right of this figure. Over 2 meters of storm surge, but not quite as damaging as Hurricane Sandy because the storm surge occurred at low tide. A little bit more recently, there's the Great Nor'easter of December 1992. This was a kind of a more typical winter storm. Of course, coastal storms are called nor'easters because the strongest winds come out of the northeast. This produced a storm surge a little bit under 2 meters, but that storm surge lasted for a fairly lengthy period of time. Again, very serious impacts, including water cascading down into stations of the New York City subway system, as you see there in the lower right. Now, I think what's interesting about the storms that I've just mentioned is one of them began as a tropical cyclone, a hurricane. And the others, however, were winter storms or extratropical cyclones, as we call them. And the big difference between tropical cyclones and extratropical cyclones is their energy source. Tropical cyclones derive their energy from the heat of the ocean waters beneath them. So tropical cyclones are most at risk for the United States during the late summer and early fall when the ocean waters are the warmest. Extratropical cyclones derive their energy from temperature contrasts, horizontal temperature contrasts. And those temperature contrasts are strongest during the cold season. So we can have impactful extratropical cyclones anytime from October through April and even May. And so there is a much longer window in which extratropical cyclones can be impactful. And they are impactful. If we look at large storm surge events in the northeastern United States, most of the large surge events are caused by extratropical cyclones. This is from a study I did with a former PhD student. We looked at tide gauge records from 3 locations, Boston, New York, and Norfolk, Virginia. And depending on the location, anywhere from 70% to 90% of the top 100 storm surge events occurred in conjunction with extratropical cyclones. So tropical cyclones get a lot of the attention. They have names. They're obviously potentially very intense events, but these much more frequent extratropical cyclone events are also impactful and will become even more impactful as sea level continues to rise along our coastlines. Here are tide gauge records from the Battery at the southern tip of Manhattan Island in New York City, just showing here the top 20 storm surge events. And all but 3 of those top 20 events are from extratropical cyclones. So we see right on top Sandy, which I've listed here as a hybrid event because it started out tropical, but then lost some of its tropical characteristics. In second place, you see the Great Appalachian Storm in 1950. Then we have another tropical cyclone, Hurricane Gloria, 1985. The 92 nor'easter comes in 4th place. And then Hurricane Donna in 5th place, 1960, tropical cyclone that's one of my earliest weather memories as a kid. But you can see that of the top 20, 17 of them are associated with extratropical cyclones. So it's very important for us to understand the potential impacts that these storms can have. Now, how can we assess the risk of extratropical cyclone, ETC, driven storm surge events with long return periods? When I say long return period, I'm talking about the most intense events that maybe happen once in a century. Well, our historical record of storm surge is based on tide gauges, and those tide gauge records are relatively short. Even in the longest locations, we have maybe 100 years of tide gauge records or somewhere thereabouts. If we want to look at the storms themselves from a meteorological context, we only have high quality reanalysis products that depict storms in 3 dimensions for about the last 40 years or so, maybe a little bit longer. Look, let's try to go forward instead of backward. It's highly unlikely that the most extreme extratropical cyclone-driven storm surge events that are physically possible are captured in either of these records. So what can we do? Well, there's an approach that's been taken by Ninglin and Kerry Emanuel, and they talk about these high consequence events that are rarely observed but potentially predictable as gray swans. You maybe heard the term black swan. Black swan is something that you can't predict. The point here is that the gray swans can be predicted or can be simulated, but they happen very, very rarely. So they're not well observed. So in the work that Lynn and Emanuel did, they attacked this problem by using a statistical deterministic model of tropical cyclones to simulate these gray swan events. And this is a figure from their paper showing that the largest event on record for the Tampa Bay region was the hurricane of 1921 with a 4-meter surge, that in the present climate, something 50% larger than that is possible, and that under a higher emissions future climate scenario with sea level rise, something catastrophically larger than that is possible. So this is the approach that we're trying to think about. How can we use our knowledge of meteorology and climatology, our ability to simulate storms, to project what may be possible? So in our case, it's a little bit more difficult to simulate extratropical cyclones because they are a more diverse set of weather systems. In order to do that, we need coupled ocean atmosphere models like this forecast-oriented low ocean resolution version of a model developed at the NOAA Geophysical Fluid Dynamics Laboratory, a federal laboratory. This model does a reasonably good job of simulating storms. The figure at the right, at the top, are observations of a metric that's related to storm activity. At the bottom, the contours are from the model. And so the model does a reasonably good job of simulating the major storm tracks. And the advantage we have is that we have a 1,500-year simulation from this model. So with that long simulation, we can capture events that may not be captured in the relatively short observational record that we have. And if we compare a modern reanalysis product, the NOAA Climate Forecast System reanalysis, cyclone frequency or cyclogenesis, where cyclones form, we compare the CFSR on the left with the climate model, the floor model on the right. We see for the region of interest a lot of similarity. The model is predicting storms to form in the proper area and to move through the proper locations. So that gives us some confidence that this model isn't out to lunch, that it's telling us something about the real world. We use this large simulation to identify extreme events. And here's an example. On the left, this event from the model had the lowest sea level pressure in the New York metropolitan region anywhere in that 1,500-year period. It's a March storm. It's a winter storm. It has a central sea level pressure lower than most hurricanes. And it's much stronger than the lowest sea level pressure in the reanalysis product from an extratropical cyclone, which was from the superstorm of March 1993. But there are other types of storms, in addition to the exceptional intensity of the storm that I just showed you, that also have the capability of producing large storm surges. And these include storms that move slowly and storms that have a westward component to their motion. And that's a characteristic that we see not commonly, but not uncommonly either. So here's an example from our simulation, 1,500-year simulation, of a slow-moving storm. This storm moves northeastward along the coast and then parks itself off the mid-Atlantic coast. Each frame here is 6 hours. So you're seeing a storm that's sitting off the coast. Here it's running through again. You'll see it sitting off the coast for a couple of days, contributing to storm surge. So this is an example of a slow-moving storm that is capable of producing extreme storm surge. There are also these cyclones that have a westward component to their motion. And the Appalachian storm of 1950, the perfect storm of October 1991, are historic examples of these storms. But as you can see in the figure on the left, in our 1,500-year simulation, we get quite a substantial number of storms with westward propagation. And on the right, you'll see an example of one. The storm will pop up here in the southeastern United States shortly, and then it will begin to move northward. Here it comes along the coast. And as it gets to the mid-Atlantic, it starts to turn to the left and eventually moves northwestward, increasing the potential impact. So through the use of this model, we can simulate a much larger number of these extreme events, and that helps us better capture the risks that they pose to people living along the coast. So I'd like to finish with a few take-home messages here. First of all, storm surge flooding from coastal storms is an important hazard along the Atlantic shoreline. In the northeastern United States, most of the impactful storm surge events are caused by extratropical cyclones. It's unlikely that we've observed the most impactful extratropical cyclones that are physically possible because our observational record is relatively short. Even 100 years of tide gauge data may not be enough to really tell us what the risks from the most extreme storms are. However, there's a way around this. Long simulations with coupled atmosphere-ocean models are useful in exploring the full range of these extreme extratropical cyclones and their impacts. Yes, we have to be sure that the models are as realistic as possible, but they are filling a gap in our understanding that comes about because we only have a limited amount of observational data. Federal funding has been essential in the development of such models. The model that I showed you was developed at the NOAA Geophysical Fluid Dynamics Laboratory. The models that are used routinely for weather forecasting have been developed in federal facilities with federal funding. So our whole weather forecasting enterprise depends on this infrastructure. Virginia in the last talk mentioned the importance of federal funding for infrastructure. The models that I'm talking about are part of that infrastructure, and they are used widely in the scientific community, including by people outside the federal government. And finally, improving our ability to anticipate these extreme weather events is critically important for minimizing danger to life and property. So with that, I'll end my presentation. I appreciate the opportunity to talk with you this morning, and happy to take some questions about this topic. Thanks, Miriam.
Amazing. Thank you so much. What a wonderful talk. If you want to scroll on over the comment section, you can see everyone asking you tons of questions, and I'm just start pulling them out because hopefully we can get through them all in the next 11 minutes so you can answer them all. So the very first one that came in was from Fish, who's asking, how are kind of the debris that get caught in storm surges making things worse? Is that a thing you look into at all?
Well, it's not my specialty, but certainly when these big storm surge events happen, and we saw this during Hurricane Sandy, if structures are damaged and destroyed, especially if they're destroyed, the debris from those structures can actually produce greater damage to other structures. They also pose a hazard after the storm surge is gone, if people are returning to an area. So certainly debris caught in storm surges does make things worse.
For sure. Yeah. And I know there's some like subway hardening things where they build giant doors on top of them so that debris can't get inside, and then damage like workers who go to repair this, hurt workers who go into the subway afterward to try to get things up and running again. And then kind of moving into the more cyclone side, we have Kelly asking, how do we determine how to name these cyclones? Is it only hurricanes? We've had a couple of speakers talk about this, but it was in a very different hour than this. So I'm sure the viewers are different at this time.
Yes. So traditionally, it has been hurricanes or tropical cyclones that have been given names. That practice goes back into the middle of the 20th century. Originally, the names came from the phonetic alphabet, and then they were given the names of people. Originally, only women's names, but today, both women's and men's names. There has been a movement to try to give names to extratropical cyclones as well. It's not done officially here in the United States by federal agencies like it's done for hurricanes, but some private sector organizations like the Weather Channel give names to winter storms, to extratropical cyclones. So we're starting to see some use of those names, but maybe not in the same official way that we see them for hurricanes.
Feel free to not answer if you don't want to, but do you have any kind of opinion about that, about expanding the kind of naming convention to these other hazards? I know there's also a campaign for even heat waves to have names.
Yeah, I mean, I think it's really a question for experts in communication and the social sciences. But I think one of the reasons why we tend to focus on hurricanes in the way that we do is they do have names, and it makes it easier to talk about them.
Rather than
you know,
a list of numbers.
to say that Sandy is coming and it's going to be an impactful storm is a little bit different than saying, well, we're going to get a big storm this weekend.
Definitely. Yeah, that makes sense. And then kind of going back, you showed a chart of storm surge numbers, and ARs at sea, noticed that a lot of them are from the 80s and 90s, and they would have expected them to become more recent with climate change, which maybe links a little bit into your extreme statistics that you talked about at the end there.
Yeah, so one thing that I maybe had in a little footnote at the bottom of the slide, but I didn't mention, is that when we did this research, we detrended the water levels because we didn't want the effect of sea level rise to be conflated with the meteorological impacts of the storms. So in that sense, the storm surges are being measured relative to whatever sea level was at the time that the storm happened. So that element of climate change isn't there. The possibility that climate change is affecting storms could be in our data, but teasing that out is a little bit more of a challenge. Although I am aware of one study that's been done recently looking at nor'easters that has concluded that while they are not necessarily becoming more frequent, that there may be a systematic increase in the intensity of these storms. But we'll need more work on that to know for sure.
Yeah, and I guess the next question kind of leans into a little bit from the modeling side. You talked about the GFDL model, but I guess can you talk about what makes that model so good at what it does, or if there's other technologies that are enabling forecasting of storm surge prediction and maybe the analysis from the model side. And then I guess the follow-up question is this being used for mitigation efforts?
So the most crucial technology for simulating storms is computing power. Supercomputers, all of our weather forecast models are run on high performance computing systems. And as those computers become more powerful, we can better resolve the intensity of storms. Basically, the way these models work is they divide the world up into a grid of boxes and use the laws of physics to describe what's happening in each of those boxes. The more boxes you have and the smaller the boxes are, the better you can resolve the very intense winds that are associated with these storms. So computer power is really, really important. But it's also important to have observations when we're making actual forecasts of what's going to happen tomorrow, the next day, or later in the week. And there, satellite remote sensing is important. Other technologies that enable us to have a better picture of what's happening in the atmosphere are important. But maybe most important, and even though it's not a technology per se, I think it's important for me to mention, most important is the human brain power that goes into developing these models. And that's where the training of scientists is really important. And as I think we've heard throughout the live stream, most of the scientists working in this area are being trained with funding that has come from the federal government. And that's something that we should never lose sight of. Now, mitigation efforts, certainly knowing what's possible, knowing the kind of hazards that can occur, enables us to better target mitigation efforts. And I would say that the knowledge that we gain from studies like this can contribute to those efforts.
Great answer. Kind of going back into the specifics, I believe you were showing a slide of some storm tracks and they were veering into the westerly direction. This has a kind of a fun comment here. So what makes them turn? And comments that the Northern Territories aren't that inviting.
Yeah. So in a mathematical sense, the atmosphere is chaotic. We get, just by nature of the dynamics of the atmosphere, we get changing weather patterns. And those changes are natural. They're just part of the way the atmosphere works. When we get these storms that turn to the left, it's because we have a phenomenon going on that's referred to as atmospheric blocking. They are being deflected in that direction rather than the more conventional southwest to northeast motion, typically because there is a high pressure system throughout the depth of the atmosphere that is preventing the storm from moving in its usual direction. This is what happened with Hurricane Sandy. If you followed the track of Hurricane Sandy, for a long time, it was east of the southeastern US coast, moving to the northeast, but then it encountered this blocking high pressure system, and it made the storm take this left turn into New Jersey. So the other storms that are simulated by the model that are making them take that left turn, that's happening because there's a blocking high pressure system to their northeast. And those are things that just happen as part of the way our climate system works.
Yeah, I think that's, an important reminder. We talk a lot about climate change, but there's lots of variability happening regardless of how many emissions we're putting up into the atmosphere. I guess, would you like a silly question or a more serious question for your final question?
It's early on a Saturday morning. I don't mind a silly question at all.
Okay, so we got how are the climate horror movies or the sci-fi movies about storm surge? Is there any truth to them? And I think they later followed up saying things like Day After Tomorrow, or maybe even a sillier example, Sharknado.
Yeah, I'll leave Sharknado behind for the moment, but Day After Tomorrow is a good example of, I think, a lot of this cli-fi area. The premise behind the Day After Tomorrow has some rooting in science, namely the idea that the effects of climate change could slow down the overturning circulation in the Atlantic Ocean, of which the Gulf Stream is part. The idea that these changes would happen over a matter of days and that they would cause New York City to be frozen over, that's not supported by science. But it's taking a germ of truth from science and using a lot of dramatic license, capturing some of the science behind that. But it would not make for a very exciting movie for those changes to take 10 years or 20 years. Having them happen in a few days makes the movie more exciting. And I remember my nephews watching it when they were young, and they thought it was really cool that their uncle did something that was related to the Day After Tomorrow. Oh,
that's wicked cool. Oh man, that's great. Yeah, I guess I think you're probably right that it's not quite as dramatic if like an ice sheet isn't crushing across New York City. It's a little bit of a slower process in reality. Well, thank you so much for taking the time to answer all of these questions, both serious and silly, and sharing your research with us. We are so grateful. And if you do get a chance, I'd recommend scrolling back. There was much praise for you. So yeah, with that, I'm going to have to welcome the next speaker on. Thank you so much.
My pleasure, Miriam.
Have a great day. All right. So we just entered, is the ticker right? Are we in the 67th or the 68th hour now? I truly don't know. Either way, it's, yeah, okay, 68 hour. We've got 32 more to go, which is wild. I think we might actually make it all the way through this, which is super freaking cool. I'm very excited to welcome the next speaker. Before I do that, though, well, actually, never mind. No, bring Claire on. Claire's hosted. She can help me.
Hello.
Especially because you are a former federal worker who's now very recently gotten back into the academic job life. So you're kind of the perfect case for why what we are doing is so important, why we are a little bit traumatized by the recommended budget from the federal government.
Yeah.
And so we're encouraging folks to head to wclivestream.com/act, take a minute to call your representatives, let them know about any of the science that you're hearing on this stream, why it's so important, all the fun facts you're learning about everything from storm surges to, I'm imagining, clouds from you.
Indeed.
Amazing.
We will be talking about clouds.
Yeah, so I'll let you go ahead.
Okay, thank you, Miriam. Good morning, everyone. I'm very excited to be back now and get to share my own research with you all. So we're going to be talking about disappearing clouds, or a transition between two different cloud regimes that maybe we would see in the future. So this is work that I did a few years ago, and yeah, I'm very excited to share it. So I want to just start off a really big picture, talk a little bit about why clouds are so important for determining climate. So when we think about the climate in really broad strokes, we can think about the temperature on Earth being determined by this energy balance. Basically, that says that what comes in has to be balanced by what goes out. So the energy coming into our Earth is coming from the sun, and the Earth is itself emitting thermal energy back out to space. And so that has to be balanced. That determines the temperature. And the amount of sunlight that is able to come in and heat up the Earth depends on this term, the albedo. I know there's been some love in the chat for albedo. Albedo just means the fraction of that solar energy that gets reflected back to space. So on our planet, that's about 30%, and most of that reflection is done by clouds. So we can see that kind of makes sense when we look at a satellite composite image like this. When we look down at the Earth, we see that it's pretty much covered by clouds all over the place. And in these visible sunlight wavelengths, clouds are acting like mirrors. They're scattering that sunlight back to space. That's why we can see it from these satellite images. But in the infrared or thermal wavelengths, clouds are acting like blankets, the same way that we talk about greenhouse gases. Clouds are really efficient at absorbing that infrared or thermal radiation. And so clouds have this dual effect. They both are reflecting sunlight, and that's a cooling effect, but they're also absorbing thermal radiation, and that's a warming effect. So to understand what the total or the net effect is, we need to understand which of these wins out. And the answer to that depends on the type of cloud that we're looking at. So maybe you've seen a diagram or sketch of different types of clouds that look something like this. I got this off of one of the NOAA websites, and you know, it's very pretty. It has all of these fancy Latin names for clouds. But actually, as climate scientists, we tend to think about clouds in much simpler terms, and which may be surprising, but what we really care about is the altitude of these clouds. And so I'm going to draw us a new sketch, and we're going to think about three different types of clouds here. Clouds that are low, close to the surface. I'm sketching them over an ocean right now, but our low clouds, they tend to be pretty good mirrors, so they're reflecting a lot of that sunlight. But because they're very close to the surface, how good of a blanket or insulator these clouds are really just depends on their temperature. And since they're basically the same temperature as the surface, they're really bad blankets. And so they have a strong cooling effect, but a weak warming effect. And so overall, these low clouds will cool our planet. On the other hand, if we have clouds that are very high up in the atmosphere, they tend to be a little bit less good as mirrors. If you look up at high clouds, those wispy clouds, you can kind of see through them. So you know they're letting through a lot of that sunlight. But because they're so high up and so cold, they're super good blankets, and they have this net warming effect. And then our last category of clouds are ones that are kind of low and high. They go through the whole atmosphere. These are your big thunderstorm, deep clouds, and they are both good mirrors and really good blankets. And they actually end up having basically those two things cancel out, and they have almost zero effect in terms of the radiation, in terms of heating up the surface. So that is kind of the way that climate scientists like to think about different types of clouds. And so what I do is I model clouds. I run simulations of clouds. I write down equations to describe clouds. But modeling clouds is really hard. And there's kind of two main reasons why this is true. And the first is that if you look at the composition of our atmosphere, most of the air is nitrogen, and most of the rest of it is oxygen, what we're breathing. And then the entire amount of water that's in our atmosphere is only about 0.25%. It's very tiny. And if we look just at that water budget, almost all of the water is in the vapor phase. And so clouds are just this, little maybe 0.4%. So basically nothing. So if we're talking about trying to model these on a computer, we're talking about trying to keep track of pretty much zero of the whole atmosphere. So it's really hard to do this computationally. And the other reason that modeling clouds is really hard is that they span this huge range of scales. So the processes that are important for forming clouds are happening down here on the scale of nanometers or micrometers. The size of an individual cloud droplet is usually only about 20 micrometers in diameter. So they're itty bitty. We're never going to be able to keep track of all of these in a computer model, especially because we have to also consider scales all the way up to hundreds or even thousands of kilometers, which are the scales at which clouds get organized. So a hurricane can be really big, but inside that hurricane, it's still made up of itty bitty little droplets. So we have to be able to track all of these scales, or at least represent them in our computer models in order to make sense of the impact of clouds on our climate system. So I want to go back to this picture that was on my title slide. This is a photo that I took while I was a PhD student. I was living in Southern California, and I'm here standing on a mountain looking out. Down underneath all of these beautiful clouds is Los Angeles. And out on the horizon, if the clouds weren't there, you'd be able to see the Pacific Ocean. And in this picture, we see two types of clouds. This low deck of clouds, these are called stratocumulus clouds. And that's what is going to be the focus of my talk today. But also up here, we've got some beautiful cirrus clouds. So these are those high, thin clouds. You can kind of see through them, versus these clouds, they're the really good mirrors. They're super optically thick, is what we say. So this view, we're standing out looking over the Pacific Ocean out here on the horizon. But if we zoomed out and looked at this view from space, now we're looking down, satellite image. Over here, this is where I was standing on that mountain hiking in Pasadena, California. And this day that I chose for the satellite picture, it was quite similar to that day that I was hiking. You can see that these clouds have intruded over the land. They're covering up over LA County. But if we were able to see far enough from that mountaintop, we would have seen out over these thick stratocumulus clouds that you couldn't see through to the ground. And if we kept looking further and further, if we could have seen all the way out to, say, Hawaii, we would have noticed that at some point, maybe a little over halfway, that big, thick stratocumulus deck started to break up, and we start to be able to see the ocean. And we start seeing these kind of puffier, scattered clouds, and we call those cumulus. And so this picture is really canonical of what this part of the Pacific Ocean usually or often looks like. But it doesn't look like this every day. There's a ton of variability. But on average, if we take the picture from space every day and we build a composite average, we can make a map like this of cloud fraction. And so here I'm using satellite data that's a combination of data collected by multiple NASA satellites. It's in this Cascade product, a fun name. But we see that when we're going from Southern California, follow this arrow out towards Hawaii, we have this picture in the mean that it's cloudier towards the coast and less cloudy out towards Hawaii. And we see this off the coast of California, but we see the same thing off the coast of Peru, off the coast of Namibia, maybe a little bit off the coast of Australia. And this phenomenon we call the Stratocumulus to cumulus transition, this transition between these two types of clouds. And these clouds are quite different, especially in terms of this effect I was talking about, how good they are as mirrors. So they're both kind of low to the surface. They don't have this strong warming ability. They're quite shallow, but because stratocumulus clouds tend to have this very high cloud cover, they reflect most of the incoming sunlight. And here, these pictures are generated by cloud simulations, very high resolution simulations that I ran. Versus when you look down here at these cumulus clouds, you see there's these nice scattered popcorn-like convection, but you can see a lot of the ocean through these clouds. So they let a lot of sunlight through, and that heats up the dark ocean underneath. And so which of these types of clouds you have is really important, would really changes kind of the underlying ocean temperatures. So I know someone has probably already asked this, but I will answer it already. What are my favorite types of clouds? They are stratocumulus clouds, and that is because they are what I like to say upside down. And what do I mean by upside down? Because they are not like underwater or something silly like that, but they function kind of opposite from normal clouds. So let's talk about how normal clouds work. This is a super simple description of it, but usually you have a situation, you've got the sun coming in and it's heating up the air close to the surface. And as that air heats up, it wants to rise. And as it rises, it cools. And once it cools enough, the water vapor in this parcel of air will condense and turn into a cloud. Okay, so that's the normal story, but stratocumulus clouds are upside down. And what I mean by that is that these clouds, rather than being heated by the surface, we're going to think about a parcel of air up here near the top of the cloud. And this air, like everything, like the Earth, like you, like me, we're all emitting thermal radiation. We're losing heat to our environment, and the clouds are losing heat to the atmosphere above them. And the atmosphere above them is giving some heat back, but it's giving less heat back towards the clouds. And so that's causing the air up here to get colder. And as it gets colder, it wants to sink. And that drives this circulation in the opposite way. So instead of being driven by heating at the bottom, they're driven by cooling at the top. And when we have these air parcels that get shoved back down towards the ocean, they're able to come in contact with the air down here, which is very moist. It has lots of moisture from the ocean, travels back up and nourishes the cloud, provides moisture back to the cloudy layer. And so that's what I mean by them being upside down. I think it's just too fun. So, but we can imagine a situation where for some reason, and I'll give an example of what that might be, but if for some reason this sinking got weaker and it's not strong enough to mix the air all the way from the cloud back to the surface, say we're only mixing a little bit, but this air is not reaching all the way down to the surface, it's not coming in contact with this really moist ocean. And so eventually the clouds are going to start to dry out. They're going to start to evaporate and disappear. And maybe we'll be left behind with some little puffy cloud remnants, these that look more like a cumulus cloud regime. And so we can describe this decoupling with our physical equations. And it turns out that what basically determines when this decoupling of the cloud from the surface happens depends on the ratio of two processes. The first being this term down here, this latent heat flux. This is how much heat gets exchanged between the ocean and the atmosphere via evaporation. And the second term is this radiation term, how much heat the clouds are losing via their thermal emissions to the atmosphere above them. And depending on that ratio, the cloud will either be well coupled, this mixing will happen all the way to the surface, or it will decouple from the surface and start to disappear. And so if we now go back to our satellite observations, we can make a plot of this decoupling parameter, this ratio of these two terms against the cloud fraction, how much cloud there is. And these are, every point is the monthly mean observation from a different part of that ocean region between California and Hawaii. And you can see that once this decoupling gets large enough, basically all of your clouds are gone. You're in this state with just a little scattered cumulus convection. And I've drawn this red line on here just to guide our eyes as what of a sort of way that we might describe these data. And so I told you that modeling clouds is really hard for all of those reasons. And so as computational scientists, we sometimes struggle to encapsulate all of that detail in our models. And so we turn to theory or understanding to help us figure out what is going to happen to these cloud systems. Can we come up with a simple explanation for what's going on? And by an explanation, I usually mean an equation, because that is how we do things as physicists, as climate scientists. And so I'm putting up these equations on this slide just to show you that, yeah, they do look complicated, but there's only 5 of them. And for context, in a typical model that's really trying to resolve all these details, we might have 3 million or so numbers that we're trying to calculate. And so 5 is like really, really simple. So that's the point here. And then we can use these simple models to ask questions about how clouds respond to different changes. So maybe changes in the sea surface temperature, or changes in the wind speed, or changes in atmospheric CO2. And that's what I will tell you about today. So we're going to remember that our clouds are upside down. The motion that is keeping them moist depends on how much they're able to cool themselves to the atmosphere above. And the same way that CO2 is a greenhouse gas and warms the surface, it also could prevent the clouds from cooling themselves. It could trigger this decoupling of the cloud from the surface. And so that was kind of our hypothesis that we were trying to test with this work. And so the hypothesis and what this research showed us was that was true. When you have less CO2, the atmosphere is warming the clouds less, or the clouds can cool themselves more, and you're able to sustain these thick stratocumulus clouds. But when you add more CO2, the atmosphere is sending more heat back down to the clouds, or the clouds can cool themselves less, and that triggers this decoupling, and you end up with these more cumulus-like clouds. And so here's kind of the main result. When we take our model and we put in different values of CO2 into the atmosphere, this is what the model predicts the cloud fraction will be. So I'm starting here on the left and adding CO2 as we go. And what you see is that we start with a lot of clouds, and for a long time, as we add CO2, nothing really happens. And then there is a transition point where suddenly the atmosphere is no longer able to stay in this coupled mixed state, and the clouds disappear. And then, so then I wanted to ask, okay, now if we're at these really high, and these are very crazy high levels of CO2, but if we are at these crazy high levels of CO2, and now I start removing it somehow from the atmosphere, do the clouds come back? What happens? And what we saw was this really interesting, what we call hysteresis behavior, meaning that we're taking a different path back to our starting point than when we are adding CO2. So when we remove CO2 for a long time, the clouds actually don't come back. We have to remove CO2 almost back to our starting point before the clouds are able to reform. And that's because there's these really interesting feedback processes that happen with the sea surface temperature. So as you're adding CO2, you're warming up the ocean a little bit as you go. But when you get rid of the clouds and you let all that sunlight in, the ocean warms a lot. And once you start decreasing CO2, you don't get rid of that extra warming from the sun right away. So you have to actually decrease the CO2 more to bring your clouds back than when you started. So that's what's causing this hysteresis. And so this is the result from this really simple model with 5 equations. But now I'm plotting on top of it the result from a super complicated model called a Largetti simulation that has like these 3 million equations. And one of the goals of this work was to try and build as simple a model as we could that captured the behavior we saw from the really complicated model. And so we were able to do that very successfully. And that really helps us understand kind of the essential ingredients, the essence of what's happening in this cloud system. And so this complicated model, it makes very beautiful pictures like this. So this is the output from that simulation. You can see we're going from this very cloudy state to a state with almost no clouds. But how much time do I have, Miriam? A few more minutes?
Yeah, it depends on how many questions you want.
Okay, so I'll just tell you one more bit of this story. We wanted to ask what really determines this critical level where the clouds disappear. And particularly, I wanted to ask how sensitive is it to what I assume the initial sea surface temperature is. So in my model, I'm letting the sea surface temperature evolve. I'm calculating it interactively, but I have to pick this starting point. And so I wanted to ask how much does that starting point matter? And so that's what this plot is showing. The starting point, this initial SST, and the critical CO2 concentration where the clouds disappear. So if we start off colder, then you have to add a lot more CO2 for your clouds to go away. And if you start off a lot warmer, basically the clouds will disappear with right away at the present day CO2 levels. And that's because the clouds are sensitive both to this radiation term, but also really sensitive to the latent heat flux, which is in large part determined by the SST. And so we can kind of translate this idea of this initial condition SST to thinking about what's happening over this big region off the coast of California. So in that result I showed you, I was starting at 290 Kelvin. This is a typical temperature, but it's basically imagining I'm looking at a cloud right on this line. But what if I wanted to look at a cloud out here where it's a little warmer, or look at a cloud over here closer to the coast where it's a little colder on average? And so we can think about that as determining the initial SST that we're starting at. And so if we're starting out here where it's warmer, then we have to add less CO2. So now these colored lines are showing that critical CO2 value where our model predicts the clouds would disappear. And as you go closer into the coast, you have to add a lot more CO2 to get that transition to occur. So I'll give you a few takeaways. First, clouds play a really important role determining Earth's climate through their interactions with radiation. Second, we can use really simple models to help us understand the transitions between cloud regimes, like I showed here for stratocumulus to cumulus, and changes in the climate system, like increasing CO2, but also, say, changing wind speeds or changes in atmospheric humidity can trigger transitions between cloud regimes. And then finally, I want to acknowledge where my support has come from. So I know that's a large part of why we're here. This research that I presented, I did as a PhD student, and it was supported by an NSF Graduate Research Fellowship. I used a lot of data from NASA satellites to do this work. Most of those maps that I was showing you are coming from NASA. And then after I finished my PhD, I was supported through different ways through NOAA. So I had a NOAA Climate and Global Change postdoctoral fellowship. And then most recently, until February this year, I was a federal research scientist at NOAA's Geophysical Fluid Dynamics Laboratory, which I think we just heard a little bit about from Tony and some of the models he talked about. So yeah, as Miriam said, when I first came on, unfortunately, I was illegally fired from NOAA back in February. And so this cause is very close to my heart personally. But I hope that you guys enjoyed learning more about clouds, and I'm really happy to take a few questions.
Thank you so much for your talk, Claire, especially after hearing everybody talk today about how difficult clouds are to simulate, how well your simple model is able to replicate that, extremely robust model is fantastic. I know you got ahead of this question by saying what your favorite type of cloud was, but we did have someone ask, what was your least favorite type of cloud?
Oh my gosh. It's like asking your least favorite child. I can't answer that one.
Okay, we can move on to the sciencey ones. So you got into this a little bit, but maybe kind of explain a little bit more. So when you're running these cloud simulations, what actually are you representing? What are those equations for? What are they showing?
Yeah, this is a great question. We use a whole bunch of different types of models that represent these processes at different levels of complexity. So some of these models, most of them are kind of quite simple. They just represent the total mass of water vapor or of liquid water that's in a certain box. And so they're not even representing the molecules or droplets or certainly not atoms. We have other models that usually we run on smaller domains, but they do try to represent the droplets themselves. That's kind of the highest complexity. I don't think we have atmospheric models that really go down below the droplet scale, but most of them are actually a lot coarser than that. They're just representing in this box that's maybe 10 meters by 10 meters by 10 meters, how much total mass of water is there? That's a great question.
Yeah, definitely. And great explanation. I think I want to highlight, you have a bunch of comments about how good of a science communicator you are, how everyone really enjoyed it, how it's very clear. Someone's saying you could even give this presentation to children. So well done there. I'm just going to check and see. Okay, so our next speaker is ready to go. So thank you so much, Claire, for taking time out of your day, not only to host part of the stream, but give us all a talk. Are you coming?
And
are you coming back
in 30 minutes. Yeah.
All right. So you get a little rest.
I'll be right back.
Amazing. Okay. So since we're running a little bit behind, I'm going to do a super quick run through of why we're here. Thank you all for joining us. I hope you've been enjoying all the talks. We're in the middle of the 68th hour, which means we only have 31 and a half to go, which means we are past 2/3 of the way there. We are in effectively the home stretch. So thank you all for joining us for this fantastic adventure. If you are inspired by the work of these amazing weather and climate scientists that are talking, and you want to let the government know that you support their work, we have a really easy to use link, wclivestream.com/act, which will tell you who your representatives are, what their phone numbers are, and give you a little script to talk to them. And with that, I'm going to have our next speaker come on. Hello, Ed. How are you today?
Oh, pretty good. How are you doing? Yeah.
I'm all right. So Ed's going to talk to us about revealing the statistics of extreme events hidden in short weather forecast data, a case study of sudden stratospheric warmings. My gosh, I should just let you say it. Go ahead.
Thanks so much. Yeah, that title's a mouthful. I apologize. My goal here is, yes, to kind of cover. Can you see my mouse? I'm just curious. Yes, I can see it. Yeah, great. Yeah. So I'll be looking at extreme events today, and some new ideas and using mathematical techniques to help us understand, what our atmosphere and our climate system can do. And the goal of that, unpacking the whole title, is we're going to use short weather forecast data, right? We want to look at extremes. We need a lot of data to do this. And I'll show you, we can't afford really for every project you want to run models out for so long. So we want to use data that's already been produced for other reasons, for weather forecasting to do that. And then the case study will be sudden stratospheric warmings, and I'll explain what that is. Before I go even farther, I wanted to emphasize who really did this work. This study was led by Justin Finkel. Let's see if I can get this forward. There we go. Justin's, he was at MIT at the time. Now he's moved, I think he just moved back to Chicago. University of Chicago, where we've been collaborating with Dorian Abbott and then my colleague Jonathan Weir at NYU. So this has been a really fun project, collaborating between geoscientists and statisticians and applied mathematicians. So it started off with this frequency of these events. It was actually discovered in Germany. Oh, can you see the bottom? Oh, there we go. I have to fix that. There we go. It's funny that it doesn't quite fill my whole slide. I know you can see it. There was a phenomenon that was discovered in 1952. This is post-war Berlin, which you can imagine was a mess at the time. Like there was hardly anything going on there. But there was a scientist there. He was observing the stratosphere, and he realized that these huge events happen. That the stratosphere periodically, in the winter, you get these very strong vortex. It's cold. It's the polar night, right? So that the sun sets at the equinox, right? And it just gets colder and colder. And as that happens, you get a cold air mass, and you get a strong jet that flows around it. But periodically, this jet will break apart and then flip sign. Okay. And where we've been interested in sort of, how often do these events happen? Okay, it's an extreme event, and it's our case study. And if we look at the observational record, this is from a paper by Blanca Ayers-Aguena. We're looking at the observations. It's about 6 every decade. So if you look at every other year, these events happen. I'll show more details on the events coming up. But we were going to ask the question was, how are they going to change in a warming climate? Do we expect these extreme events to increase or decrease? They're important because these events in the stratosphere actually couple down to the troposphere. After a warming, you get a lot of cold weather events, snowstorms and stuff like that. So we'd like to understand sort of this coupling between the atmosphere. So what we're looking at here's the the estimate from the observations, and these are different climate models here. Like here's the GFDL model, CSM. These are 2 American models. Here's a French model and a British model. You can see there's a whole range of the frequencies here. Some it's like, oh, well, almost once a year. And these ones are like, okay, maybe once every 4 years. The problem is that, there's a lot of uncertainty here. What is this gray cloud here is saying, well, we only have 40 years of data. This is the uncertainty in observations. And then if you look at the models, there's also a lot of uncertainty. And, the black bars here are saying, well, all the models are sort of consistent with the observations. We really can't discriminate between them. Is one better than the other or not? Oops. And, is it 4 a decade or 8 a decade? And I like to think of it as, we're trying to hit the broad side of a barn here, right? It's like, well, somewhere there's too much of a range of uncertainty here, right? And that's what we want to fix here. And the goal of this talk is to say, well, if I can't rule anybody off the island here, if I look at their trends into the future, half the models say that these extreme events are going to decrease into the future. And then the other half of the models say, oh, no, they're going to increase in the future. And we can conclude that we really don't understand what's going on at this point. We need better, we need to constrain things. It would be nice if we could say that some of these models are wrong. Like maybe these models over here are wrong. Maybe this model right here is wrong. And then we could say, well, we could trust the models in between better. Okay. In a sense, what our goal here is, I'm going to really try to fix this. Every time I move the slides, it cuts off the bottom here. Let's see if I can fix that. That didn't help. let me tools. Can I just do view slideshow or something? I'm sorry. Oh goodness.
Can you do like a command?
I normally use Keynote, which was having trouble. So let's see here. Just one slide. That's all I want. I'm really sorry about this, guys. It's embarrassing. Let's see.
No worries.
Full screen. If that can help. No. View. Single page. There we go. I think that's it. There we go.
Got it.
Okay, sorry about that.
Perfect.
Yep. Okay, I have a PhD, but I can't figure out my slides. Anyway, what we're going to aim is, instead of aiming for the broad side of the barn here, I want to narrow down the uncertainty. I want a weaker area. We can really say something about what the true answer is, and then we can rule. These models are probably wrong. This model right here is wrong. Okay, so that's the goal of here. The model is nail down the starting point. Okay, and it's really about here is we're quantifying extreme events. How often do they happen? This is a once every 2-year event. It's not that extreme. How about if you have a really extreme event? And by extreme here, there's two meanings for extreme, right? Once might be that it's rare. So you could say, oh, it's extreme in the sense it was rare. It only happened once every 100 years. It could also be a very impactful event, right? And those two things sometimes go together, sometimes not, right? You can have a rare event that doesn't cause any damage. We're interested in rare events that cause damage. Let's just think about the rare, I always joke that it seems like every other year or so we have the storm of the century that hits, and the meteorologists, we got all excited, like, oh, there's so much snow. How often does a storm of the century come, right? And you can think of this by just taking a coin, right? A very biased coin that you flip, and the probability of getting a heads is just 1 out of 100, right? And I think we all know that if you flip it 100 times, you would expect to get 1 head, right? With this, right? Yeah, you expect. The problem is if you only do it 100 times, well, what's the actual probability of observing one event, right? Because when we say expect, that's the average, right? That's if you do this over and over and over again in an experiment. Yeah, on average, 1 out of 100 comes. But if you actually only do it once, the probability of actually observing one event, once in the century of storm once is actually only about 1/3 of the time. And this is just a binomial distribution. So about 1/3 of the time you'd observe your storm of the century once every 100 years. And then 1/3 of the time you wouldn't actually see it at all, right? And then you can see you have to go to 3 significant figures before you can tell the difference, right? If you have 100 years of observations, it's about equal chance of not seeing the storm of the century or seeing it. And then it's about half the chance of seeing it twice, right? And this is this issue. If you're really trying to quantify extreme events, if I have 100 years of observations, I really can't tell you what a one in 100 year storm is. You really need about almost a factor of 10 larger, 1,000 years to really define what that is, right? And what we'd like to do is we don't have the luxury of waiting 1,000 years to make that prediction, right? We'd like to be able to quantify extreme events better, right? And that's what we want to use. We want to use models here and say, okay, well, we only get 1 observation, right? But I can run models again and then run them longer and get better statistics and try to do that. And that's the game here. But then we end up with these trade-offs, right? If I want to do really long integration times, right? Thousands of years, so I can really quantify these 1 in 100 year events. So I can really estimate what they're going on. Well, then I want a model that I can run for thousands of years. It's got to be, these climate models, they're very comprehensive models, but they're made efficient enough that we can afford to do that. But they're not our best models, right? We don't run climate models for weather forecasting. Weather forecasting models are actually have higher resolution, right? We want to resolve all the storms better, especially these extreme events. We really want to resolve the scales that are relevant. These ones they're better models. They're sort of higher quality. However, we just can't afford to run them for thousands of years. So you have this trade-off. You can say, well, I can take a simple model and run it a long time, get very good statistics, but it's not the best model. So I have scientific uncertainty. Or I can run a really good model, right? My best weather forecast model, but I don't run it long enough. And then I end up with sort of sampling uncertainty. This problem began like, well, did I miss the storm of the century or not? And what we want to do today is using these hindcast ensembles. It's the fact that, for weather forecasting, for subseasonal to seasonal prediction, we're actually making all these long ensembles of forecast running our best models. Here we're going to be using the European Center's Medium Range for Weather Forecasting model, IFS. And they did these forecasts over and over again, so like twice a week in running off these ensemble. It gives us on the order of 1,000 years of integration time, with our best model, okay? The problem is it's not like 1,000 years run out where we can get the climatology. We have to be a little bit smart about it. That's what what we're trying to do is develop techniques to use these ensemble forecasts. And again, I'll explain as this goes on a little bit more as we go. So now let's get to that sudden stratospheric warmings, or SSWs. Okay, and what we're going to do here is we'd like to say, what's a really impactful one? What's a rarer event versus a normal sudden warming? This is what we're here looking at is this is the year 2008 to 2009. The blue curve here is what actually happened. Here I'm measuring the winds, the zonal mean winds at 60 north and 10 hectopascals, which is a really good measure of what's going on in the stratosphere. Go up north, just set up a radio sound, and you can measure these winds. Okay, and the black curve right here is what happens on average. So if you look in September, this is when right at the pole, the sun shuts down right at the equinox, and you start developing this cold pole, and the strong vortex goes up, and it peaks out around 40 meters per second in January. 40 meters per second, that's over 80 miles an hour. It's really strong winds that are just spinning around. And then it calms down. And then in the summer, you actually get a reversal, and it's easterly winds, or weak easterly winds, as it gets much warmer when you're in the polar night. Okay. So then the next thing we're looking at here is these ranges around here. So this is one standard deviation bounds. So most of the time, the wind kind of bounces around in this region. This light gray is the extremes over the entire observational record. So you find that sometimes it can get very strong, up to 70 meters per second, and then sometimes it can dip down quite negative. Here's an event. This is what actually happened. This is a sudden warming. The vortex was going over 70 meters per second. So this is, again, 150 miles an hour. And then over a course of a week, it completely flipped sign, and now you're going negative 30 meters per second, 60 miles an hour in the opposite direction. This is the extreme event that happened right here, this massive warming of the vortex. We'd like to sort of understand what's the frequency of this. This is actually the most extreme event we've ever observed in the record, right? You can see that's the cold, the most negative we ever saw in the entire period. Here's the next year. So again, the background's the same. I'm just showing a different year of winds. This is a more normal sudden warming. It's like, okay, we had a pretty reasonable vortex. Boom, up, almost got there, and then boom, reversed over here. And this event here, again, was associated with some snowstorms. But this event right here is sort of more of a normal event. How do we differentiate a really strong event from a more standard event, right? So what we wanted to do first is say, let's come up with different thresholds so we can measure more and more extreme, right? So we're just looking at, can you cross 0? Can you cross -8, -16? And then you can measure all these events right here. So again, a normal, this one got a little negative. This one right here got very strong. What's the frequency of this one? And now we're going to do is try to vary through kind of different ones. I'd say first would be a standard event. And then I'm going to go, it's never actually happened in the observable record, but we're going to show you the models do it. I like to call it the apocalyptic anti-vortex, where the jet that's normally going 80 miles an hour one direction is completely reverse sign, and you get this opposite, where the winds are so strong. It's never happened, but we'll show you that it happens in models. So what's the chance of getting to that? Okay, and then here's where we get the extra data. So these are these ensemble forecasts. And here I'm only showing a few of them, but it turns out that twice a week you launch these things of 10 ensemble members, and then you run them for 47 days, right? And you can see that in the beginning, that they're all kind of going along, and then they start to spread, and this is that spread in uncertainty because they have different initial conditions, right? So you do this over and over and over again. If you look at the winter weeks, this is how we get almost 1,000 years worth of data, right? And very high fidelity model simulations. And what I think of these are alternate sort of things that could have happened. Like in this year, you start off here, most of them follow what happened, but there was a chance that you could have gotten a pretty extreme sudden warming. We'd like to use these events right here to learn more. Okay, how about this one is interesting right here. When we had the really extreme event, none of the forecast ensembles got it. This was a really extreme thing that the Earth did something that the model wasn't expecting. It's a very rare event. But you can see over here where, there was actually a chance of a very rare, big event occurring as well. So we want to use all these sort of alternate realities to sort of learn the statistics. The trouble is that they're not all independent, right? And you want to get kind of geeky into the math. In the beginning, they're all the same, right? These are all, they have the same they have slightly different initial conditions, but overall they're largely the same. So we don't really have 875 years of data. We have something in between. And this is what we wanted to do, is develop statistical methods that can account for the fact that, the ensembles are not independent of each other, right? They get more independent as they go on. And that was the name of the game. And how can we do this in a principled way, right? So particularly those first 2 weeks. So we have something in between the data. How do we do that? Okay. So first I want to just show the results to kind of convince you it's worth doing the math. And then we'll go on, how do we do that? So what we're going to do here is we're going to measure the rates of these events, right? Again, this is that -40 would be the most extreme thing, never happened, but I call it the anti-vortex. And then there would be a standard event. okay? And I'm going to show two things I have here is in a linear scale. So this is the rate, right? This is like two a decade, 4 a decade, 6 a decade. Over here, we've just done the same data, but it's in a log scale, right? If you want to look extreme. So this is now once a decade. This point right here corresponds to down here. This would be 1 every 100 years corresponding way down here, right? Because when we look at these very extremes, we like to be able to see it this way. And then the orange curves right here are just using the observational record, right? So we have 1959 to 2019. This was done a few years back, so we don't have all of the most recent years, but a good 60 years of data here. And this is that uncertainty that I started with. Like, it's like, well, we think it's about here. I have a slightly different definition, so it's 5 every 10 years. But there's this large range of uncertainty. The 95% confidence interval is the thin line, and then the thick line is the 1 standard deviation. Okay, if we only used the 20 years for these ensemble hindcasts, right? That was a period where they did all these forecasts. It was a slightly different period, right? There were slightly more sudden warmings during that period. However, the error bars are much bigger because we have less data, and they're very consistent with each other, right? These are these data sets, but we wanted to put that down as a reference point because that's the year we're going to be using for our ensembles. And then we have these two statistical methods for forecasting. One is, I'll talk about, one is a flux counting. It's a very naive way. Oops, I spoiled my thing. And then the other is the Markov state model, which is a more sophisticated method. What they're doing now is they're just resampling, using all that data here to get the rates. We find that the rates are about the same, right? So we don't have a change. However, the uncertainty bounds have gotten much smaller. Okay, and this is what we're trying to do, is saying, okay, for a run-of-the-mill event, which we can observe fairly well, we actually do know the rates pretty well. However, we can narrow down the uncertainty bars. But then what we want to do is we want to start spreading out and saying, okay, how about more extreme events? For a bigger reversal, bigger. And you can see this is why it kind of collapses down to these very rare events. It's easier to look over here on the log scale, right? So if you ask, for the vortex to go down to 20 meters per second, well, okay, it's about once in a decade events right here. Problem is it basically happened once or twice in 20 years, right? So twice in 20 years, the error bars get huge because we're really very poorly sampling it. And here was that very strong event. Like it could be, well, it could happen every 6 years. The uncertainty is just way too large. This is where our methods come in much better, and they can actually clarify. And using all those ensembles, now we can say, well, for that monster event right here, that was probably more of like a once in a 30, 50 year event that we appeared. It's consistent with the observations it's occurred about once. And we can keep going down. Now we're looking at once in 100-year events, putting down numbers. And then what we can do even further is say these are events that have never happened, right? But they happened in the model simulations, our forecast models. And then we find here that this anti-vortex, where the really reverses sign completely from climatology, we have an estimate. This happens every maybe 500 to 1,000 years. This is a very safe prediction to make because you're going to have to take a long time before you can prove us wrong. And we have a changing climate system. But we can put a measure on that. And again, what we really want to do about this which is amazing, is we can put this is actually for a period of 20 years. So we can say for the 20 years that we had, 1996 to 2015, these were the statistics. We can actually do this experiment again for different decades and try to say, okay, can we see a climate change signal, right? Is it moving? Are these extreme events becoming more likely or less likely as we go into a different climate regime? This is just looking at the seasonal distribution, getting more geeky here. But the main thing is once you try to know when they go on, the statistics gets finer and finer. You need more and more data. But let's go on to how do I do this, just to give you a flavor of the method. So we have two methods. Method one is flux counting, is what we called it. And then method two is actually the smart math that Justin and Jonathan were interested in. It's using a Markov state model with a delayed embedding. So I'll unpack that. Method one was where we wanted sort of, when you're going to come up with a really fancy method, you should say, like, what's the standard way to do it? Like, what's a simple way? That's my contribution to the project. Like, ask an atmospheric scientist, what would you do? I'm like, well, I would count the number of events, right, and do the statistics, and we did that. So, and then, it's simple, straightforward. It doesn't handle the statistical dependence, and I said that from the beginning. Like, well, I don't know how to handle that, but I can say, like, let's just count them, right, and then we can compare that. The Markov state model, the beauty of that is we're actually building a statistical model, so it can handle the statistical dependence. We actually, by construction, it knows it doesn't take the fact that all the trajectories in the first few days are doing the same thing. It doesn't get hurt by that. The problem is it's complicated, and I'll try to give it to you in my last 5 minutes. It's also very data hungry. If you don't have a lot of data, using a very advanced method is not really the best idea. These are methods that are used when you've got lots of data. I can do a lot of careful things. But if you have very simple and not much data, it's best to keep simple. So we're going to compare these two methods. Method one is the flux counting. And again, here I have just a simple, to illustrate what happens. Imagine that the blue curve here is what actually happened in the real world. And I've got a couple of years here that happened, right? 1 year, kind of the way winds were varying around and so forth. And then the reds are the ensembles that we send off. These are our virtual words that we're simulating with the high fidelity model. And the idea is that you just count how many SSWs happen per day, right? So if this was January 1st, and this is December 31st, look at, okay, how many sudden warmings? Well, nothing happened, right? I've only got, in this very simple example, I've got four model Earths going on. None of them cross. So I would say there's a probability of 0 going there, right? How about the next day? Well, okay, the next day I've got 1, 2, 3, 4, 5, 6 trajectories going on. Oh, 2 of them crossed my threshold. So I'd say the probability of that day happening would be 2/6 or 1/3. If I look at the next day, okay, I've got how many live? 1, 2, 3, 4, 5, 6. This one stopped, right? That forecast stopped, but I got a new forecast that came in from here. So again, one of them crossed, 1/6. So the idea is you just kind of count the sudden warmings as they go along. And again, it would be silly if this is all the data you have, but I mean, we have thousands of these integrations. So you're looking at these, and Justin like to think of it as a flux because you're looking at how the trajectories are crossing your threshold. It's the flux of trajectories coming across. Okay. The problem is, again, if you launch one right here, very close to an event, all those ensemble numbers will go through it. We have this statistical dependence problem. It turned out, when we went back to the data, it was pretty comparable, actually. Justin was actually kind of annoyed by this. He's like, dang it, my cool method wasn't much different from the very simple method. The cool method actually gives us extra features, which I'll talk about later. But it actually gives us confidence. And I think the key was we had so much data that even though there's this dependence issue, it's not hurting us because, well, there's enough sampling. So that's where we go. Now, the Markov state model is this other idea. And this is really when you go into statistics and you want to understand extremes, what you want to do is you want to build a model of what the system that you're studying. And then if I have that model, then I can really sample that model very rigorously and get all my error uncertainties from the model. So the idea is we use the data to build a new model, and then that new model, we can do perfect sampling with it. It's an analytic model. The idea is it's called a Markov state model, is that you divide the atmosphere into different states. Okay, and here it's super naive. I'm going to say maybe on December 31st, there were just 2 ways the atmosphere could be. It could be a strong vortex or a weak vortex. Okay, and then the next day, on January 1st, there were 3 different ways you could divide it, like super strong, medium vortex, weak vortex, and so forth. And then a Markov state model it's just a very simple model. It's just a jump. It says if I'm in one state, what's the probability of going in the next jump to these different models? It's just you say from each one, and you can randomly sample this. It's just a stochastic process. Okay, and the question is, how do you assign the probabilities of these jumps? And that's where we use all the different trajectories. So if you have all these trajectories right here, and you say from this model right here, let's do these dates. So I have 3 states that I can start in. If I start in state 1, like the strong vortex state, well, I have one trajectory and it goes from state 1 to state 1. Okay, so my transition, it goes from 1 to 1 is 1, and then there's no trajectory that goes from 1 to 2. So the probability of going from 1 to 1 is 1, 1 to 2 is 0. Okay, how about if I start in state 2? Okay, in state 2, I've got 2 trajectories. 1 goes to 1, 1 goes to 2. Okay, I have half a chance of jumping 2 to 1, half a chance of jumping 2 to 2. And then if I started in state 3, here I've got 3 trajectories. Okay, 1 of them made it to state 1, 1/3, and then 2 made it to state 2, 2/3. Okay, and again, it would be simple if this is all the data you'd have. This would be a pretty bad model, but again, we have thousands of these trajectories we're looking across. So you can actually build up these probabilities with pretty high fidelity. And the key is if I had an ensemble that all started here, it doesn't actually hurt me because they just all go along together, and I don't take that extra information. I just say, okay, well, that's fine. Those ones all did the same thing. Okay, and then what you do now is, again, you build this up for the whole model for every day of the year in every state. And now I can get the probability of the sudden warmings at each time, and then do the very good sampling. Now, there's a lot of choices you have to make here. And this is where, sort of the math comes into it. One thing you might ask is, how do I divide the state space into the right bins? Like, how many states should there be? And which ones should you pick if I decided how many? Here we use k-means clustering. This is from statistics. It's a way of saying, look, okay, if I have a lot of data set, can I cluster it into organized patterns that makes, if I cluster it too much, then I'm not gaining much information. Another thing you should pick that, even before you do clustering is what variables you should use. The IFS, this integrated forecasting system's got millions of variables. It's a very complicated model. It's actually not well sampled if you think of every one of those variables as important. So what we had to do is we had to reduce that. And we did that by actually just doing a delayed embedding. So instead of actually looking at states, the states are not like one time. It's actually a little snapshot of a movie. So you look at the evolution over the last 10 days of the atmosphere, but all you had to do was look at the vortex. And then these movies are actually what your states are. And it's kind of characterizing the atmosphere, and not in terms of, oh, it's a state at one time, but actually as a state as it's evolved over the last week or so. And then what you do to make sure that you're doing this right, Justin really did so many different combinations of this. There are a lot of choices here. Do those choices matter? And he found that the choices really don't matter. You can do it different ways, different numbers of clusters, different variables, different embeddings, and you get the same answer, showing us that we really have enough data here to constrain this problem. Okay. So as I showed before, it turned out that the simple naive idea of we'll just count the sun warmings worked about as well as the Markov state model. And why do all that extra work, right? And Justin he's a great guy, but he was a little annoyed. He's like, I wanted my method to be better. The key thing is his method actually allows you to do much more. Okay. I'm going to have, the Markov state model. Once I've got that, I can actually explore the predictability and the dynamics. So if I care about just statistics, okay, fine, you can do it the simple way. But if I really want to understand how the system evolves, how things change, now that I've got this model here, I can really explore and do all these kind of experiments and saying okay, well, how does this model, evolve? What causes the atmosphere to do extremes? What are the features that cause extremes if I wanted to predict them? I'm going to throw up some really complicated, nasty slides at the very end. Poorly explained, complicated figure, I'm being honest. This is what we're doing is we're looking at feature importance using different machine learning methods. You can say, okay, I've got a model. What are the most important features that I want to be able to predict the future for the statistical model? And it's showing us that, okay, it turns out heat fluxes and certain waves, vortex strength, these are the features. And you could go back and then you can do physics with them. The other things you can do is you can start looking at sort of, how does the predictability depend on where I am in state space, for example? And here you can say, well, okay, if on a given day, my winds are 10 meters per second and I've got a heat flux going up, what's the probability of an event occurring in the this winter? And if it has, when is it going to happen? So again, you can make these statistics questions in doing that. So again, I'm zooming by it. So we're just trying to advertise that once you build these statistical models, you can learn a lot more science. I want to jump to the end, the conclusion. The idea is, from these short weather forecasts, we're using our best possible weather models out there, right? Our most sophisticated models, and we can use them to get climatological information about extremes. Okay, the idea is it would be wonderful if we could run a model for 1,000 years and then say, okay, here's the storm of the century. But the way we're going to do it is we're going to say, well, we have this other data set that was created for a different reason. This was a research data set. It was really actually developed so they could compare different seasonal forecast models so we can improve them. But we can piggyback on that and then learn about extreme events. If you've got a lot of data, they're potentially forecast, you use them. It's the best data set, it's the best data available. And we've got different methods to look at them. And the fact that our different methods, sort of simple methods plus sort of sophisticated, give you similar rate information, gives us confidence that we've got enough data here and that we can trust our methods. And we can use this for other features, right? And again, the idea is, if you want to say okay, well, how does one decade vary from another decade? It's really hard when you have extreme events happen, like a hurricane happens. And you want to say, well, was this hurricane related to climate change or was this just a hurricane that happens, right? Hurricane Sandy hit New York. Yes, it was over a decade ago now. My daughter was just learning to walk. I remember that. Was that a crazy event? It turns out, well, it happened about 400 years ago too. And was that event a factor by climate change? You can use these statistical models to say, okay, does the one decade make that extreme event more likely? You need these ensembles. Well, anyway, I'll stop there to keep the stream on time as best I can. Take any questions if you have. Yeah.
Hi, Ed. Thanks so much. That was a really great explanation of some pretty complicated statistical models. Unfortunately, I think we're running a little bit behind. So I think it would be great if you could jump into the chat and answer. You got a lot of great questions, but I think we don't have time to go through them right now. So if you could jump into the chat and answer some stuff, that'd be wonderful. So why don't we bring up our host for the next 2 hours, who you just saw. It's the wonderful Clare Singer.
Thank you, Miriam. Great job, and go get some well-deserved sleep or something. Hi, everyone. I'm back. I'm going to be hosting this next segment, and we are going to have two really great science talks and then a super special panel at 10 a.m. Eastern. So stick around for that. It's going to be great. We have some of our international colleagues who are going to come talk to you about the importance of U.S. science in their careers overseas. So I just want to take a minute to remind us all what we're doing here. If you're just tuning in, welcome. We have just rolled into hour 69 of this 100-hour live stream. It's incredibly exciting. We will be going through tomorrow afternoon into the start of hurricane season. And we're here to first tell you about the really amazing science that all of the people presenting are talking about. Super interesting research, super important research. And it's really important for many things, but it's contributing to public safety. So as we think about going into hurricane season, the research that you're hearing about, the science you're hearing about is what builds our weather forecast, what builds our climate forecast, what helps keep us safe when we have really extreme storms and dangerous events. And all of this research and forecasting capability is funded by the US federal government. So the US has been a world leader for the past many decades, leading this scientific research and forecasting capabilities. We built the first computerized weather forecast models here in the United States, and so much more. This is really a miraculous occurrence, this research capability, and it's at risk. Federal funding is threatened to be cut. Cuts have already happened. As if you were around a little bit ago, when I was speaking, you heard me say that I was a federal climate scientist and I was fired a few months ago. So these cuts are real, and there are more that are on the horizon. If you feel strongly, if you feel compelled, if you feel excited by what you've heard, please go to this link, call your representatives, tell them how much you value climate science and climate forecasting, weather forecasting. It really makes a difference. Your voice matters. So without further ado, we're going to bring on our next speaker. We have Dr. Erin Pettit. She is a glaciologist from the Oregon State University. She's going to talk to us about glaciers, and I'm so excited. Thank you, Erin. Please take it away.
Yeah, good morning. Yeah, it's been really neat to hear all of these talks, and I love thinking about like what's going on both the really short term, so those storms, the intense short-term changes that go on in our weather, but all of that is based on kind of these long-term things that are going on in the background, and sometimes it's not so much in the background. And so I'm going to talk about glaciers. So we often think of slowly moving, changing things, but they actually do influence the shorter-term things as well. And all of these models and data and everything, it all kind of fits together in so many ways. And so, yeah, I'm a glaciologist, and I've worked all over the world. A lot in Alaska, in our Cascade Mountains, in the continental US, and then a whole bunch of work in Greenland and Antarctica. And I'm going to talk a little bit today about our glaciers here, and then I'm going to take you to Antarctica for just a brief showing you like what we do, why it matters, and how it's all integrated. And so, hold on, next slide. So I really would just want to start. I called this talk like ice to water, and how much, and it's about how much glaciers impact the United States and us. And this started a long time ago. Like glaciers have they've been part of the American stories, many American stories for a long time. And things like glaciers carved Yosemite Valley, glaciers gave us Long Island. There's everywhere in the US you can turn, and I can tell you how glaciers impacted where you live, and whether that's directly in terms of the landscape you live on or the water that flows through your landscape in many different ways. And I put this up because John Muir, who helped start our national park system, is really considered the first glaciologist in the US. He's the one who recognized how the science of how glaciers have impacted us. And so where we are right now is glaciers are changing everywhere. We're losing most of our glaciers in the US, and that is having impacts in many places. And we're losing most of our glaciers over the whole world. So I want to start with just some basics of like, what is a glacier? Glaciers start with snow, and snow is amazing. Snowflakes, I had some other pictures of snowflakes in here that I had to cut out, but it is true that every snowflake is different. It affects us all, many of us in many different places across the US. And it's always like fun, but it's frustrating because you have to drive through the snow or whatever is going on in your life. It affects you. But snowflakes are what builds our glaciers. And so when the snow lands up in the mountains, that snow sticks around. And if it doesn't melt in the summer, and if it does that over and over again, over many over many years, it builds up and it gives us a start at ice. And the way we talk about it is that the snowflakes, they start to round, they turn into granular snow. And if they stick around for a long time, they turn into what we call firn, and then that turns into glacier ice. So glaciers are really just giant piles of snow that have turned into ice due to compression. And this is a little drawing that a former student did when we were up in the mountains in Washington State about what a glacier looks like along the distance it goes down down the mountain. And the snow is up in this accumulation zone. I call it the too much snow zone because that's where the snow accumulates. But when that ice gets so big, this is the same ice, pretty much the same ice that you might have in your summer drink. But when you get set to such a big mass, it actually does deform, sort of like red hot iron in a blacksmith shop. So it oozes down the mountain, and it also slides on the water underneath it. And it goes down the mountain and then it melts. And so the key to any glacier is that you have snowfall up high and then you melt down low. And that balance is really critical to maintaining the size of our glacier and to allowing it to grow or shrink depending on what's going on in the climate system. These glaciers are precious reservoirs of our future water. So they, instead of having a dam filled with water, the glaciers are doing that for us. They are storing this water for a long time. They also give us water, just enough water each summer to feed the ecosystems downstream, to feed our ocean circulation. There's a lot of different ways that these glaciers end up impacting us. As they flow down, they will create cracks. Those are called crevasses. I'll be showing you some of those later on. Yeah, they're just incredibly beautiful, but incredibly impactful on our landscape. But this idea of balancing that snowfall in and the melting is really key to how we approach thinking about glaciers. So if it balances the amount of snowfall and then the amount of melt, and if you're at the ocean, it's the calving, so those fracturing that creates that. That's the balance that will tell us how big or how small a glacier will be. And it's very much like your bank account. You're earning money and you're spending money. And the size of your bank account, like what you see when you get that bank statement, depends on how much you've earned and how much you've spent. So if you spend too much, your bank account gets smaller. And if you earn more, your bank account gets bigger. So when we talk about how much ice mass we're losing, it's always that balance between in and out of the glaciers earning snow, and then melting is where it's spending snow. And I want to first start with a little bit of our mountain glaciers here. And this is the South Cascade Glacier in Washington State, which is one of the longest observed glaciers in the world. The United States Geological Survey, our federally funded agency, has been studying this since 1958. And these glaciers, they're tucked away in the mountains. This one is in Washington State, and it's kind of a place that we go to look at how the whole range the whole area is working. And how do we do this? We really have to get on the ground and make measurements on the ground. It's really not something you can just even look to a satellite for many of these. Like, I will talk a little bit about how we do this from satellites, but some of these, it just takes having people going up there twice a year and seeing how the glacier is doing. And we've been doing this for since 1958, and we would like to keep doing it forever. And that is, you know, this particular glacier, I'm hoping that it will stick around for a while. This one is very special to me. It was one of the first glaciers that I went up and did research on back in 1998, I think. And I've been watching this glacier just recede over many years. But let's think a little bit bigger now. So we can watch these smaller glaciers in our mountains go, and they are super critical. But where I want to take you now is to Antarctica. And this is the biggest ice sheet in the world. It covers the entire continent of Antarctica. There's so much ice here that it kind of spreads out like a giant pancake instead of flowing down a mountain. It overtakes the entire continental continent underneath and flows out all the way to the edges where it falls into the ocean. And so I just said that in order to measure a small glacier in the mountains, we have to go out there twice a year and check it out. It's like, well, how do you do that same kind of mass balance for something as big as Antarctica? And it's a really hard problem. It's not trivial. So the total snowfall across all of Antarctica, and then the loss from calving, melt, icebergs all around the ocean, keeping track of that, actually going and measuring that is really difficult. And this has been a hard problem for a long time. So it's been tricky to figure out whether Antarctica is growing or shrinking over many decades. But a team at NASA came up with a really brilliant way to actually weigh, basically it's using gravity to weigh the amount of ice on the Earth. And it's in a pretty amazing satellite system. I don't work on this directly, but I use these data to kind of help me know where to go and what the questions are and how to answer them. And so this shows the over 20-year loss in Antarctica and Greenland. And what I want to point you to is this giant red bullseye in this part of Antarctica. And so the reason this is a bit of a bullseye is that the deep warm ocean waters are coming up close to the ice in this area much more than in many other places. There are other places in Antarctica where that's happening, but this one, this bullseye is where there is the most mass loss, most rapidly changing glacier in the big glacier in the world right now. That glacier alone is contributing 5% of our sea level rise at the moment. And it has the potential to give us something like 2 feet of sea level rise alone. So I want to actually, before I go there, so we got 2 feet of sea level rise from this glacier alone. That will be coming out over a certain amount of time. It's probably not going to stop coming out. But what we want to know is how fast that's going to come. How much sea level rise are we going to get in 5 years from this glacier or in 25 years from this glacier? So these are the questions that we're asking, and where I'm working. So this glacier is the size of Florida, and the glacier itself is not the entire bullseye. There's a few glaciers there. It's the size of Florida, and the area that I study is where it falls into the ocean. And so this is just a little cartoon to help you see what it means when a glacier flows into the ocean. So the glacier is coming off the land, that's in the far upper right. And when it hits the ocean, this ice is cold enough that it forms this floating ice shelf, and then it eventually breaks up into the ocean. What that looks like from a satellite perspective is this. And so I'm going to talk you through this, and then I'm going to play this video. But in the upper right here, again, that's where the ice is on land. This is the main part of the western part of the continental ice sheet in Antarctica. This is the size of Florida. That white line, this white line that goes through here is about 80 miles long, and that is this that is the area where it suddenly goes afloat. So it's sitting on land up here, and then it starts to float down here. And this is a satellite image over the last almost 10 years now that shows the ice flowing off the land and it breaking up into these tabular icebergs. And we're studying this area where that red star is because this is the last little slow flowing area. And that's one of the keys to knowing how much ice we're going to get from this area in the future is how much we're going to lose this floating ice area. And it's breaking up sooner, which allows for acceleration of the ice on land because this floating ice area acts a little bit like a dam for the upstream ice. This is what that looks like when you get on the ground. And so what I do is I go in and we're looking at places where my team is getting the data that the satellites can't get. Like there's so much that we get from the satellites that has been just absolutely amazing, but there's still a limit to what satellites can do. So we need to go on the ground and try to get a better idea of what's happening from the ground based. And this is work that's all funded through the National Science Foundation and especially the US Antarctic Program. And in order to get there to do this work, there's a lot of coordination that happens both between different countries, and the US Antarctic Program is the leader is one of the main countries. Like we do so much of the Antarctic overall, the collaborative Antarctic work that happens is all being led by the US Antarctic Program. All the other many countries around the world are just really love to have this collaborative environment where we can all help each other. But I took a team down there of 8 people, and we had to get all the way out, and you'd see our little pathway through New Zealand, then to McMurdo Station, and out to our little remote site. We do go through, this is McMurdo Station. It's, I'll show you a little picture of it here. It's not the prettiest place, but it's a really functional work base for getting some really good research done. And I really, this is a really important piece of what our federal government has provided the Antarctic research community for a long time. We fly down there using the Air National Guard. Again, this is about collaboration across federal agencies. There's also things that happen in McMurdo Station that are part of the Corps of Engineers. Like there's just a lot. This isn't just one government agency, it's multiple, and everybody works together because they recognize the value and importance of being in Antarctica and doing the science there and how it impacts us. This is what the back of that airplane looks like when we're headed out to our field site. So again, this is not a luxury trip. We really enjoy this, but it's definitely not for everyone. We then skip to a smaller plane to get out to our actual field site. So this is a small plane called a Basler. That's actually, again, an international collaboration here with the Canadians. They fly these planes that get us out to our smaller field sites. And then we spend a month in a tent, sometimes more than a month. This is, we're out there trying to get a good data set because we don't get to go very often. We went to this site twice, and that's kind of all the data we get. We have to pull together, integrate with models and the satellite data we have to really tell the stories. This is another what a typical day looks like. It's not always sunny there. And so we have to manage a lot of trying to work to get some data to help us constrain those models, to help us really understand the processes, to know what physics to include in our models. So it's all part of this, just a bigger place. But we're there to do the science. So this is our science tent. We do have a little tent that is kind of our hub of science. We use snow machines, we use skis, and we're out there to collect some data. This is just a couple of examples of key things we want to get. So this is what we call fern coring. So we're just going down about 30 feet or so. And this gives us actually weather over the past 5 to 10 years. So we can see all the different storm layers in that and start to date those and figure out what's been happening down here over the last 5 to 10 years to help us understand the system. And then this is me going for a long walk and pulling a little sled. But this is me collecting ice penetrating radar data. And I'll show you a little bit on the next slide. This is a little bit like it uses a radar, so a radio wave that goes down into the ice and helps us image the interior of the ice. And so this is sort of a radio version of ultrasound that you would get on your body to help see the inside of your body. So it's one of these things where you see the image and the doctors know how to read it, but it's not always obvious to you as the patient. In this case, I know how to read these, and many of us do, but it looks a little funny to those people. So in this case, I was standing on top of the ice, way at the top. The radio waves go through the ice, and they are reflecting off of the ocean at the bottom, and that's this kind of noisy, brighter stuff at the bottom is the ocean. And what I want you to see in this is that it's not just a nice flat ocean boundary. It's got these like cutouts at the bottom, and then the red dots are outlining where there are fractures coming up from the bottom into the ice. And those fractures are telling us how weak or strong the ice is. Like where there's more fractures, the ice is weaker. And this is what we're really interested in trying to get at, because this ice has been melting, but it's also now falling apart and fracturing. We can also see these same cracks from underwater. And so this is part of an international collaboration that we had where the US-based research ship went down, and a Swedish scientist joined our team in order to use an autonomous vehicle underwater to look up at those same fractures. So I was imaging them from the top, looking down. She's imaging them from the bottom, looking up. And it's giving us a really interesting picture of what's really going on with this ice, which is the ultimate question is, how far are these fractures going to break through? Is this going to fall apart into a bunch of icebergs and change this whole system? The other thing we can do with these fractures is actually listen to them using seismometers. The same kind of seismometers that we use to study earthquakes, we can use to study ice quakes where it's fracturing through. And this is just a little blip of our data. And this is my graduate student recovering one. It's a really tedious process to go through and get each one and make sure we collect the data really carefully. And so we do, it's a lot of fun, but really hard work to get out there. And then we have to come home, we process all these data, we understand, we try to use these to link to the processes, and then we share and try to help understand and get them into the models so we can figure out what's happening. So to kind of summarize, this Thwaites Glacier in particular has a lot of warm ocean waters that have been coming in more and more recently, and they're eating away at this coastline in Antarctica, which has been weakening this whole glacier, the floating glacier extension. That's causing this fracturing and breakup of this ice. And as that goes on, it accelerates the inland ice, and all of that heads to sea level rise. And this is where this is directly related to what happens along the US coastlines. It is changing the sea levels all over the US. This happens to be in coastal Oregon, where I live, where higher tides are getting higher. It means those storm surges are going to have different impacts. There's coastal erosion everywhere. It's all interconnected in that the sea level rise is feeding into how much like hurricanes impact a particular coastline. And so it goes on. Really important. So I want to just end with this, leave with this video, and the one thing I really do want to just put out there is that ice, whether it's ice in our mountains, it's sea ice in the Arctic, it's ice in the Antarctic, ice is a critical mineral. So thank you.
Thank you so much, Erin. That was fascinating. Folks have so many great questions and are expressing a lot of excitement for your work. They're loving the videos and a lot of appreciation for how hard it is, what you do in the field. So thank you for all that effort. I want to start off with this question from maybe our youngest listener. We've got Malcolm, who's 5 years old, who wants to know, what is a glacier?
Malcolm, such a great question. You know, a glacier is this giant mass of ice that sits typically in the US, it sits up high in the mountains. But if you go to Alaska, those mountain glaciers then flow down into the ocean. It's just a big pile of ice. And it's formed from that compacting snow year after year. It takes a number of years to really turn snow into a glacier, because a glacier, once we define a glacier, it has to actually start moving under its own weight. It's a little bit like silly putty. If you take a ball of silly putty and set it on your desk or your table, you'll slowly watch it ooze outward. And that's a very good analogy for how glaciers flow. They have to be big enough to get that flowing motion, because they are ice, solid ice, like what's in your freezer.
That's great. I love that. I hope Malcolm knows what silly putty is. I think that's a great example. We had a lot of questions in the chat about permafrost. Not something you talked about, but people wanted to know kind of what's the difference between glaciers and permafrost. What's going on with permafrost?
Sure,
They hear
yeah.
about these words. Yeah.
Yeah, so permafrost is when you're in a place. I lived in Alaska for 12 years, so I do actually know a lot about permafrost from both my daily life and from research that goes on. And permafrost is, you get permafrost where the average annual temperature, so the seasonal summers and winters, are below freezing. And so the ground the little surface of the ground warms up in the summer, but there's deep freezing underneath. And it doesn't have to be soil and water freezing. You can think about solid rock and water inside cracks freezing. And this is a little bit of what happened in Switzerland this year, that the rocks were no longer being held together by cold. But yeah, the permafrost is melting everywhere in the Arctic. And where I lived in Alaska, I was just telling people that I had a little outhouse on my cabin when I used to live up there. And the outhouse was not doing so well when the permafrost underneath started to melt. And that's not something you want to have to deal with. And
Yeah.
so yeah, it is creating weaker landscapes. So that's when the ground itself is frozen, and there might be ice mixed in there, but it's so it is an icy feature, but it's a little different than glaciers. And glaciers often have permafrost around them. So that's so there's on the outsides, and depending on where you are, they have permafrost around them. So.
That's great. You just brought up, and someone had asked about this, the tragic event that happened in Switzerland with the glacier there. Can you talk a little bit about the physics of what was going on at that event?
Yeah, sure. Yeah. So there, the very top of the mountain fell apart because of the warming of that rock. And so it was between the freeze thaw cycle and the cold up there, it started to weaken and it collapsed. It landed on a glacier. And sometimes you might think, well, if you just pile a bunch of dirt on a glacier, what's that really going to do? But glaciers can be really sensitive to, they slip and slide down the mountain, just like another of our kid toys, the slip and slide. They have water at their base and there's water in them. And especially in the spring when the snow is melting, there's a lot of water around. And what happened there is that pile of rock landed on the glacier and basically triggered extra sliding at the bottom. And that then started this kind of domino effect of collapsing parts of the glacier and sending this big flush of water and ice and sediment down into the valley. And realistically, like, this is one of the things we're concerned about with the glaciers on Mount Rainier. Mount Rainier is a volcano in Washington State, and the upper mountain there is sort of undergoes this process where the rock gets weaker through time, and we could have that exact same thing happen on Mount Rainier, and that would similarly destroy a lot of villages. So a lot of villages are what we call small towns, up to, Tacoma, Washington, which is not so small of a town. So these kinds of things, it was really scary what happened.
Really scary.
Really important. So.
Okay, well, thank you so much. I think that is the end of our time. Was a really wonderful presentation and just so great to have you on.
Well, thank you all for doing this.
Yeah. Okay, so excellent. So before we move on to our next wonderful speaker, I just want to take a minute again to remind us why we're all here. We are halfway through our 69 out of 100. We'll be going through Sunday afternoon. We're going into June 1st because that is the start of hurricane season. So we're here to talk to you all about the amazing climate and weather science, research, and forecasting that is done in the United States and funded by the US federal government. This work is so important, it keeps us all safe, and it's so exciting. It's really a miracle what we have been able to accomplish through the sustained federal funding in this country over the past many, many decades. We're here because that funding is at risk, and we need all of your help to support it. If you are feeling inspired, excited, passionate about the work that you're seeing presented here today, please use this link at the bottom. We have a app set up. It has a little script for you to help you know what to say. You can call your representatives. Just tell them how excited you are about climate and weather science, and how important it is to you that it continues to be funded in this country. We are at risk of losing funding for research, for our federal labs, for our weather forecasting offices that are providing all of the forecasts that keep us safe, especially as we go into hurricane season. Again, that starts tomorrow, the official start to hurricane season. And so this couldn't be more timely. With that, I want to welcome our next speaker. Hello, Paquita. Can you hear us?
I can hear you just fine. Can you hear me?
Beautiful. Yes.
Wonderful.
Thank you. Welcome. So our next speaker is Dr. Paquita. I'm going to mispronounce your last name, and I'm so sorry. Zuidema. And she is a professor at the University of Miami. And she has done just a lot of amazing research in my field of science. So I'm very excited to have you on here today. She's an expert in marine low clouds. So if you were here a little bit ago, I was talking about those, and she is going to talk about some marine clouds in our polar regions. So thank you so much, and please take it away.
All right. Well, thank you, Claire. So and it's great to follow up on Erin's presentation on Antarctica. This one is based, this is more about fieldwork that's happening around the Arctic. And in particular, this recent campaign that happened a year ago based out of Sweden, where we were looking at cold air coming off of the Arctic sea ice and moving southward, and how that was interacting with the atmosphere. This was a really big project. It was $8 million international. It brought NCAR's C-130 plane. It's one of its flagship research planes up to the high Arctic for 6 weeks, where we were just focused on this one goal of sampling the air that was coming off of the polar ice cap. So why were we doing this? It's Arctic air plunges south. That this is common over the U.S. in the winter as well. So this is an image from earlier this year. This is what they look like. They're really beautiful. It's this very cold air that moves over the warm waters, and a lot of heat and moisture fluxes up into the atmosphere and develops these cloud patterns. It's not only beautiful, it's also very economically important to the U.S. This is the same scenario from January, where snow reached New Orleans and there's this cute photo of a snowman in front of their church in downtown New Orleans there, and a lot of records were set in snowfall on that day. So understanding what generates these processes and what exactly it means at the local scale in terms of temperature and precipitation is something people are going after at the moment. It's not very easy to model because it is dependent on both these large scales, these large circulation influences, and then at the micro scale on how this ends up converting into the precipitation that we feel on the surface where we live. So there's a lot of interest in the Arctic at the moment. This is a statement that's often made that the Arctic has been warming faster than the rest of the globe. This paper only came out a couple years ago. This number of 4 times faster gets kind of debated, but at any rate, it's there's agreement that the Arctic is warming faster. We're losing sea ice as part of that whole system, and what we don't necessarily know yet is what this diminishing sea ice means for these outbreaks of the cold air. So one point of view would be that because the Arctic is getting warmer, that you would expect the air that flows south towards the mid-latitudes would be milder as a result. So that that's a very fair, intuitive way of looking at it. Another point of view is that, well, as we're losing sea ice, then that means there's more water, more warm water that can pick up moisture into the environment, and that then translates into heavier snowfall when it reaches the coast. So that's been shown along the Norwegian coast. And another aspect to this is from a purely economic point of view, that as we're losing the sea ice, it opens up more shipping channels. And this figure here shows where the shipping is occurring. You can see that there's the Northwest Passage. There's already boats going through the Northwest Passage. It's that little thin purple line going through the Canadian archipelago. So there's interest in understanding what will happen with the sea ice in, not next year, next decade, just from thinking about whether or not to send more shipping there and avoid some of the longer routes. So that's, why should we go to the Norwegian Sea rather than just go off of the coast of, say, New York to sample, to understand these outbreaks better? We're doing that too, but there is something kind of special about this open water that's north of Scandinavia, in that this is the place where warmest water from the Atlantic Ocean reaches the furthest north. And so you have this warm water from what's left over from the Gulf Stream right next to the polar ice cap. So it's a area of extremes. This is also the part of the world where the cooling of the ocean is such that it helps drive the oceanic circulation as well. So there are reasons to go here, rather, as well as just looking off of our coast. So yeah, this is one of the days during our campaign. We were there in March. So a challenge with these aircraft campaigns is that you want to go when there's enough light that you can see by, but we were interested in these winter conditions. So we wanted to go as early in the year as we could, but still have enough light to fly by. So when we were there in March, the air over the Greenland ice sheet was about minus 25 Celsius, and the water was a bit above freezing. So this is the kind of patterns that you get in the cloud streets, and you see how first there's these the cloud streets develop. These have to do with the wind patterns as well. And then further downstream, it sort of starts to split up into these more open structures as the clouds could precipitate out. So we want to understand these type of transitions as well. So here a leading question is that, so this is from one of our flights. These clouds are about minus 25 Celsius. You look at them and they look a lot like the Stratocumulus clouds, the clouds that you see off the coast of California, meaning that they look like liquid clouds. That actually is what these clouds mostly are. It's liquid that's existing below the freezing point. And that's actually, that's counterintuitive, right? We don't really experience that in our homes that much. We put water in our freezer and it turns to ice. But in nature, in cloud drops, this doesn't necessarily happen. So in fact, pure water droplets only freeze at a temperature of about minus 40 Celsius. So that's quite cold. So to get an ice particle, you need something to get a cloud ice, a snowflake. You need something that the cold air can nucleate around, and these ice nucleating particles are very rare, especially in the Arctic, which is a relatively pristine environment. So only one of about 50,000 particles is able to nucleate a piece of cloud ice at minus 20 Celsius. So this explains why we see so much liquid. And this also has, liquid clouds tend to last longer. Once they turn into ice and snow, then they're able to grow pretty fast and they start to fall out of the clouds. So that changes their ability to reflect light back to space a lot, just depending on whether a cloud is either liquid or ice. So we want to try to get at this. So this basically says that you see in this image that this is the cloud fraction is very high in this image, and that's because these streets are mostly liquid. And it's only down at the bottom of the image that you're starting to lose that cloud. And that's the point where they're also turning more into ice. So in a nutshell, we hope to understand the Arctic weather and climate and how that's changing, what it means to us. And with the word climate, I guess I'm thinking of anything that's longer than about 10 years, which includes kind of beyond our ability to forecast on a winter time scale. So at that, the Arctic is climate, the weather and climate in the Arctic is so variable that there's a lot of internal forces on what a winter can look like. It's not just all about rising carbon dioxide levels. So it's complicated, and we still don't really have a good handle on how to predict what the Arctic is going to look like in a decade from now. And then, so that's kind of the more immediate goal. And then to improve our predictive capabilities, we also need to understand how the clouds distribute the liquid and ice. So, so this is the plane. This is all the stuff we have on there just to kind of measure the cloud sizes. The reason why there's so many probes, and I don't have a nice graph showing this, but each of these probes is only getting a part of the cloud. It's either only getting the liquid or only getting the ice, only getting the large particles or the small particles. Some of these are going after the nucleating particles. Those are even tinier. So there's a range of scales that's like 6 orders of magnitude that these are trying to capture. So that's why there's so many of these little probes in there. Yeah, and then we also have, to kind of give us a bigger scope of the context of the cloud, we have these remote sensors, radars and lidars and microwave radiometers that just give us a bigger scale of this. A lot of people are involved. It draws on researchers from all across the U.S., many different universities. It's a wonderful opportunity to educate students and just show them, I mean, there's nothing like seeing senior researchers argue in front of you about what they think is going on. It just really communicates that there's still a lot to do for the next generation. This is what we did. These are the flights that we did. We had this goal of reaching the Greenland ice sheet and then flying back from there. So here's an example. This is one that a nice gift that my student made of a typical, of one of our flights. So in this case, the circle there is a low, and there's air circulating around that, and we were kind of going after how the clouds are breaking up into an open section there. So something kind of interesting for us is that while we were there, even though we were headed into the spring, the sea ice was actually growing while we were there. So there's multiple lines there, but that maroon line is what the sea ice extent was towards the end of our campaign, and it was further out than the kind of white pinkish line that you see. That was when we started. So and that's because the sea ice it's actually very sensitive to what the atmosphere is doing at that time of the year. So you get cold air spilling out over the warm water, and that generates this new ice growth. There's a example of it in the bottom of that photo there. So that actually that leaves behind, takes some of the sea salt doesn't freeze, so it also changes. So this helps with the oceanic convection at the same time. So we had 3 flights that reached the Greenland ice zone. I'm going to focus on the one where we were able to reach an ice cover of 100%. So we were upwind of these cloud streets whose evolution we wanted to understand better. So this is how we would do these flights. We would fly out high because we were very worried about icing on the plane, right? The plane itself is a great ice nucleator. And once the plane ices up, then you can't get data. B, you're putting the plane and yourself in harm's way. So the pilots are very careful with us to not have that happen. This is what we were seeing on the way out, this new ice that was developing. There's sea smoke in the image there. That's in the bottom left, where just vapors coming off of the ocean. The radar image at the bottom shows how the air near the surface of the sea ice becomes more and more stable. So in more and more thin and low lying to the surface. This is a complicated slide, which I think I'll skip for the sake of time. But the atmosphere is fairly clean. The surface was about minus 30 Celsius at the very end of it, and then the image at the bottom it's a lidar image, and it shows it's starting to pick up the sea smoke on the way back. The first detected particles were ice, which is odd because we know at this temperature range there really should be liquid first before it can be ice. So in the spring, there's actually a lot of pollution that is brought into the Arctic from the mid-latitudes, and it kind of sits there. It can't fall out very easily. So in this particular flight, it looked like these ice nucleating particles were pretty well distributed throughout the atmosphere. Yeah, just to affirm that most of the clouds we sampled were pretty cold. We also were able to look at a polar low flight so you see the circulation in the middle there. That's polar lows are like little hurricanes. They can be very destructive, and we were lucky to be able to sample one pretty well. They're very hard to forecast because they are so small. So we were excited to be able to do this. This is something that my student and I are trying to understand better, how liquid and ice are and precipitation are affecting this change in the cloud structure. And let's see. Well, a big thank you, of course, for the opportunity to do this. And I hope I kind of communicated why this research is important and why it's important to keep this plane in the air. The United States is very lucky to be able to have an economy large enough to support a fairly expensive research plane. Not every country can do this. So you can also think of this as part of our contribution to this planet to try to understand what's going on better. And I want to leave you with, I have a video, it takes about a minute, that I set to some music. I'm going to see if it works. Okay. Okay, thanks for indulging me on that. But I wanted to show this also just to communicate that we live in this beautiful, complex planet that we don't necessarily understand every aspect of. And it's also just serves our humanity to just appreciate where we live and to try to take care of where we live. So thank you for your time.
Thank you so much, Paquita. That video was amazing. Your presentation was amazing. Everyone in the chat was just loving it. All of the pictures you showed of the field work, absolutely beautiful and so inspiring about making us curious about what's going on in these corners of our planet that we don't get to go to every day. We had a bunch of questions. People were so excited to hear about super cooled liquid. So I want to take this question. There's two that are kind of very similar from Kelly and Manda. What is special about minus 40 degrees Celsius? Why are these liquid cloud droplets remaining liquid in our atmosphere? Why are they not freezing? Can you tell us a little bit more about that?
So if you think of what a snowflake looks like, it has the 6 prongs to it. Ice particles are in this lattice. They they're in a very particular kind of a pattern, whereas with liquid droplets, the water vapor molecules are they don't have to be that arranged. They can just they have a positive and a negative electric dipole moment, and they sort of can interact freely. It's like being at a party. You can kind of move around from person to person and have a conversation. But with an ice particle, it's like being in a sitting in a classroom, like you're kind of locked into your seat. So this is actually not a bad analogy, because think of trying to get a bunch of people that are milling around to take a seat. It doesn't just happen quickly. You need to organize people and encourage that behavior. And same with these water drops. It just doesn't happen right away. The situation needs to be right. And so ice nucleating particles, the ones that work well, like silver iodide is used a lot at snow resorts. And that's because silver iodide has a crystalline structure that looks a lot like what an ice particle looks like. So that kind of makes the water vapor molecule comfortable enough to go into the ice form.
I love that analogy. That was awesome. I haven't heard it before, but it's super, super clear. We have a question from Sydney. I think you had mentioned something about how the sea ice is really sensitive to what the atmosphere is doing. And so Sydney was taking that one step further. Does that mean if we abruptly stop emissions, that the poles would bounce back, that we would regrow our sea ice or our land glaciers quickly? Or is that maybe a little bit not the right interpretation?
Oh, that's an interesting question. I bet other people have thought about this more deeply than I have. But one thing, so I don't necessarily think it would bounce back quickly, because there is this albedo effect that happens that there's this positive feedback loop that happens. Once you start to lose sea ice, then the ocean absorbs a lot more sunlight, so that kind of keeps going. If you were to stop the carbon dioxide emissions, actually, I would trust Claire's perspective on this, because she's thought more about the larger scale, longer term impacts. But I would not expect the poles to bounce back quickly. And I also think it would take us a while to be able to detect that the poles have bounced back. There's kind of an interesting thing happening right now where the loss of the sea ice is not happening that quickly anymore, even though emissions are still increasing. I might have oh yeah, that's right. Okay, here. So this figure on the right here shows what the trend is in the loss of sea ice. And it's actually flattened out in the last decade. So there's also these other impacts besides just the emissions, and we don't entirely understand those.
Yeah, yeah. These Arctic and Antarctic regions are really complicated. That's a great question, though, Sydney. I think if you were here for the previous talk, also, Erin was speaking about glaciers or ice that's on land, and that is quite different from sea ice. When we melt those glaciers, it takes a really, really long time for them to reform. So that definitely I don't think would be a reversible process on a quick time scale. The sea ice, maybe you could you can imagine that sea ice forms on a few years, but those big glaciers like the Greenland ice sheet or the Antarctic ice sheet, those form over hundreds, thousands of years.
Right. That's
So
a good.
unfortunately, yeah, it's not a super reversible process. It's why we want to, stop emissions as soon as possible. Okay, great. Thank you, Paquita. I think we are going to move on to our next scheduled event. That was a wonderful talk. Now we're going to take a break from our amazing scientific talks, and we're going to transition into another panel discussion. So we are just about to kick off our 70. I can't believe it. We are going strong, 70 out of 100. And for this next hour, we have a really special event. We are going to be hosting a panel with some of our international colleagues. So I'm very honored to be hosting this. These are folks that are very big names across our field, and we're just so grateful to have them here. And we want to hear from them about the importance of U.S. science and U.S. scientific funding in their lives, in their research, in their countries, at their institutions, because we know that our climate system is globally connected. Things don't just happen in the U.S., they don't just happen in Germany. Everything is connected together, and our scientific community is connected together in the same way. You have heard from so many amazing speakers about the wonderful international collaborations. We just heard about Antarctic research, Arctic research. Those fieldwork campaigns, they are super expensive, and they have huge groups of people from all over the world who work together to collect that data. And this international community, it's really special. But we also know that the US has been a leader in our field and a leader in funding this work. And so with that in mind, we're gonna talk to our panel. I'm gonna start off with some questions that we have prepared ahead of time, but then we're gonna have plenty of time to take questions from all of you in the chat. So please stay tuned, stay attentive, and we're going to be so excited to answer your questions in a minute. So I would like to just start off. We're going to have all of our panelists introduce themselves just very briefly. Could you please say your name, what institution you're at, what is your role there, and just a few sentences about what your subfield of research is, so that our viewers know a little bit about you, and then we'll come back around for more questions. So why don't we start on my screen? We'll go with Nicholas.
So hello, everyone. Thank you so much, Ian, for this amazing opportunity and for doing all of that, I think, on behalf of US Science, which is in dear need of such exercises and support efforts. So my name is Nicholas Gruber, or short Niki, and I'm a professor here at ETH Zurich in Switzerland. And I work primarily on the role of the ocean in the climate system, and also do a lot of work on the carbon cycle. I'm also currently head of the department, and also have been director of the Center for Climate Systems Modeling, which is a joint effort of ETH and several other institutions here in Switzerland.
Thank you so much. Thank you for your time. These folks are all really important, busy people, so we're so grateful to have them here with us today. Bjorn, can you please introduce yourself?
Hi, my name is Bjorn Stevens. I'm a director at the Max Planck Institute for Meteorology, and I work in the field of climate physics, mostly with an emphasis on atmospheric processes. And I'm not that important, and I'm not that busy, so.
Please don't undersell yourself. Okay, Susan, you're next.
Hi, I'm Susan Trumbore. I'm also at a Max Planck Institute, the one for biogeochemistry, but I maintain a toehold in US Science as a member of the Department for Earth System Science at UC Irvine. So I'm really happy to be here, and thank you, Claire, and everybody for doing this job. I've been watching a few of the live streams, so it's really nice.
Amazing. And Tim, last but not least.
Thank you very much, Claire. So Tim Palmer, I'm based at Oxford University, where I've been a Royal Society research professor, and actually where I did my PhD originally in theoretical physics. But in the intervening years between the Oxford, the sort of sandwich in the middle, if you like, is that I've worked for pretty much a quarter of a century at the European Centre for Medium Range Weather Forecasts, and worked with people developing ensemble prediction and seasonal prediction, with many fruitful interactions with the US.
Amazing. Thank you all. So I want to just start off, and I know that many of you, if not all of you, have actually spent some time working or living in the United States. So I want to get a bit of a brief biography of your career. When did you work or study in the US? I want to hear about what is your relationship with US science, and if you have any active or really notable collaborations that you've had with US scientists over the years that you would like to highlight for our listeners. So I'll mix up the order for these questions so we don't get bored. But why don't we start with you, Susan, since you said that you actually have an active affiliation at a US university.
Yeah, so I'm proud that I helped start I was one of the founding members of the Department of Earth System Science at UC Irvine. And I'm continuously proud to keep collaborating with everyone there. And yeah, it's hard to see people losing their jobs now at UCI because of canceled grants and things like that. So yeah, so I'm an American. I got my PhD in Lamont Doherty, then Geological Observatory with Wally Broker. Yeah. and then I moved to, I did a couple of postdocs. Most of my work is measuring radiocarbon by accelerator mass spectrometry. So I worked in a couple of labs, including Lawrence Livermore National Lab. And then I moved to UC Irvine and spent 20 years there. And I guess you could say I'm part of the brain drain to Europe because I consistently got funding as an assistant professor at UCI from these big programs that you talked about, big NASA the NASA terrestrial ecology programs like Boreas, the study for climate atmosphere interactions from boreal forests, and also LBA, the large scale biosphere atmosphere interaction in the Amazon. So most of the research that I'm still doing grows out of what I learned in those big interdisciplinary problems. So for example, we now have our own biosphere atmosphere observatory called the Amazon Tall Tower Observatory in Brazil. So I maintain active collaborations with people at Lawrence Berkeley Lab with climate modeling and improving climate, sort of carbon climate models. So I have lots of connections, I guess.
Amazing. Niki, why don't you go next?
Well, I would say that actually scientifically, I really grew up in the United States. My first encounter was actually in the late 1980s. I was a student here at ETH, but I decided to go to the US for a year and had the amazing opportunity to work at Scripps Institution of Oceanography for a year with the late Dave Keeling. And so I really got into carbon cycle research early on. And also, interestingly enough, in the late 80s, also already sort of the first sort of hardcore discussions about the realism of climate change, and particularly the then director of Scripps Institution of Oceanography, Paul Nirenberg, was a very strong skeptic and very politically influential. And Roger Ruel was still around at the time, and so I was suddenly exposed to all of these discussions about climate change. And then while doing my PhD here actually in Switzerland, I spent about a third of my time actually in the US with Dave Keeling. Then I did my postdoc at Princeton University for 3 years, actually also with funding from the US, from the NOAA Global Climate Fellowship, great program, and been very influential in supporting me as a postdoc. And then I became an assistant professor at UCLA and spent 6 years there. And then I had a 2-year transitions over to ETH. So, and even today, I think a very substantial fraction of my research is still done in tight collaboration with people in the US. So a lot of, particularly on the observation side, from people from NOAA, but also on the modeling side from various modeling centers around the US. So I would say probably half of my research contacts and collaborations are really in the US. So really for me, it's what's happening right now is both personally very devastating, but also scientifically devastating.
Yeah, definitely. It's great to hear you're also a fellow NOAA CNGC alumni. So
yes, I am.
It's a very prestigious group I'm honored to be part of. Yeah, a wonderful program, and one of those programs that has been canceled for this upcoming year, very unfortunately. Why don't we hear next from Bjorn? Keep the UCLA train going.
Right. Yeah, I'll work backwards. I was at UCLA more or less at the same time as Niki. I lingered for a bit longer, but I kind of grew up in a sort of academic way at UCLA. My training was entirely in the United States, so I did my undergraduate and graduate at land-grant colleges in Iowa and Colorado, and then postdoc at NCAR. Like Sue, I also benefited a lot from the facility access that you had in the United States. So I got involved in measurement campaigns using common facilities through NCAR. I got involved in climate modeling using common facilities also made available by NCAR. So the support for public education and the support for scientific access, actually also for people who are just getting started in the field, was really important for my professional development. And today, of course, I have many colleagues and friends in the United States, and I also look forward to the steady stream of talent that normally comes through programs like the one you just mentioned, Claire, because they enrich science worldwide. And so the United States has been I'm also I hold U.S. citizenship. So like Susan, I'm also working somewhere else. Yeah.
Excellent. Yeah. It's amazing to hear how all of you are, so connected to U.S. science, even though you are working in other countries. Tim, let's hear from you now.
Thank you. I just thought I'd mention two things quickly. The first is I spent a year at the University of Washington over on the North Pacific Northwest, 81, 82, long time ago now, under the invitation of the late Jim Holton. He employed me as one of the NASA postdocs on a NASA grant he had. And in those days, I was working on stratospheric dynamics and started to develop the use of potential vorticity as a diagnostic for looking at sudden warmings in the stratosphere. And this led fairly quickly to a paper which has become quite well known now, which I co-authored with Michael McIntyre from Cambridge on braking. We discovered braking, that Rossby waves can break in the stratosphere. This was a feature that arose from looking at the sudden warming in this particular potential vorticity framework. And I would say that work has been quite important for a number of reasons. The lack of Rossby wave breaking in the southern hemisphere is the reason why we have the ozone hole over Antarctic, but not the Arctic. And also it kind of triggered an enormous explosion of work around the world of using potential, and by the way, ETH has been a leader in this very much, of using PV, as we call it, potential vorticity, as a diagnostic, not only for the stratosphere, but in the troposphere as well. So this is kind of work that really sprung out of this early sort of study in Seattle with people like Jim Holton and others there, Conway Leovy, Dennis Hartman, Mike Wallace. I mean, it was a very strong department. The other thing I wanted to say, and by the way, I came within epsilon, probably epsilon cubed, I think, to accepting a permanent job there. I mean, it was such an attractive place to live and work And it was really just some family issues. And then I got offered an ECMWF job. And it was just an agonizing decision for me. It's the worst decision of my life, trying to decide between Seattle and Reading. In any case, the other thing I wanted to say was, when I worked at ECMWF, I got interested in seasonal prediction. And the world leaders there were clearly people in the US, people like Mark Kane, Steve Zibiak, George Philander, Jagdish Shukla, Peter Webster, Kiko Miyakoda, many others I could talk about, Ants Liebmer. These are all in the US. So I would go over routinely, and I got involved in the TOGA, the WCRP TOGA program and CLIVAR program subsequently. And that I really learned. I mean, I knew nothing about oceanography before interacting with people like, say, Mark Kane. And I'd just like to say that today, Europe is pretty strong in seasonal prediction through programs like the Copernicus program, which is a big EU program. But it basically all derives from that leading work that those US scientists did. And it just sort of exemplifies the best of climate science, which is international collaboration. I mean, we can talk about this some more later, but this just typified all that was good about climate science, and what made me glad to have changed fields into climate science, that it was exceptionally collaborative. People weren't being secretive or competitive, they were just being collaborative, and it was benefiting everyone around the globe. And now, of course, seasonal prediction really does benefit everyone, not just the scientists. So those are two of my interactions in the US, which have been pretty important for my career.
Tim, half of the people you mentioned were foreigners. I just wanted to bring that out because the U.S. has always been such a melting pot. It's where many people from around the world would go and meet. That sort of openness served as a mixing pot for lots of great ideas.
Yep.
Maybe just one thing to add, because I said at the beginning, that sort of scientific upbringing was really structured by the US. And when I look now at my own sort of type of work, how I interact with people, how I work with my peers, that sort of foundations of this work is very American, but it's been very inspiring as a result, because exactly that collaborative nature has been instilled for me from the very beginning, and that it was just normal that you work that way. And I think that influence, the cultural influence on how we actually undertake our science, has been a strength of the US from the very beginning, and has been inspiring and also I thought, for me, as a foundation of how I work today. And I think that, so seeing that a bit breaking off has devastating effects, not only for what you do, but also how you do it, how you work together.
Yeah, that's a beautiful sentiment about the collaborative nature of our field, but also, yeah, very, very tragic to think about it potentially disappearing. I wanted to bring up, I think it was Susan who maybe mentioned this. In the US media, we've been hearing people talk about this potential brain drain, people leaving the country. We wanted to ask you all on the other side of the Atlantic Ocean, have you started to see any brain gain? Are you seeing scientists coming to your institutions already? Is that something that we can maybe look forward to as a silver lining, or how do you feel about that? Whoever wants to take this question first. I don't know if we all need to answer every question, but if anyone feels strongly.
Well, certainly I've had a number of emails from distinguished US colleagues kind of making inquiries, let's say, and clearly people are thinking seriously about this. And I know a number of European countries are kind of trying to, make funds available if there were serious applications. I don't know whether this is an appropriate analogy, and I'm not claiming it's a perfect analogy, it's not a perfect analogy, but The UK, for example, benefited enormously in the 1930s from the exodus of Jewish scientists from Germany, and the US did as well, actually, of course. So as I say, I'm not trying to sort of say there's an equivalent kind of level of persecution here, but nevertheless, when people do feel unhappy with their situation, and science is an international field, so scientists, perhaps more than any other kind of discipline you can think of, are kind of, more movable. So we have examples, I think, looking back in history where there has been a movement. It has certainly benefited the host country enormously, and it's certainly been to the detriment of the country from which these people have moved. It's not something I don't feel happy about this in a sense, but it's just a fact of the matter. Scientists are quite international people. You've talked to us already about this, so we are potentially movable if we don't, if we don't feel we're getting the resources and the infrastructure needed to do the work we want to do, we feel we ought to do.
Susan, do you want to answer this too?
Oh, go ahead, Bjorn.
I was going to say maybe I don't put as much stock in the brain gain and drain. I think the bigger factor is the fact that the U.S. was a place that many people from around the world could go to advance themselves intellectually. And the big loss are, your generation, Claire, in the sense of the young people who would go there and do brilliant things from around the world. So that might not be a drain because they won't get there because of some of the policies. It might be a reflection. So you see a real uptick in applications from, the best and the brightest. Say, if you look between China and India have about, 3/8 of the world population or something like that, or a third, a little bit more than a third of the world population. And the United States, over generations, especially with the, since the middle of the last century, really was the place that people went to if you were interested in science and new ideas. And that's been called into question. And that sort of damage that will be generational, that will happen for a long time. And so in addition to the brain drain, I think sometimes we're overlooking the fact that the closing of the doors in some way of U.S. science to the best and the brightest from around the world is really going to do lasting damage to the ability of the society there to profit from the insights these people bring.
Yeah, and maybe I would just add, there's also, not everybody who loses a job can immediately move to another country. They have family, they have other obligations, but also I think there's no way all the goodwill in the world that the EU or other countries with enough resources can absorb the sheer numbers of people that are going to, are at risk. And so there's tremendous concern about, the loss of continuity of all the things that people do, right? That the records that are kept by NOAA and NASA, and if those data streams stop, the whole world suffers. So I think there's tremendous goodwill to help however we can. I know the EU is looking for ways to assist things, but we know that, we can't replace it all, and for reasons like what Bjorn said, it's also where we send our students, our best students, so that they get experience in the kind of collaborative atmosphere and way of doing science that the US has.
Yeah, thank you.
Sorry.
Go ahead, Niki.
Apologies. I can confirm that because I see this already with my doctoral students, that it was obvious 5-10 years ago or 20 years ago, the place to go as a postdoc was the US. Now, at the moment, nobody wants to go to the US for a postdoc. I mean, this is going much faster than the reverse. And the second piece, I think we're in Europe. I don't think we want this drain to happen. I think this is not in our interest. Of course, we're here to help and want to help, but the first and foremost, I mean, the best thing we can do is to help you guys in the US to maintain the strengths and leadership that you've had, and that should be our primary objective. And yes, of course, doors are open for scientists to come. But I second what Bjorn said, that probably the more immediate and perhaps more longer lasting is that you're no longer perceived globally as the leader in science. And that has long lasting repercussions.
Yeah. I wanted to come back to a comment that Susan just made about US observations. And we have been talking all week about the leadership that the US has through NOAA and NASA through our observational programs and observing systems, whether those be satellites, ground-based networks, etc. Ocean-based networks. We've heard some really amazing talks about the Argo program, for instance. So we wanted to hear from all of you about how you use these US observations in your research, and also what the proposed cuts in US funding specifically for those observational programs might mean for the work that's happening in your own groups or at your institutions more broadly. Why don't we start?
Claire,
Yes.
could I just slightly interject before you get onto that question? Because I just did want to add one last point to the last topic, and it was kind of brought to mind by something that Niki said. Here in the UK, we have kind of experienced the downside of cutting ourselves off from our natural research partners when in 2016 we collectively voted to leave the EU. And I don't think even the most ardent Brexiteer would have actually wished what ultimately happened to the UK science, because we then became the pariah of Europe. We became the place that nobody wanted to visit for a visiting science position. In Oxford, I recall very distinctly prior to Brexit, when I had a postdoc position that I needed filling, I'd get the most stellar applications from both from Europe and from the US. And after Brexit, both of these dried up. The top US people didn't want to come to the UK anymore because we weren't partners in Europe, and the Europeans didn't want to come either. And we've had to, although we're still outside the EU, we've had to renegotiate joining the what's called Horizon Europe scientific program, and we're sort of slowly, and I have to say it is slow, recovering from that utter sort of falling off a cliff that happened in 2016. And so I have kind of personal experience of what this kind of can do to your national programs. We all depend critically on collaboration, and we depend critically on an exchange of people and ideas and everything. And these sorts of, I mean, in the case of the UK, it was Brexit, that these things can be quite devastating to one's scientific standing and so on. So I just wanted to make that point because I have some pretty direct.
Yeah, thank you. Thank you for interjecting.
Yeah.
That was a really prescient comment to make. But I do want to get back to this question about observing systems, satellite observations, ground-based networks, ocean-based networks. I don't know, Bjorn, do you want to start us off with a comment?
I was thinking about that, and I think there's so much the U.S. has done in this regard that it's really easy to take for granted. It's sort of it's just a bit like the oxygen you breathe. So there's obvious things like Argo and the series energy budget measurements, the satellite programs, the ground-based networks, the CO2 measurements. But there's less obvious things in the way that they serve as data centers. You know, when I go get the soundings from the world, I go to the University of Wyoming site. Right now, we're in the field last summer revisiting an area that was measured 50 years ago, and I've been comparing that to measurements that were made 50 years ago, and they were archived and documented and curated at institutions in the United States, even though that was an international program. So we go to NCAR to get that data. There's basic tools that we use in development of new tools like UX Array at NCAR. These are just basic infrastructure that is very much rooted in longstanding programs in the United States. And so one of the upsides of the United States seeing itself as a world leader was this feeling of responsibility to also support the world in its scientific endeavors. And I think that's the United States did that very well in the past. And if you look at other programs, no matter how generous they are, they don't have that view towards supporting or laying a foundation for a much broader community to do science. So I think the world is a bit scrambling now because we realize something is going away that maybe we took too much for granted. And I don't think we have a good plan for how to reestablish that. Yeah, that would be my general comment, but maybe to some of the more specific things like the measurement networks and Niki and Sue have a lot to add.
Maybe Sue first.
Okay, so the Max Planck Institute for Biogeochemistry basically cloned a lot of what one of the NOAA labs, the carbon, the global monitoring laboratory. So we really closely interact with the NOAA laboratory and intercalibrate to add to the global monitoring system of CO2, methane isotopes, all the other things that are provided. So I don't personally work with that so much. It's more Cecilia in my, there was another director at our institute. But of course, there's enormous concern because the NOAA group has really been the leader of that global community that tries to use the atmosphere as our ultimate truth for what we're emitting and what's getting consumed. And if we lose that top-down perspective, we know that our bottom-up models will just do wild things because everybody's favorite source or sink will be more powerful than everybody else's. And so we rely on the atmosphere for the truth of what we're doing. And, NOAA is certainly responsible for more than its share. NOAA and NASA, because, we need the satellites now but the ground truth from the satellites is measurements that are done on flasks. And so, the thought of losing such a huge portion of this, long-term network. And it's not just greenhouse gases, it's, water vapor in the upper stratosphere, it's ozone, it's, all the other atmospheric chemistry. And not only that, but the use of that knowledge to understand the basic biogeochemical cycles, like why methane stopped increasing or started increasing again. A lot of that research was also done. So it's not just monitoring that we're losing, it's also the ability to interpret those measurements with inverse models and forecasting things like fire probability, things like that.
Yeah, and if anyone was around, we had a great talk yesterday from Alex Turner about the methane hiatus slowdown. Super interesting stuff. Niki, do you want to add in on this topic?
First, I'd like to second what Bjorn said. I think the wealth of data that the US has contributed to the world is tremendous. But it's really this leadership also in open data policies that have been actually quite influential also here in Europe and has enabled enormous amount of work throughout the world. And just to be concrete, if I look at the most recent papers of mine looking, for example, at the carbon uptake by the ocean, either through repeat hydrography measurements or also surface PCO2 measurements, half of those observations, more than half of those observations come from the US. And it was very clear that the US has taken the leadership in actually collecting the planning for that, collecting the data, making the data available through the data centers that also Bjorn has talked about. Europe has now increased its contribution, but it's not at the level of the US at the moment. And without those observations, I could not have written about a third of my papers in the last 15 years, I would say. I mean, I'm relying tremendously on those types of observations, including also the satellite observation from NASA. So it is what, and I'm very, very grateful and thankful to the US taxpayers here to enable that. And of course, all the scientists that make this happen. But this is what we're about to lose. And of course, what that means is the rest of the world, we have to pick up big time. Maybe in certain places, rightfully so, because we may have been a bit too reliant on somebody else providing the services to us. And I think we also need to contribute our share. But again, it's this leadership perspective, this ability to say, okay, well, we do this to make the world a better place. And that philosophy has been so much deeply grounded in how the science globally is perceived, the global leadership. And that's why we've always accepted the leadership for the US, because it wasn't felt as if you guys want to benefit from us. It was you guys want to lead because we have a common goal. And I think in that spirit is kind of what we're losing right now in the current administration.
Yeah, and that spirit is so important. Tim, go ahead.
I just thought I might pick up on, again, something that Niki said about, the taxpayers picking up the tab for, observations, and us doing it for the sake of society. And I just want to put a slightly different spin on this, because I've always felt that the US system for, say, weather prediction is actually a much better system than we have here in Europe. And what I mean by that is that, the taxpayer funds for the NASA and the NOAA satellites and the modeling that the National Weather Service provides, and the forecasts are all sent out free of charge to the community. Now, what happens as a result of that is that in the US, there is a very vigorous private sector that feeds off this basic output from the Weather Service and provides very tailored forecasts for specific industries and specific users. It could be, aviation or shipping or oil rigs in the Gulf, or whatever it is, out farming. Lots of very vigorous and very successful private sector, whereas in Europe we charge, the weather services charge for the forecast information if it's anything over the sort of very basic. And what this actually does is to stifle the private sector. Private sector says, "Oh God, we've got to pay for all this stuff. We're never going to make a profit." So it turns out not to be as good, in my view, as a model. And I think the US Treasury gets back a lot more from its tax revenues on this very vigorous and successful private sector that the treasuries in Europe don't get. So I've always been, I've had great admiration for whoever set up that model in the US, because it's not just, it comes over as altruistic. We're doing it for the good of society. And of course, that's great, because all of us here around the table, that's what motivates us. We want to be doing stuff that will help society. But actually, it's also good for the treasury, for the tax collection, because it promotes a very, as I say, vigorous and successful private sector. So I would just say this to my US colleagues, don't cut off a really good thing. You've developed something phenomenally good, which this is one area which we haven't been able to replicate as well in Europe, and it would be terrible if you lost that extraordinary commercial advantage, in my view.
And that is a super interesting perspective because, yeah, we've been hearing a lot recently about the idea to privatize the National Weather Service in the U.S. But yeah, you're right. The fact that it is public has allowed for so many private industries to build on top of that. We had a great talk the other night from Adam Sobel talking about his collaborations with the insurance industry, building on top of weather forecasting models for the insurance sector.
It's building on top of it. That's the point.
Exactly.
Yeah.
We had a few questions. I want to move on to some questions from our viewers. They've asked 100 questions by now, so we won't have time for all of them. But there were a few questions that I see that are kind of related that are asking about how science is funded in your countries, and wondering, is it different from how science is funded in the US? So you talked a bit about this just now, Tim, but is science in the UK and in the EU mostly federally funded, or is there also private funding, other types of funding that's coming in, or does it work very similar to the US? How can our viewers think about those differences and any lessons we might learn, or maybe hazardous lessons we might try to avoid, like you just shared with us?
I would jump in because I think one of the things I found fascinating as a U.S. American who lives in Germany is the public funding of science in Germany. In some ways, the German concept of scientific freedom really also means that you have funding to do the science, that you don't just have the ability to go get funding like in the US. So when the public funding for science in Germany happens, what they do is they fund organizations, whether it's the German National Science Foundation or the Max Planck Society, and those organizations determine what the money is used for. So there's more of a decoupling from politics and science. And it's rooted in this idea that a democratic society needs publicly funded science. It's sort of a tenet or a foundation of a critical society, and that the politics shouldn't really decide where to put the money. So in the Max Planck Society, for instance, it's federally funded, state and federally funded, but publicly funded. And the members of the Max Planck Society decide on what topics that's allocated. And the same with the German National Science Foundation. It's publicly funded through a public grant, but the members of the Senate, which are academics who are voted and elected, they decide on how that money is distributed. And so a lot of these models were put in place after the war, I guess, in Germany, and they often had the wisdom of people from the United States who were designing these policies. But it means that the funding for science is much less political, that scientists have more autonomy, and I find it freer in terms of that environment. I'm not a fan of the philanthropic model for science because that's even less free than the political model. Mostly it supports the egos of the people who are doing it. There's some counterexamples. And mostly it gives the impression that philanthropic science doesn't rely on an enormous base of public science. So what people often see is they see the philanthropist who puts the last 10% on something. And they miss the fact that the whole public enterprise of education, of graduate education, of funding, of infrastructure is really a core element of society. And I think that's recognized at least a little bit better here in Germany than it has come to be recognized in the United States. So that would be a bit my perspective on the funding, that it's more public here, and maybe there's more funding in net in the United States because it's a richer country with more resources for science. But it's been moving away from this democratic public model in recent years in ways which I find troubling, not just the last year, but over many years.
Mm-hmm. Yeah, thank you for that perspective.
I don't know, since the question, I just read the question now, it talks about UK science, so I don't know whether I should just chip in very quickly to say that, I mean, we have, research agencies, much like in the US, but I just want to, again, emphasize, and this has certainly been, my own career has benefited immeasurably from this, is that in addition to the, if you like, the National Research Council funding, we have EU funding, and this comes through collaborative grants or things called, an organization called the European Research Council. But what this has, if you go down the European route, you then are necessarily, you have to think about how your research proposal can develop with partners from around Europe. And I think that has made, it's made UK science a lot stronger than before we joined the EU. And as I mentioned just now, the Brexit thing was a catastrophe because it really led to a significant diminution of UK science. I'm always conscious in the US, you have your own agencies, and I don't see, I mean, if I was, if I was brought, not that I will be, but if I was brought over to advise the US government, I'd try to kind of suggest you need more research programs where these agencies work together rather than in collaboration, in competition. So is the word I'm trying, in competition with each other. And again, I just make this point that European funding has really taught us about the benefits of collaboration.
Yeah, thank you. I want to go on and take some more questions from our viewers. We have one from Kelly, who asks, on a very different note, what is something that you would like to say to young scientists and students who might be feeling very destabilized, very uncertain about what's happening in the U.S. science, or maybe in the U.S. broadly? But if you have any words of wisdom or advice for the young people listening to this call.
Come together. No. I don't know. I mean, it's very hard because it's also uncertain right now. I think that's the hardest thing is, not everybody's lost their job yet, but so many are threatened, and that is hard no matter what. I don't think this can continue. I really don't. I hope that Americans will value their science infrastructure and educational infrastructure in general enough to try to stop what's going on. But if not, then if you really want to be a scientist, there will still be science in the U.S. You'll still be able to get educated, but maybe if you want to do the top science, you might go to another continent to do that. That's very hard to say as an American, but I honestly don't think that this is going to be forever. But
yeah, it's very hard to imagine that indeed. And I think as scientists, we always have to be optimistic about things. We want to see the good outcomes, and that takes a risk. And I think, and so I would really encourage you, and I think also young people who have an interest in science, not to lose that interest. I mean, maybe what requires a bit more flexibility in what options you can pursue. But if you have a dream, if you have your idea, follow it. And I think there will be a path. I'm very, very optimistic about that. Might be a little bit more tortuous than originally planned. But if you look back in time, in history, it have been sort of darker times for science. And at the end, those who really wanted to prevailed, and I think that good spirit, should really be a beacon for us.
Yeah, and I think the economic losses will be so huge with a diminished science program for the U.S. The competitiveness, the just the ability to have the payback that comes with being able to predict hurricanes or extreme weather or crop yields in advance. There's just so much that science does that's basic to the operation of economics in general that I don't that's why I don't think it can continue.
Yeah, I think the number that I keep hearing from some economic study that was done is every $1 that gets invested in NOAA in the US gets $70 in return from all of the benefit that NOAA provides with the National Weather Service and other programs on things like forecasting hurricanes. So it really is just a huge benefit to our society to have these robust scientific enterprise happening.
It probably doesn't help people though who are losing their jobs, like you did just a little while ago.
Yeah.
And
Indeed.
I think maybe in a concrete term, there are quite a few international programs that people can apply to and consider it as a, if someone is really out of a job, they can maybe try to find a way to use it to sort of step back and rethink about what they're doing, maybe take a kind of a sabbatical in a place that they wouldn't have thought of before. Maybe think, as scientists, we're all teachers, and there's many opportunities for teaching. So we might have to hold our breath for a while, because despite all the sensibility that everyone just discussed, it doesn't mean that people will behave sensibly in politics. But I also think that maybe in a funny sort of way, we can think about how can we use this as an opportunity, especially if you're young and more mobile and have more choices, to maybe to try something related that you're good at, maybe in a different place, and enrich yourself for the moment when we can breathe again.
Indeed,
I wonder if I could make a slightly tangential point here, but I want to make it at some stage, and I see we're running out of time.
Go ahead, Tim.
I understand there are cuts, in a lot of different disciplines, but I think climate has been targeted, let's say, for cuts above and beyond many other fields. And I suppose that the people who are instigating these cuts feel that climate policy is not, is not top of the current agenda of the administration. I just want to make the point I want to make is, and for example, I've been on the first 5 IPCC assessment reports in one form or another, and I've been to endless climate meetings. And what I'm about to say, I'm pretty sure everyone on the panel here will endorse, which is that although there are clearly a few of our colleagues who do get very kind of politically active over climate change, I would say 99% of the climate scientists I meet and interact with, whether it's in UK, Europe, US, Asia, whatever, around the world, they're doing it just because they feel this is an important problem, and they want to get to the bottom of it better and more, understand more, predict more, whatever that turns out to be. Whether maybe with better understanding, we'll find actually, climate change isn't so much of a big deal. Who knows? There are lots of uncertainties still in climate science. Point I want to make is that almost everybody who works in the field isn't a political or a climate activist. They're just a scientist who are striving to understand this potentially important problem better. So I think, it seems to me, irrespective of what your policy is in your country about net zero, whether you think it's something we should be pursuing with great vigor or just kind of put it right down the priority list compared with other things. Nevertheless, trying to figure out what is happening to our climate system with the various things that we're doing, whether it's catastrophic, a kind of lukewarm insignificance, or a hoax, whatever you want to call it, we should be supporting the science, because it's only the science that's ultimately going to answer these questions. And science is, and even climate science is ultimately, should ultimately be apolitical, non-political. And I feel, if it's a shame we can't sort of convince a lot of our funders that it could be in their, if they don't feel climate's a big deal, it could be in their interest to fund the science. So we better understand, and maybe we'll converge to that point of view. Who knows? We have to be neutral about it. And as I say, almost everybody I work with is neutral. It's just a few, perhaps the prominent few that aren't. So I just want to make that point, which seems to me an important point.
Yeah, thanks for bringing that up, Tim. And I think a lot of our listeners will have gathered, if you've been tuning in for the talk so far this week, that we really are mostly just a bunch of nerds who are really geeking out about some aspect of our Earth. We love studying it. We love understanding it better, making better predictions about what's going to happen in the future, whether that's tomorrow for your weather forecast or in 100 years from now for a climate projection. But at the heart of it, as scientists, we are really just nerding out about understanding this beautiful planet that we live on.
Some people even wear sweaters with their topic matter on them.
Some people even wear sweaters with their topic research. Indeed. The cloud again has been getting a lot of love in the chat. Thank you all. I want to end on that note because you are all such an extraordinary collection of scientists in our field. I want to end with a science question for the panel because there's been a lot of them in the chat, people just asking random questions they have about the Earth system. And I think this one probably goes to you, Bjorn, because they're asking about clouds. So Janek says, I wanted to ask if there's some understanding of how a warming world with extra water vapor would impact the formation of clouds and how that would feed back and impact the climate.
Yeah, I'd like to know that as well. So I was counting on people like you, Claire, to answer that question. It's the big one. It's been the big one for a while, but we're getting close to it. I think there's two things that are happening that are allowing us to get close to it. It's just that the record of observations has accumulated over the past 50 years or so with warming, that we're able to tease out changes in clouds from data in ways that just you couldn't imagine doing 10 or 20 years ago. And on the computing frontier, we do have the capacity now to simulate. Actually, if we wanted to, we could simulate the world at about 100 meters resolution for about a year. And that would allow us to get new insights from the physical equations that we have to solve. The United States would have been a great place to do that because they lead the world in computing and in the development of some of these models, satellites as well. So the shorter answer is we have some ideas. We don't really know. We haven't known for a while, but we're getting close. And this was a bit of a bump in the road on our way to answering that question.
Okay, thank you. So with that, I think we are coming up on the end of our hour, the end of hour 70 of this live stream. Really amazing. I can't believe that we have been going for 70 straight hours, 30 more to go. We are going for 100 hours, just highlighting the amazing, incredible, miraculous research that has happened in the United States in weather and climate science, and all of how that work has been really supported and made possible through federal funding. I want to thank you all so much for being on this panel. Just really amazing to have you all here. Oh, you're back. And just to wrap up the comment from Michaela, we had so much love, so much support for having all of you take the time and spending your time here with us today. It really means a lot, and really appreciated the insights that you could share from how things are similar and different in your countries, and just hearing your journeys about how impactful US science has been in your own lives. So thank you so much, and I hope you guys continue to tune in and hear more of the research. We've got just amazing speakers coming up, and a bunch of early career scientists who are so great to hear from. Thank you again. And with that, I think we're going to move on.
Thank you, Claire.
Bye-bye. Thanks very much.
Thank you.
Good luck.
So thank you all. I think I am handing it off. This is the end of my 2-hour hosting. handing it off to Matt. Hi, Matt.
Hey, Claire.
Good to see you. It's just been so wonderful to spend this morning with all of you here on the live stream. And please continue to tune in. And Matt, take it away.
Yeah, great. Thanks for that really nice panel, Claire, and our panelists. That was great. So, hello, everyone. My name is Matt Luongo. I'm a climate scientist and oceanographer based in Seattle, Washington. And thanks for joining us in now, I think, hour 71 of the Weather and Climate live stream. We have another great hour of climate, ocean, and weather science for you. We'll be speaking with Doctors Jonathan Nash and Carlos Martinez. Before we begin, we want to remind you why we're here on your screens. We know how important weather and climate forecasts are to you and to everyone in this country. Luckily, the US has long been a world leader in weather and climate prediction. We developed the first computerized weather forecast to help you know what you can expect in the coming weeks. And we made the first computer models of the climate impacts of carbon pollution, so you can know what to expect in the decades to come. To make these forecasts work, we've created an unparalleled network of observations using everything from weather stations to satellites, planes, balloons, boats, and floats. The resulting forecasting and observation system is a true scientific miracle, and we're excited to share some of that miracle here with you. This miracle was really only made possible by decades of investment by you, the American public. But in recent weeks, funding cuts have put this miracle at risk. Weather stations are so short-staffed that we're losing our observational coverage, which is already hurting our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for our basic understanding of the weather and climate is disappearing. The administration's proposed budget, being considered now by Congress, is far, far worse. It would cut the NSF and NASA's Earth science budgets in half, completely eliminate NOAA's research arm, which is what I'm funded by, and end foundational programs for young scientists like the NSF Research Experience for undergraduates and graduate research fellowships. But it doesn't have to be this way. If you like what you see here, then we ask you to please use the link on your screen to contact your representatives and tell them to save our forecasts, to keep the lights on for weather and climate science so we can keep this miracle alive. And please spread the word to join this live stream. Last, a brief reminder that all of the speakers here are in their own personal capacities and their views are their own. So we've seen a lot of great talks, and I've been so excited to be joining in and seeing the energy here. And our next speaker is no exception. Our first speaker today will be Professor Jonathan Nash. Professor Nash is an oceanographer interested in turbulence and mixing as they relate to ocean dynamics. Today, he'll be talking about using robotic observations to watch and understand how glaciers melt from below. Please put your questions for Professor Nash in the chat, and we'll get to them in a little bit. Good morning, Jonathan.
Hey, good morning. And it's just great to be here and to hear the panel and all this energy towards the science that, we talk about these, the forecast models, and they all rely on understanding the physics of specific processes and incorporating those into numerical models. And that's one of the things that I'm passionate about, specifically with respect to the glacier ice ocean system. And so that's what I want to talk to you about this morning. I am a professor at Oregon State University, and we build some crazy little boats that can sample places that other things can't sample. And the question is, that I want to ask is like, why do the glaciers care that the ocean is there? And I want to give you a little bit of motivation for that. First of all, this takes a large team, and I'm not going to mention anybody by name except to say we have a great group of people from many different universities, and this is all supported in large part by the National Science Foundation. We we bring students on board, we go into the field, we have a lot of fun to make very basic observations of the physics. And what are we looking at? So why am I inspired, I guess, is a question. And I'm inspired because I love nature. I love understanding the physics of the natural world around us. And, I love to be on the water, and it just, to watch the glaciers melt, I think is something that it touches all of us. And, I've had the experience of going to Alaska and Greenland and watching watching the glaciers, slowly retreat. And the question is, what is causing them? How do we understand those processes? And I'm going to give you a little bit of a sort of a background. Well, here's just a few more pictures. Here's Alaska back in a glacier that we really like going to, and I'll talk more about today, is Zeitlzit, or known as LeConte Glacier. And we send these little robotic boats, so you can maybe see one of them here heading in towards this glacier. Obviously, this glacier is melting, but it's also breaking apart due to warming waters. More examples, we are constantly sending our boats into the danger zone to try to understand what's going on there. Okay, what is going on? So I think we've seen various forms of charts that look like this, whether it has carbon dioxide or global temperatures or whatever. This is a map. This is a plot of surface temperatures. And what we see is the projection of sea temperatures to rise. Why do we care about that? Well, I want to let you sort of provide some insights as to how warming ocean temperatures will lead to the retreat of glaciers and melting of glaciers. In parallel to that warming ocean line, we also see these retreating glacier lines, and those lead to rising sea levels. And the glaciers are here on the blue line. There's a gray line here for the Greenland ice sheet, a brown line for the Antarctic ice sheet, but they all add to be a significant contribution to global sea level rise. Okay, so what is a glacier? We saw a nice talk this morning by Erin Pettit, who talked about glaciers in Antarctica. I'm going to talk about glaciers mostly in the northern hemisphere. This is a beautiful projection by a NASA image showing how the glaciers are flowing from Greenland into the ocean. And the purple colors, the pink colors, those are where the glaciers are moving the fastest. And you will see that they are moving the fastest wherever they reach the ocean, okay? And so what we've also learned is that rising ocean temperatures have led to a speeding up of the glaciers. And so we know there's a connection between ocean water warming and glacier melting, retreating. How does that work? Well, it works because I don't know if you've like taken like a chunk of ice or had some ice cubes or something, you put them out on your countertop and you watch them melt, and they actually take a long time to melt if they're just sitting there. But if you put them inside a cup of water, they melt pretty quickly. And that's because water has a lot of thermal mass, and it has the power to do lots of melting. And in the case of glaciers, that's what it does. Warm ocean waters, and when we say warm waters, they could be just a couple of degrees above zero, but they are warm compared to the ice, and they have the ability to erode the base of glaciers away, causing the glaciers to become unstable, and they break apart, and that's what we're concerned about. And so the flow looks like this. We have waters flowing beneath the glaciers, we have melting along the glacier face, the glaciers on the left, the oceans on the right, and as those glacier waters melt, they rise because glacier melt waters are like fresh, and fresh water rises above salty water because it's lighter, it's buoyant, like you float when you're off in the ocean, swimming away, better than you float when you're in a lake. So those waters rise along along the face of the glacier, and they mix with ocean waters as they go, and so they're constantly sucking water in from below and bringing it up towards the surface, and that's bringing warm waters in to melt the glaciers. And so how does that do that? What are the processes that make that happen? Okay, the challenge is that the state-of-the-art models still lack the physics needed to represent the glacier melt processes, so we want to understand them. We go to a place called LeConte Bay or LeConte Glacier, and we call it Zeitlzit. That's its native name. It's the southernmost marine terminating glacier up in Alaska. It is known as the Thunderbird Glacier, and that's because it thunders. It's very loud, and it is calving all the time. We can't get near that with humans. It's super challenging, and so we send these little robotic boats, and there's a little picture of a boat, and we sit back on a human vessel about a half a mile away. And we have a variety of little boats. I will show you a little bit more about them. First of all, I want to show you how glaciers work, or I don't want to show you how glaciers work. I want to show you just some time lapses. So these are like daily time lapses, and you can see the flow of the glacier. And when Erin was talking about glaciers this morning, what makes a glacier a glacier? A glacier is a snowy mass that is actually flowing. It's moving under the weight of its gravity, and it's heading off to the ocean. And the ocean, in its part, is melting away the glacier. And how does it do that? Well, it does that by lots of currents. This is the swirling. This is a sped up image, but again, another time lapse, and you see all these great swirly motions, and those swirly motions are bringing warm waters from the deep ocean towards the glacier. And what do we find? We find that Alaskan glaciers are melting 100 times faster than we thought. Okay, what do we mean by that? Well, it really isn't that they're melting 100 times faster than we thought, because like we kind of know how fast they're melting, but it's melting 100 times faster, or 10 times faster maybe, than what some of the models that predict the melt process are saying. And we're actually, this is an article from like 2018, and we've learned a lot since then. Okay, how do we learn stuff? Well, we learn stuff because we take models, we take inferences from some system, and we apply them to some other system, and we find out maybe they work well or they don't work well. And in this particular case, we've been predicting glacier melt using a model that was derived under sea ice. Well, why did we do that? Well, it's really challenging to measure melt or anything at these calving glaciers. They're like super dangerous. We can send a rover to Mars, and we can't send a device to bolt itself onto a glacier, except that's what we're doing. So that's what we're doing here. And what's going on? Sea ice, well, when sea ice melts, that's the white stuff on the top. It forms fresh water, and that fresh water is buoyant. It's lighter than the salty water below, and it stays between the salty warm water and the ice, and it sort of acts as an insulating blanket. Okay. Now that's not what's happening on a glacier. So we call this a negative feedback, because the melting water stops more melting. Okay. On a glacier face, so now we have glacier ice on the left and ocean on the right. When those glacier waters melt, they are buoyant, they rise, they are turbulent, so they bring in water from out deep. That warm water, that water is warm, and it can help increase the melt. Okay, so we call this a positive feedback, and we don't like positive feedbacks, because positive feedbacks lead to runaway processes. Okay, you have more melt, you have more melt. Oh, you have more melt. Okay, you have collapsing glaciers, and that's what we're concerned about. Okay, glaciers are tricky. There's ocean currents, there's ice texture, there's crystal structure, bubbles, all sorts of stuff going on. So how do all those things work together? I'm just going to come back to this sort of diagram. This is what we think is happening on the right. We can model the flow of buoyant, bubbling water up, near the face, but can we measure it? Okay. And so what we've been doing is building autonomous vehicles that can go and sample at the glacier face. We take off-the-shelf rubber boats, and we put motors on them, we put control systems in there, we put fancy winches, and we drive them to the face of the glaciers where we can't go. We bring in a lot of undergraduate students and engineers to build systems that can be bolted to a glacier face. And this is our lab on a ship. So we are sitting about 1 kilometer away from the glacier face, and we are building systems that we're going to bolt to the ice. What do those systems look like? Well, this is the latest thing that we've been doing. It's called the submarine melt stake. It has some ice screws. It has a whole bunch of sensors to measure ocean currents, the flow of heat, the ice structure, and whatnot. It's got cameras, lots of gizmos. Okay, this is what it looks like. It's about 4 feet long, 2 feet wide, and has a lot of sensors. Okay, I'm going to show you some data from those sensors. I'm going to show you how we deploy this. What we do is we put it on a remotely operated vehicle. So that melt stake that I just showed you there, we've put it on the back side of just a blue ROV. It's a hobby grade remotely operated vehicle, and it's on the back of that, and it's now attached to it. And then we put that ROV onto our little boat, and then from afar, we drive it to the glacier face. And so here we are driving it to this glacier, and you can see, there's so much sort of stuff in this image, right? There's this beautiful glacier, there's blue ice, there's white ice up above. And then down below, there's these currents. You can see them on the left-hand side, pushing our boat to the right. Those are moving about 1 meter per second. And those are warm ocean waters meeting the glacier and coming up the face as they sort of melt the glacier face. There are also subglacial discharge. There's also rivers flowing beneath the glaciers that are bubbling up there. Okay, what do? We drive our boat right to the face of this glacier, and then we lower that remotely operated vehicle, and you can see it going into the water right now, and then we drop it down to about a half a football field distance beneath that boat. And then what we're going to do is we're going to bolt those sensors to the glacier face. Okay, so as we're doing this, we have a drone. We have a little, an aerial drone that's looking around and making sure everything's safe, because, we don't want anything to happen. Right now, we're in the process of bolting those sensors to the ice. And I will tell you, I am pretty nervous at this time because we have a ton of stuff on this boat. And the last thing we would want would be for something to happen to it, because it's just a lot of stuff. And we are now attached with that cable to the ice face. And then, oh my gosh, there's been a calving event. This one, fortunately, has been a long way away, so it hasn't actually hit us directly. But we are now stuck to the ice. We have to figure out a way to get unbolted from the ice and then to get away from the situation and try this again. So miraculously, we haven't actually lost anything yet. This is what it looks like from the ROV perspective. We are driving towards the ice face. We have these ice screws that we are going to engage to bolt into the ice. And there we are. We're screwing them in place. Let me just fast forward a little bit, maybe, if I can. Oops, no, don't do that. Fast forward a little bit. Here we go. We have now put that device onto, this is the melt stake. We have bolted it on there, and we've released our ROV from that device. And then a little while later, we will tell it, hey, please release, come back to the surface, and we'll pick you up. And so right now it's making measurements. It's got acoustic measurements. It's got temperature measurements. It's got cameras on there. And then if we just wait a few seconds, we're going to say, hey, release from the ice. Here we go. And it will unscrew itself. And you can see it'll drill itself out right now. Give it some time. Give it a little bit of time. There it goes. It's unscrewing. And then it is buoyant too. So it's going to pop to the surface. And then we're going to go collect it. Okay. We've deployed this in a number of locations up in Alaska. And what do we see? Well, the things that we see is we have acoustic sensors that are pinging on the ice. And they're like, hey, how far are you away? How far are you away? How far are you away? And this is just like a little fish finder. That's what this plot is on the right. And you can see there's time on the bottom axis, and there's distance on the y-axis, and you can see as time progresses, the ice is getting further and further away from us. Okay, so from that, we can say, hey, we're melting at this rate. Okay, the upper panels here show the velocities that we're measuring, and we can see it. Sometimes the current is blue, and sometimes the current is red. Sometimes it's really blue, and sometimes it's really red. Okay, so the stronger those currents are, perhaps the more it's melting. And you can actually see this in this plot. You get strong currents at the later part of this record, and you can see the slope of this line. The ice is moving way quicker. Okay, so just if we sort of quantify that a little bit more, there's 3 plots. The first one is velocity, the second is temperature, and then the last one is distance to the ice. And you can see the distance to the ice is increasing at about 2 centimeters an hour, and then it moves to 5 centimeters an hour. And that happens when the ocean waters speed up and they become warmer. Okay, so we're measuring melt, and we're measuring the processes that are driving melt. What are we learning? Okay, we are learning that the melt rates that we observe are all slightly higher than the melt rates that are predicted. Okay, on the x-axis here of this plot, we have the predicted melt. So it's 1, 2, 3 meters per day. Okay, this is melting. The ice is melting 2 to 3 meters a day. Okay, so I didn't tell you this before, but our instrument keeps having to screw itself into the ice to follow the ice as it goes, because it's melting away, and we keep screwing it in autonomously while we're sitting back on the ship drinking coffee. Okay, at the same time, the observed melt is significantly higher than what is predicted. We predict 2 meter per day melt, and we observe 3 meter per day. Okay, sometimes we predict 2 meters of melt per day, and we observe 2 meters. Okay, so what is going on? What is causing all this variability? And that's what we're trying to ask. trying to understand. One of the things that's going on are bubbles and sediments. Okay, sediments are falling down from above, bubbles are rising up. This is real time. This is not sped up. I don't know if you can hear in the background, there's hissing, lots of hissing. That's coming from bubbles bursting out of the ice. We see sediment falling down the ice. There's a lot of really cool complex dynamics that are going on that we didn't really understand until we bolt sensors there. Okay, so that's why we make these measurements, because we want to incorporate these dynamics in the next generation of climate models. Okay, what else do we see? Well, we see these channels in ice. So this is a recently calved chunk of ice that came off the ice of the glacier face, and it's got these beautiful colored channels in it. We can characterize their scale. These are also features that we're just learning more and more about. Okay, to summarize, I put this on there, this slide, because it just kind of is like, this is all the stuff we're trying to do. But what we're learning is that there are, warm bursts of water that enhance the melt. We're learning that there's sediments, that there's other types of waves, and that calving itself can enhance the calving as well. So it's a ton of stuff going on, and we are just sort of at the tip of the iceberg trying to understand all of these processes. Okay, to summarize, this takes a village. It takes a huge team, and I'm not just talking about this particular project. I'm talking about to understand how to predict the weather. We need so many different sources of information, okay? And that's basic physical understanding of processes, okay? And how do we do that? Well, we fund projects that are studying, how trees transpire, the moisture coming off of trees. We're trying to understand like urban heat. We're trying to understand everything. They're all those parts. This is one tiny piece of the puzzle, but it's really important for one particular aspect of the system, which is like sea level rise, how the North Atlantic deep circulation is going to change and things like that. So anyway, it's been really a pleasure to be able to present this work. We have a great group of students and other colleagues, both here and around the world, that help make this possible. And again, the National Science Foundation has been critical. Thanks so much.
Thanks, Jonathan. That was great. It was really awesome. Yeah, and we have a ton of questions in the chat. So we have about 6 minutes to do some of the questions, but really excellent imagery here. So I'll start off with a couple of the science questions. So one of the questions was, how does temperature profile change during submarine melting?
Well, that's a great question. And I think if the question is, how does the temperature profile change? The melt process itself is just very interesting in itself, because it takes a huge amount of energy to melt a small amount of ice. You have to bring in warm water, but then you have to transport the heat into the ice boundary to melt the ice. And in doing so, that ocean water actually becomes very, very cold. And so when you think about how does temperature change during the melt process, you take effectively 100 cubic feet of water, you somehow bring it in contact to 1 cubic foot of ice, and you end up making extremely cold, slightly fresh water that ends up rising towards the surface. And so the answer is actually, during melt, ocean waters become very, very cold.
Oh, great. Very not what you might expect. Okay, another good question. So you mentioned the Thunderbird Glacier, and you've been showing work from LeConte or Zuidema. What are the most important glaciers, as a cryospheric scientist, that are being researched around the world?
So there are we go to Sudden because it's near a town called Petersburg, Alaska, which is very much connected to that system, and it's easy to access and it's easy to understand the processes there. The goal is to transition towards making measurements around Greenland. Greenland is extremely important in the near term. So in the next 10 to 100 years, Greenland, the ice contribution, the glacier melt contribution from Greenland is the dominant contribution to sea level rise. And there are a huge number of glaciers in the Greenland system. I showed you that on one of those first plots about Greenland and how the ice is flowing there. But there's many of them with many names that I can't pronounce.
Yeah, and just from personal experience, I've been to the Ilulissat ice fjord, and it's absolutely insane. So I think that's 10% of Greenland's ice outflow or something like that. So a couple more questions that folks had. How old is that blue ice? Hundreds, thousands of years?
Yeah, so the blue ice here, I think, is sort of on the order of hundreds to 1,000 years, not really more than that in this particular glacier. In places like Antarctica, obviously, it's much older than that. But it's just, we don't even really understand what is causing, all of the structural changes in the ice itself. And so part of this process is, and like I showed you, if I just go back up to, well, you can see all these bandings of blue and white ice here. So this is a chunk of ice. So up was to the right, down was to the left, and you see, very clear dark blue ice in places, and then just above it, you will see a band of brighter, whiter ice, and so that whiter ice has a lot more bubble content than the darker blue stuff. And the character here, I mean, this is a zoom in. There's a ton, and this is 50 meters below the ocean surface, and there are bubbles that are a couple millimeters in diameter, smaller, larger, and whatever, and they're all bursting out of the ice.
Awesome. Okay, quick question, and then we'll end with a little bit of a longer one. You've been talking about warm water, but how cold is that water?
Yeah, so up in Zuidema, it is sort of 4, 5, 6 degrees Celsius. So that's sort of like, 40 degrees Fahrenheit. And then in places like Greenland, it could be just a couple of degrees above zero. So, 37, 38, something like that.
Great. Okay, last question before we move on. What got you into Arctic research?
So, I mean, that's a great question. In high school, I had a science fair project, and I was really always interested in the flow of water. And I thought I wanted to design airplanes. I thought I'd wanted to, be a naval architect or something like that. And then I realized that the same sort of processes, the same sort of dynamics that are important to the design of cars or aerodynamics are also important to the geophysical world, the world around us. And so I started looking at trying to understand heat flow in the oceans around the world. This is just one part of the thing I study. Like I also study why the Gulf of Mexico is so warm, how the heat in the near surface waters affect hurricanes and storms, the same in the Bay of Bengal. I'm interested in how we move heat around the ocean. And the important places, to me, places that I think are really important, it measures heat to drive atmospheric storms. The ocean moves heat to melt glacier systems. And that's how I got excited about it.
Awesome. Great. Well, thanks, Professor Nash. This has been an excellent conversation, excellent visuals for sure. I think people were really excited about that. Appreciate you taking the time this morning.
Well, it's been great to be here. Thanks for being part of it.
Absolutely.
Okay.
So before we move on to our next speaker, let's just briefly recap why we're here. So weather and climate forecasts are critical to everyone in this country. The U.S. is a world leader in weather and climate prediction. As an oceanographer myself, while I'm hosting on the half hours, I'd like to briefly highlight an oceanographic scientific innovation that federal support from the American public has made possible. So first, I'd like to highlight Argo floats, which are often referred to as the crown jewel of ocean observing systems. And you've probably heard Argo floats, if you've been following along, over and over and over again, because that's how crucial this observational system is to the weather and climate community. The Argo observational program is a fleet of robotic instruments that drift with surface currents and gather data throughout the world's oceans. These floats spend much of their lives parked at around 1,000 meters of depth, which is away from pesky near-surface biology, and they drift along with currents. Every 10 days, the floats descend up to 2,000 meters of depth. Then, as they rise, they collect data on temperature, salinity, and pressure, and sometimes biogeochemistry. When it reaches the surface, the float uses GPS and satellite communication to send its data to data centers, where the scientific community then makes it available to the public. And that's part of why you keep hearing about Argo floats over and over again, because this data is available. The Argo program started around 2000, and in the 2 decades since has grown to the point where we collect 400 plus profiles from thousands of floats deployed throughout the global ocean per day. These Argo floats are crucial data points for understanding the upper ocean's role in Earth's climate, from constraining how it has changed over the past few decades to projecting how it may change in the future, and providing realistic measurements of upper ocean heat content, which affect weather and hurricane forecasts. NOAA, the National Oceanographic and Atmospheric Administration, is one of the main funders of US Argo deployments. And the federal support that leads to these sorts of technologies and discoveries is at risk. We ask you to please use the link on your screen to contact your representatives and tell them to save our forecasts, to keep the lights on for weather and climate science and the Argo program, so we can keep this miracle alive. Our next speaker will be Dr. Carlos Martinez. Dr. Martinez is an early career climate scientist studying climate dynamics and variability, and today he'll be talking about the Caribbean Seasonal Rainfall Cycle and the ingredients that shape it.
Awesome. Thanks so much. Can you hear me and can you see the screen?
Yeah, it looks great. Good morning,
Awesome.
Carlos.
Great. Good morning. And looks like we're shifting gears to the tropics with my presentation, which will be focusing on the Caribbean Seasonal Rainfall Cycle and the ingredients that shape it. This research could not have been possible without the funding of the National Science Foundation, as well as data from NASA and NOAA, with the NSF NCAR, the National Center for Atmospheric Research, and my work that I did previously at Columbia University at the Lamont Doherty Earth Observatory and the International Research Institute for Climate and Society. Alrighty, so we'll get started. First, asking ourselves, why focus on this region? Well, for starters, there are Americans that live here. In the US Virgin Islands, for example, these tiny islands over here, there are about 105,000 people that live there. And then in Puerto Rico, which I have extended family in, I was born on the island, and it's one of the reasons why I wanted to focus my research in this area. There's about 3.2 million folks in this island alone, which is larger than the populations of 20 US states, not combined, but individually. So there's a large presence of Americans in this region, and investigating this region can be really valuable for Americans that live here, for their safety, for food security, and other socioeconomic commodities as well. And so our next motivation is, well, why rainfall? Well, as you may know, rainfall is a critical resource for many communities, and especially in the Caribbean region as well. When we think of rainfall, some of the things that we tend to rely rainfall for is food. For example, coffee, like the Blue Mountain coffee in Jamaica, is an important commodity for that island, and it's a major exporter of coffee across the world. Bananas, rice, and other commodities. So farmers really rely heavily on rainfall for those needs. True for livestock as well. And then, of course, if you've ever been to the Caribbean on a cruise or at the beach and you're upset that it rained the entire 7 days, rainfall affects tourism. Tourism accounts for example, in Puerto Rico, about 10% of its gross domestic product, or GDP. And so the reliance on rain is important for understanding, who's coming, when can they come, etc. And finally, energy production and water management. So understanding changes to the seasonality of the rainy season, its intensity, can impact power grids, the energy production that's in that region, hydropower, for example, and also the retainment of water too. And so because it's so highly resourced in this region, this region's very sensitive to any changes with the rainy season. Too little, and you experience, for example, these large ecological droughts that have exacerbated food production and other socioeconomic commodities in the region, which many islands have faced for several years now. For example, in Puerto Rico, just a couple of years ago, they had no water every 24 hours because of a drought during the middle of COVID. Heat waves and also fire risk too with that. And then having too much rainfall. So the experience that my extended family faced when Hurricane Maria hit the island of Puerto Rico. My grandparents had, 180 days with power. My father had to send a generator to my family in Caguas to help them with that. But rainfall events intense rainfall events can cause landslides, mudslides, flash flooding events too. That can also exacerbate food security, tourism, and those resources, those commodities rather, that I mentioned earlier. And so with that high sensitivity and what we see with what could happen with our future climate, this is deeply concerning for this region, which is now very highly susceptible and vulnerable to changes in the rainfall season. From the Intergovernmental Panel on Climate Change, they found in the recent 6th assessment report that this region is expected to have a declining trend in the number of in the monthly totals of rainfall across this region, particularly during the summer months. And that's due to higher evapotranspiration, causing more increased aridity, and thus you get more severe, long-lasting droughts potentially in the islands. But in addition to that, the extremes are expected to be more intense. So tropical cyclones with higher precipitation, severe storms, and droughts, they're expected to be more extreme across the region as well. And so the last motivation here, this is more into the science itself, is that the Caribbean rainfall, it's kind of complicated in terms of what influences it. There are many ingredients that impact its current state and variability. And I'll break this down piece by piece what I mean, because there are small and large scale features in our atmosphere and the ocean that influence it. The first is what's known as the intertropical convergence zone, which is this elongated zonal band of thunderstorms and convergence that moves north to south with different parts of the year. That influences moisture in this region. Then you have this big H, which is the Bermuda High, or the North Atlantic subtropical high. It's a semi-permanent center of high pressure that just kind of meanders around the North Atlantic and provides this clockwise rotation that influences the extent that moisture is then transported onto the Caribbean. And for any tropical systems that move through from West Africa onto the Caribbean region, the steering of that high influences the direction of those tropical cyclones. Then you have some more regional unique features like the Atlantic warm pool. This is a body of warm ocean water that expands and contracts with the seasons, and that can enhance precipitation in this region and enhance tropical systems when they move through the region too. And then some other things, you have a low-level jet, so like a jet stream in the mid-latitudes, there's a jet in the Caribbean Sea, and that can modify the extent that rain is and moisture is converging across this area. And then, of course, those local features that many of you may know, so the easterly waves, this conglomerate of thunder that move across West Africa, they can develop into tropical cyclones. And then you have the cold fronts from the continental US that can move into the Caribbean basin. So as you see, there's a lot of here. So the literature, when I was going back and reading, I found that there was a lot of missing pieces in understanding how these puzzle pieces evolve across this region to inform rainfall. And so that was the basis of my research when I started was, well, what does the rainy season look like in this region? And a sub-question to that is, well, how am I going to find that out? One way we can record rainfall is through data known as, for example, rain gauges. So that's what you see here in this picture. This is one rain gauge, and they're common tool for assessing precipitation at one particular location. This example here, for example, you see how you have a funnel where the precipitation is falling, and then you have this tube here that records the precipitation. And it's been used across many stations for a number of decades for long-term records of precipitation. And the United States has had a robust network of rainfall data collection and storage, not only in the US, but around the world as well. For example, the US National and Atmospheric Administration's Global Historical Climatological Network, or GHCN, they have approximately a collection, a repository of 100,000 observed stations from over 180 countries. 50,000 of them are just in the US alone. And this information it's critical for any type of study like mine, where you need consistent multi-decades of information for, in this case, rainfall, to understand what the rainy season looks like. And as you see in this photo, just showing, for example, with their hourly data, the color bar is showing the record length. In many stations in the United States, these records have been going on for 50 plus years, which is the kind of data that you would need for this type of study. It's publicly available. There's hourly, daily, or monthly data as well. However, as you saw in that graphic, there are many locations around the world that have that kind of robust network of consistent daily or hourly data, for example. And that's true for the Caribbean. And recent studies that have tried to obtain rain gauge data in this region, you can see that there's just rain gauge data for the entire island. And that limited availability is due to how the data is private. Some of the data is missing some months or years. This is because you have a hurricane moving through or some extreme event that can damage that rain gauge data. And even though radar imagery can also be utilized to estimate precipitation, that available data, it's limited in this region. And so this is where satellites come in. Satellites can also estimate precipitation, and it can help fill the gap that we see across the rain gauge network, for example. And this is just an example of the collection of satellite data collecting precipitation estimates. And you see that many of these satellites were funded by NASA, by NOAA, and the Department of Defense. This information is critical, again, for regions like the Caribbean that have that limited data to be able to utilize satellite data to, again, offset that limitation. And so what I did was I took the rain gauge data from NOAA. In addition, I did some international collaboration. That's one of the main key points I want to share here, is that this research would not have been possible without the ability to collaborate with partners, because the island of Puerto Rico, for example, or the US Virgin Islands, as you saw, those ingredients expand well beyond the Puerto Rican region and the Central Caribbean portion. I needed to collaborate with other countries to, again, have a better understanding of the overarching rainfall cycle across the region. And so I partnered with the Caribbean Institute of Meteorology and Hydrology, which is one of the main weather and climate operational services for the entire basin, and utilized their rain gauge data and developed this graphic, which you see here, which is the 40 stations that have daily 40 plus year data that I was able to use and subclassify the stations into subregions, which I will explain why in a second. And then in addition, with the satellite data to help fill those gaps, what you find is the result. Here is an example in the Central Caribbean, which is the green circle here over Puerto Rico and the US Virgin Islands. What you see in the blue is the aggregate of those stations and what the climatological rainy season looks like, so what it looks like in a given year potentially, and then the satellite data from NASA to complement the rain gauge data. And what you see is that there are two peaks. The Caribbean, many portions of the Caribbean have 4 seasonal components. You have the winter dry season, you have then the first rainy season, which is typically the growing season, known as the early rainy season. Then you have a less wet but still wet period known as the midsummer drought during the summer. And then you have what typically is the largest portion of rainfall for a given year is the late rainy season, anytime during the fall. And what I noticed is that when I looked at other regions, I found that there are different characteristics between them. For example, in the Northwest Corridor, which includes portions of southern Florida, their early rainy season is much more prominent. And then in portions of the Eastern Caribbean or the Lesser Antilles, they don't even have an early rainy season at all. They have what looks more like a monsoon type pattern. And so one of my key findings, because of the availability of the data that I was able to have, is that the rainfall cycle in this region is not one and the same across the entire basin. And so why is that? And that's where the ingredients come in. As I shared earlier, these key ingredients move differently and evolve, which I will share step by step how that is happening in our current state. In addition, but how I got there was I utilized, again, I went to NCEP NCAR, or NOAA NCEP. I used data with sea level pressure to look at the subtropical high. I looked at sea surface temperatures. I looked at the low level winds. All of these are publicly available data sets from modeling centers, from NOAA, from NASA, and other entities. And so what you'll see in these schematics is a breakdown of how the rainy season functions. And we'll start off with the winter dry season. And what happens here is that the subtropical high, that big H, it's huge. It's very large and has a dominant presence over the Caribbean region. And it brings a lot of dry air over the Caribbean, in addition to what's called divergence, or moisture being diverged from that area because of the cold fronts that move through, bringing, again, dry air. This is why you have relatively dry conditions. It's a great time to go as a tourist, if you wish, during this time period. And then the wet season starts to begin in some portions of the southern tier of the Caribbean because of the movement of the intertropical convergence zone in SAMS, which is the southern South American monsoon system. Then we have the early rainy season, and we see a lot of changes. So the high contracts, and it initiates this area of convergence, or moisture that is converging, allowing for precipitation to form. It forms over the central portion of the Caribbean, but it doesn't form over the Eastern Caribbean. And that's why the Eastern Caribbean doesn't have an early rainy season. And as this feature moves northwestward, it intensifies, which is why the Northwest Corridor experiences a more prominent early rainy season. In the meantime, the cold fronts don't reach the Caribbean as far south, so they start to retreat, and so you get a weakening of that dry condition, and those intertropical convergence of bands move northward further. Then we go into the midsummer drought, and what you see is that this is why you have that less wet but still wet period, is that the feature with that convergence band, the precipitation from this feature moves away from the return of the dry easterly trade winds across the region as well. And then the ITZZ bands, they continue to move northward, which is why the wet season increases in portions of Central America and the Eastern Corridor. And then finally, you have the late rainy season. And so this is when all of these ingredients come together and it's why you get the most precipitation of the four seasons across many portions of the region, where this band again comes back to the Caribbean basin. You have, instead of the easterlies, you have southeasterlies, which then is transporting moisture into the region. The Atlantic warm pool, which I didn't share, which was the the red shading here, it's at its largest extent. So that's going to enhance convection and moisture across the area as well. And those bands from the intertropical convergence zone are at their northernmost extent. And so this is why this portion of the seasonal rainfall cycle has the most rainfall. Okay, so then the scientific conclusions here. I found that because of the data that I was able to collect, that the rainfall cycle is hinged on three main facilitators of moisture. One is the eastern and the Atlantic portions of the intertropical convergence zone, and then that western half of the subtropical high that induces those southeasterlies and brings that moisture into the Caribbean. Then you have those regional effects, the warm pool, the low-level jet, they modify the extent of moisture by those facilitators. And it's because of the evolution of those pieces, that's why we get an understanding of how different portions of the Caribbean's rainfall cycle is. And so one of my last slides here that I'll share is, I shared those scientific reasons, but one big takeaway that I want to bring here is that without the funding, without that data so critical for a region like the Caribbean, and without the collaboration with the Caribbean Institute for Meteorology and Hydrology, I could not have developed this observational understanding of the rainfall cycle in this region, which again, 3.3 million Americans live in this area. And what value does that have? Well, it has two main values, for example. One is for modeling. Observations are so critical for understanding how well models are doing with those various variables. And so the research that I have done recently was look at the black dotted line, which is the observations, and then the various models, which again come from modeling centers, data that's really critical and important that I was able to utilize to assess how well they're doing, and also look at why are there differences to then improve then prediction, so that farmers, so that water managers, when they're seeing in the coming months, there could be less rainfall or more rainfall, they can plan accordingly and make the proper steps for their livestock, for their crops, for tourism, for energy and water management and production as well. So I'll conclude there to say thank you so much and happy to take any questions at this time.
Awesome. Thanks, Carlos. This was great. And if you have any questions for Carlos, please add them to the chat, but I have a nice little backlog here that I'll start working through. So first, I just want to take host privilege and say thanks for bringing up the importance of international collaboration. That was one of the things that I found kind of maybe most disheartening early on with some of the NOAA restrictions, was having to kind of log your international discussions and collaborations. And as a scientist myself, my science wouldn't be possible without work with my international colleagues.
Yeah, no, I mean, yeah, I was going to say ditto. I feel you.
So I'm going to start with a question from Sydney. Does the Caribbean seasonal rainfall have any relationship with lengthening drought periods in the U.S.? Maybe kind of in a different way, how connected is this moisture that you're talking about with moisture in the continental U.S.?
That's such a great question. I'll go back to, let me see. Lots of animations here. Okay, that's such a great point, and that's a point that I missed. And so I'm really glad you brought that up, Sydney. Thank you for that question. I am not super familiar with the teleconnection specifically, for example, in the Gulf Coast, or as you say here, feet storms from California to the Midwest, kind of the interactions between the tropics and the mid-latitudes. What I will say is that these, as you see, these features across the Atlantic, they expand beyond the Caribbean. And the atmosphere holds no bounds, right? And so these features that move through and affect the Gulf Coast, for example, or the eastern seaboard, are modified or are affected by what happens in the Caribbean. So investigating the Caribbean region, not only because there, for example, are 3.3 million Americans there, but downstream it informs the Gulf Coast. It informs the eastern seaboard. How we're able to investigate, for example, changes to the steering flow of the subtropical high is going to, for example, affect where these tropical systems are going to go. Are they going to go more into the Gulf? Are they going to go more into the eastern U.S. if they form in the MDR, the development region, for example? The warm pool, right, which is about 28.5 degrees centigrade is what you need for that warm pool. The expansion and contraction of that, how does that change over time? Will that affect systems that move into the Gulf and into the east, into the Gulf states, where you see what's called rapid intensification of these tropical systems? They intensify much more rapidly as they enter into the Gulf region. There is an indirect and direct relationship when investigating this region, and then downstream what that does to those portions of the continental U.S. But specifically with the lengthening drought period, that is a question that I don't know specifically, but I would be interested in looking.
Cool. All right, next question. What is the contribution of large hurricanes in the climatology of annual precipitation? I'd be interested to learn the number of daily observations that went into constructing climatology. So maybe the first part, and then second part if you know.
Yeah, super great question. So when I looked at the climatology, what you see in these ingredients, a lot of these are larger scale. And then the easterly waves, tropical systems, that's called like transient flow, right? They move over a given location for, a day or two, and then they leave. And so what I found was for the climatology, the background flow or the mean flow, like these large scale features that are kind of semi-permanent, that's what's influencing the climatology of the rainfall cycle. Not to say that those smaller features are important, because those are the ones that tend to form the extremes that we see, which is really critical in understanding how those are going to change. But one example is there was a recent study in Cuba that looked at the percentage of rainfall in Cuba that comes from hurricanes, and it's only 10%. And it makes kind of sense in terms of the climate, in terms of climatology, and that's because you would need a tropical cyclone to hit that location year after year after year after year to have that kind of signal and have a higher percentage. And then for the second question on the number of days, 40 stations across the region, but that's why I complemented it with the satellite data to help bridge that gap, that spatial gap that a region like the Caribbean experiences, because there just isn't a lot of publicly available data. And the publicly available data that is there comes from actually NOAA's Global Historical Climatological Network, for example, the stations in Puerto Rico, which is, again, then it's really lucrative. It's important that we have that information.
Cool. Next question from Michaela Biasuti. What causes the movement of the subtropical high during the season?
Oh, great question. So there can be, there's several factors at play here. One can be associated with natural variability. For example, there's what's called the North Atlantic Oscillation, which is this mode of sea level pressure between the Bermuda High and the Icelandic Low, typically during the winter time, and how strong or weak that relationship is with sea level pressure and that gradient across the North Atlantic can influence the strength and the movement of the high as well. There are, it's semi-permanent, so the movement is subtle, but the subtleness is actually, it causes a relatively large influence in this region. Any kind of subtlety with the wind flow from easterly to easterly, for example, can impact the amount of moisture that this region experiences. How that movement changes, that's a really interesting question that I don't know if there is a conclusion to what that could look like in the future with our warming planet. So some good questions to think about with future research that I hope to work on.
Okay, last question. How did you get into this research?
Oh, yeah, thank you. I love that. So as I shared, I'm Puerto Rican. I have family on the island. And when I was figuring out my catching the weather bug when I was growing up in Dallas, Texas, I was seeing the impacts that my family was experiencing on the island with different extreme events. I would say that curiosity, how I linked that to research, was because of my RU experiences, my research experiences for undergraduates. I was a National Center for Atmospheric Research SOARS in the SOARS program, which is an REU program at NCAR, the Significant Opportunities in Atmospheric Research and Science. And then I was also a Noah Halling Scholar, which is another under RU type experience. And both of those experiences led me to see, wow, research has impact on people. And I saw how, a published paper, it doesn't have to be just that. It can have real, tangible, and impactful, and relational impact on peoples and communities. And so if it weren't for those experiences, I would not have been able to tie that curiosity with this ability to help my community, people that I love, and yeah, the value of American investments on education too, in weather and climate for the next generation is as critical. as the data, as the funding of research.
Yeah, and this is a theme that I keep seeing over and over again in this live stream, is that folks kind of first got into this via an REU or a summer research experience or something and found out about how this could be a field and a career. So thanks, everyone. Let's give Carlos another round of applause in the chat. Appreciate you coming out today, Carlos. Thank you.
Thanks so much. Take care, everyone.
Okay, so we are officially entering hour 72 of the Weather and Climate live stream. So for those of you who are just joining, my name is Matt Luongo. I'm your host. I'm a climate scientist and oceanographer. Thanks for joining us as we are, I guess, 3 days in. We only have 28 more hours to go. We have another great hour of weather and climate science for you. We'll be speaking with Professor Scott Powell and Marissa Saenger, who's a PhD student in climate science. Before we begin, we want to remind you why we're here on your screens. We know how important weather and climate forecasts are to you and to everyone in this country. Luckily, the United States has long been a world leader in weather and climate prediction. We developed the first computerized weather forecasts to help you know what you can expect in the coming weeks, and we made the first computer models of the climate impacts of carbon pollution, so you can know what to expect in the decades to come. To make these forecasts work, we've created an unparalleled network of observations using everything from weather stations to satellites, planes, balloons, boats, and floats. The resulting forecasting and observation system is a true scientific miracle, and we're excited to share some of that miracle here with you. This miracle was only made possible, though, by decades of investment by you, the American public. In recent weeks, however, funding cuts have put this miracle at risk. Weather stations are so short-staffed that we're losing our observational coverage, which is already hurting our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for our basic understanding of the weather and climate is disappearing. The administration's proposed budget, being considered now by Congress, is far, far worse. It would cut the NSF and NASA's Earth science budgets in half, completely eliminate NOAA's research arm, which is what I'm funded by as a postdoc, and end foundational programs for young scientists like the NSF Research Experience for undergrads and graduate research fellowships. But it doesn't have to be this way. If you like what you see here and you're learning a lot, then we ask you to please use the link on your screen to contact your representatives and tell them to save our forecasts, to keep the lights on for weather and climate science so we can keep this miracle alive. And please spread the word to join this live stream, either on Tumblr or Blue Sky or wherever. Last, a brief reminder that all of our speakers are here in their own personal capacity and their views are their own. So we've seen a lot of great talks over the past few days. I've really been enjoying and learning quite a lot, and our next speaker will be no exception. This is Professor Scott Powell. Professor Powell is a meteorologist based in Monterey, California, interested in tropical meteorology, remote sensing, clouds, and convection. Please put questions for Professor Powell in the chat, and we'll get to them at the end of his conversation and end of his presentation. Morning, Professor Powell.
Good morning. Good morning from the West Coast, or maybe afternoon, I guess, if you're on the East Coast of the U.S. or Europe now, since it's 12 o'clock out east.
Yeah, I'm in Seattle, so morning for us.
Yeah, exactly. So I want to talk to everybody today about the importance of observing and modeling certain types of clouds in the tropics, and in particular cumulonimbus clouds, the type that cause heavy precipitation, lots of big weather impacts. And before I get going, we were just talking a little bit about the previous speaker, his involvement in REU and the Holling Scholarship, and I'll just add myself into that, ring as well. I participated in both, and those were very important foundational experiences for me as well. Not to mention the stipends that come along with them. I went to a private school, University of Miami, for undergraduate, and those were actually very useful for paying tuition, which, allowed me to, have that opportunity and, to get a good education as well. So I just wanted to mention that before I get going. Another one of these folks who my early career experiences were really, influenced by those programs, which are absolutely fantastic. So like I said, we're going to talk about clouds today, and I just want to briefly kind of go through what my group at the Naval Postgraduate School does. So we look a lot at cloud processes and satellite and radar meteorology. And each quadrant's kind of a different project. Do a little bit of work in studying continental convection. I'm going to talk a lot about clouds today. This is a project that's wrapping up with the Department of Energy, looking at some of the processes that are happening, like at the cloud scale, and what controls which ones grow versus which ones don't. Lots of applications to severe weather associated with that. Marine convection, this is like kind of a core of my research program, thinking about connections between the atmosphere and the ocean, processes that are happening really close to the ocean that impact clouds, and then again, like what affects the growth of clouds. And that's sponsored by Department of Energy. It's been sponsored by Office of Naval Research. NOAA's Climate Variability Program is all supporting that research. I've spent a lot of time thinking about large scale dynamics, so kind of like global scale processes in the tropics that are related to clouds. I'll talk about the Madden-Julian oscillation very briefly a little bit later. That's one process. The El Nino Southern Oscillation may be something that people are more familiar with as well. That's sponsored by NOAA as well. I'm not going to have time to talk about deep learning, AI, ML applications today, but my group's been involved with that with some NOAA and NASA satellite data as well. Oops, went backwards, sorry. So before I jump into the science, I just kind of wanted to put my view of, kind of the timeline of all these different types of processes that are occurring in the atmosphere and ocean that we're, been seeing lots of great talks about over the past now 3 days. Which is by itself a pretty amazing feat. I'm going to be spending a bit of time, talking about the stuff over here on the left, stuff that we consider traditionally to be weather, things that happen on timescales of minutes, hours, like clouds, thunderstorms, tornadoes, days to weeks, cold fronts, hurricanes. We've seen lots of talks about processes also that occur on longer timescales, and there's climate change, which is just sort of long-term trends. And all these long-term processes that we bill as climate have important feedbacks onto all of these shorter timescale processes. And in between, we have what I like to think of as a bridge between weather and climate. The limit of predictability for our forecast models is something like maybe a couple of weeks, and beyond that, you're not going to trust your weather forecast at all. But there's these processes, the Madden-Julian oscillation, the El Nino Southern Oscillation, which are these coupled atmosphere-ocean processes that impact weather globally in a way that's kind of predictable. We see this in many publications, but our forecast models don't do a good job at getting that right, getting that long-range predictability right. And I think that a lot of that has to do with cloud processes, and I'll explain why I think that in a few minutes. So I'm going to spend a lot of time kind of talking about stuff on the left-hand side of the plot, and in particular, really drilling down to the basic building block of processes in the atmosphere, these clouds. And it may seem a little crazy. It's like, okay, why are taxpayers, funding this research into an individual little cloud or something like that? And it's important to remember that a single cloud in say India or Indonesia is not going to cause weather to happen in the US, but the aggregate effect of a bunch of these over long time periods in large regions actually has observable impacts that make this type of process important to study. So I'm going to assert that cloud systems in the tropics are impactful for global weather. And then I'm going to jump into looking at a few pieces of research my group's been doing and trying to better understand these individual clouds that make up these impactful cloud systems. So first, I'm going to show, this is not my work, but this is from NASA's Global Precipitation mission. This is satellite-derived precipitation mapped on the world. And I've got Asia, Australia over here on the left. I've got North and South America sort of in the center, Africa, Europe over here on the right. And the bright colors are where there's lots of rainfall. And this is annual average precipitation. And, one thing that jumps out is this bright blob of rainfall out over the maritime continent into this Indo-Pacific region. And this is a part of the globe where there's very warm sea surface temperatures. So there's this almost constant transfer of energy from the ocean to the atmosphere, the source of energy and moisture that can help these clouds develop. You see other features like the intertropical convergence zone of the Pacific and the Atlantic, some rain over the Amazon. You see storm tracks in the mid-latitudes in the northern hemisphere on this as well. And then you see places that are devoid of precipitation. They're often places where I've got cold sea surface temperatures, where we're not going to have that energy moisture transport from the ocean to the atmosphere to support deep convection. And we can also look at this over a season. This is sort of a daily average over 20 years. And we can see how precipitation migrates as a course over the course of a year. And I'll play this one more time. You can see this precipitation in the Indo-Pacific I'm going to highlight. It moves across the equator over the course of the year. Now we're in sort of May, June. Now you see the monsoon really lighting up in South Asia. And what you don't see in this plot is, a single year, the variability from day to day. This is averaged over 20 years. But if you look at a given year and you start thinking about getting down to weather time scales day to day, there's, things that cause pulses of precipitation within this big blob of rainfall over the Indo-Pacific region. And those pulses of precipitation have these downstream impacts which expand out of the tropics and affect us in the mid-latitudes and the subtropics, including in the United States. And earlier I mentioned this, weather to climate bridge time scale, which happens on, scales of weeks to months, which is further than a weather model is good at predicting, but still is something that we feel like we should be able to predict. And the primary mode of variability associated with that timescale is something called the Madden-Julian oscillation. And this is actually something I did my dissertation on. I'd love to go on and on about this, but I only have one slide about MJO today. And this is from NOAA PMEL in Seattle. And there's a lot going on here, but I want to focus your attention first to this Indo-Pacific region. You see this cloud right here. This is kind of representative of the MJO, where we have like a enhanced precipitation, enhanced storminess in this region. And what happens when clouds ascend is that they condense water, and this releases energy to the atmosphere. And then the atmosphere has to create a circulation response to maintain balance, to obey physical equations that govern atmospheric motions. And when you consider this like on a really large scale, lots of clouds that are undergoing this process cause these extratropical, and extratropical means outside of the tropics, types of processes to happen. So for example, convection, moist clouds in this region of the world can develop this kind of what we call a Rossby wave pattern, a pattern of low, high, low pressure systems that happen outside of the tropics, but can be 2, 3, 4 weeks delayed from when the convection happens in the tropics. And so in this example, you see a low pressure system over the West Pacific, and wind in the northern hemisphere around the low blows counterclockwise. So I would have this flow around the bottom of the low, which is this moist onshore flow on the West Coast, which can contribute to atmospheric rivers, which are these kind of streams of really souped up moisture content. And when that hits land and it rises up above topography and along the West Coast, it can just cause tons of rain to fall. You can also get the opposite pattern. I could get high, low, high, and I could get winds going offshore. That gives me enhanced probability of Santa Ana wind events in Southern California, enhanced wildfire conditions. But this has also been linked to severe weather in the U.S., tropical cyclone activity throughout the world, and many other things. So I'm going to argue that getting this MJO in the tropics right is dependent upon getting clouds right. So we need to get clouds right to get all this weather impacts throughout the globe well predicted. So I'm going to jump into some results. And this is some of my work, but is, many people have shown very similar conclusions. This is based on radar data from the tropics. And this plot shows the amount of rain on, going up and down on the plot. So low down on the plot means not a lot of rain. High up on the plot means a lot of rain. If I go to the left, it's a dry atmosphere. And if I go to the right, the atmosphere is very moist. And each dot's basically a different data point. And what this shows is that if the atmosphere is dry, it doesn't rain much. You only get a lot of rain, these dots that are high up on the plot, when there's lots of moisture in the atmosphere. But there's a lot of dots that are clustered down here, where there's lots of moisture in the atmosphere, but there's still not a lot of rain. So that tells us that moisture is a key ingredient for these clouds in the tropics, but it's not the only piece of the story. And I just want to mention that these types of studies are, you can do this type of analysis with radar and satellite, and all of this is only possible due to really decades of investment by multiple agencies, which I've mentioned before and I've listed over here, which have all supported my work at some point or the other. So the basic idea then is that I've got a cloud, and somewhere in that cloud I've got motion that's going up. And when that motion goes up, it causes condensation, that causes heat to be released to the atmosphere, and there's lots of water vapor in that cloud. Outside the cloud, it's drier. And along the edges of the cloud, you get mixing of that dry air into the cloud. If we go back to, high school chemistry or something like that, the main constituents of the atmosphere are diatomic nitrogen and oxygen. And they have molecular weights of 28 and 32 grams per mole. But water vapor has two hydrogen molecules, which are really light. So the water vapor molecule ends up being much lighter than dry air, which has nitrogen and oxygen in it. That means that when I'm mixing this dry air into the cloud, I'm taking heavier air outside of the cloud, more dense air in the cloud, and I'm getting it into this cloudy updraft, making it more dense. And we know that less dense stuff tends to rise. So this is a process that we call entrainment. And as we're bringing this dry air into the cloud, we tend to make the cloud not grow as much. And that process is something that's really actually difficult for models to nail down. Part of that reason is because the models don't, necessarily explicitly represent all these individual cloud elements. And this is just a satellite imagery from Japanese Himawari 9, which is very similar to NOAA's GOES satellites. You can see Australia on the bottom left. I've got some clouds in the tropics here. And I'm just going to highlight your attention in this red box. And I'm going to zoom in. And I'm going to animate this. And there's just a lot of stuff going on here. I see clouds at different layers moving different directions. Some clouds are growing, some clouds are dissipating. This is the real atmosphere that we're looking at. This is what we're trying to model in our numerical weather prediction systems. And when we do that, we're modeling them on a grid that looks like this. We can't explicitly represent every inch of the atmosphere. So what we have to do is break up the atmosphere into little chunks. So I'll just, you can pick any box that you want. I'm just going to highlight this box right here. Maybe this is a few kilometers wide, but inside this box, I've got a cloud, I've got a clear area in the same place, but in the model, this whole data point has the same temperature, has the same humidity, has the same wind, but there's obviously a lot of variability in what's happening in this region. And so the way that we handle this is we run what we call parameterizations, which is kind of just a fancy term for running a model within a model. And those parameterizations in our weather forecast models have some limitations, some baked-in assumptions, and a lot of those come because we have limited observations of these clouds that we're trying to actually represent. But we can model them. And this is not from a weather forecast model. This is from a research model that we use for studying individual cloud processes. So instead of having a grid box be kilometers wide, it's just 100 meters wide. And what I'm showing you here, the white areas are little clouds that are forming in my model. The red areas are where the air is ascending inside the clouds or underneath them. And we can see all these clouds bubbling up. And some of them here are going to eventually grow deep. They're going to go to the top of the troposphere, and you're going to see these amble clouds flatten out. And what we can do with a model that we can't do with observations is we can track which ones grow and which ones don't grow, and we can compare them to learn a little bit more about what kind of cloud processes might be happening in the real atmosphere. And when we do that, we can get a plot that looks like this. On the left, I have something that represents growing clouds, and on the right, ones that don't grow. And if you look at just the top panel, this is vertical velocity. So it's basically how strong is the cloud updraft? How much is it moving up? The Blue colors represent stronger upward motions. You see that there's stronger upward motions in the growers than in the non-growers. The bottom is just how fast the vertical velocity is changing as the cloud updraft descends. So blue means basically you're kind of putting the foot on the gas. If you see blue colors in the bottom left, or in the bottom right, if you see red, the updraft is putting sort of the brakes on. And so we see, this stronger updraft in the grower clouds. The other thing I want to notice is that the contour of the black line is a lot larger on the left than it is on the right. These clouds that grow tend to be bigger from the get-go, low down in the atmosphere, than the clouds that end up not growing. And this is maybe the more difficult plot to understand, but we can also break this down into how fast the cloud grew. So the different colors here, the red colors are clouds that really quickly went from low down to high up. The blue and the black dots represent clouds that took their time. And on the x-axis of both plots is how wide the updraft is in terms of this area. And it doesn't matter how long it took for a cloud to grow. Basically, once the cloud got up to this certain size, like, half a square kilometer or something like that, they took off and grew into deep convection, 5,000, 6,000 meters, even deeper. So what this tells us is there's some sort of critical threshold. If the atmosphere gets above it, your clouds can suddenly kick off. And that's when you start getting, when you aggregate all these clouds together for long periods of time, these downstream global impacts. But the question is, like, what causes these clouds, to get to this size to begin with? And, does this critical size vary as a function of the atmospheric state? And those questions are still, open, I would say. But the basic idea is that a narrow cloud, the dry air outside gets into the updraft and it stymies that updraft. But for the wide cloud, the width of the cloud protects the updraft from the environmental air and allows this deep convection to happen. Just wanted to share with you a video from a field experiment I led in 2022. This was sponsored by the Office of Naval Research, and this is just sped up video from a Twin Otter aircraft that we have at NPS, where we were flying right through cloud base in post-frontal convection. It's not tropical, but the dynamics of this convection in the organization is actually very similar to systems that we see in the tropics as well. And I'm just going to let this video finish right here and just show you a quick result from that. I just realized that the live stream is probably like a couple seconds behind me talking, so I have to slow down a little bit.
It looks pretty good, honestly.
Here are a few plots of vertical velocity in red, temperature in blue. And typically we think of a cloud updraft as being warmer than the surroundings. Warm air rises. Everybody knows that. And the plots here just time on the x-axis is the aircraft's flying through a cloud. And you see these places where you get a spike in vertical motion, upward motion, at the same place where the temperature spikes up. And that makes sense canonically with what we think we understand about updrafts being, positively buoyant. But then we see these cold updrafts as well, places where you get spikes in the vertical motion, but then the temperature goes down. And it turns out that about 20% of the updrafts we observed displayed this behavior. And at first I thought this was something wrong with our observations, but then we went to, model this and we found the same thing. And it turns out that there's a different force in our equations of motion, pressure gradient force in the vertical direction, that actually was really important for about 20% of these updrafts, which tells us maybe we need to take a look at this in the tropics as well, instead of just the mid-latitudes like we did for this project. Just real quick wrapping up here, a shout out to a couple other programs that I haven't really had time to talk about today. One is the ARM program sponsored by the Department of Energy. And the simulation of clouds that I showed earlier was actually made possible by data that was collected at this dot right here in the Indian Ocean. But my work spans data from many of the different dots or pins that you see on this map. This is a fantastic network of observations with many different types of instrumentation that supports a lot of ongoing research. As well as radars and other instruments, which I've actually spent a lot of time analyzing over the years, but didn't really include much in this particular talk. These are sponsored by ONR, ARM, National Science Foundation. Some of them can even go on ships, which is really cool. You see this is a radar mounted on a ship. some of these instruments you see on the bottom right can also go on ships. And just kind of looking toward the future, speaking of ships, one potential field experiment that may happen in coming months is NOAA-led and called TPEX, which would occur in the Pacific region, potentially with multiple ships with instrumentation. What I'm showing over here is the Tau buoy array, which is an array of moored buoys in the Pacific, which is really useful for INSO forecasting. And on the left is just a schematic diagram of many processes that happen in this region that I'm not going to have time to get into, but the idea is that convection over the West Pacific can, cause migrations in where you get the difference between like warm sea surface temperatures on one side of the ocean and cold sea surface temperatures on the other side. So it can sort of affect where convection happens, which is important for, as we said before, the global ramifications of tropical convection. So I'm just going to throw these conclusions up. I just want to, make a point that, the taxpayer bang for the buck here, I feel like is really, things that people in the U.S. care about, right? Agriculture, energy production, military operations, which I can, not really speak to, but, somewhat tangential to working as a DoD employee. These things all start with the weather. And this, climate research as this build has impacts on weather prediction as well. So hopefully I've, given you a little bit of an idea of what that looks like. And just a few minutes, so I'm happy to take any questions. But thank you for having me.
Awesome, Scott. Thanks so much for the really nice presentation. So I think your passion for MJO has kind of shown in the chat a little bit. So could you give maybe like a 30,000 foot overview of what the Maiden-Julian Oscillation is?
So the Madden-Julian, yes, I took a sigh because it's like, wow, this is complicated. But so the Madden-Julian Oscillation is observed as variability in precipitation in the tropics. So if you were like, pick one point in the tropics and you were to measure the precipitation over several months, you'd see it kind of go up and down. But those peaks of precipitation would be spread out by 30 to 90 days. So it's like really long time scales compared to weather. And, a slightly more complicated answer is that it's related to, sort of mathematically described modes in the atmosphere. We call them equatorial waves that we can derive based on like a bunch of complicated equations. Yeah.
Cool. There's a nice question. So I think you were showing some cloud resolving models there. What was the resolution of that? Just that's my own personal question.
That was what we call large eddy simulation.
Okay. Yeah.
So the grid spacing was 100 meters. So that means instead of like a grid cell being 10 kilometers, it means every data point's 100 meters, like a football field, basically.
So there's a question in the chat that's what are the benefits of running models within models, which they've referred to as modelception, which I think we call nested models in the field, over just running a model with a higher definition like these large eddy simulations.
Right. I mean, imagine if you wanted to run a model for the whole world that resolved every single cloud, right? That requires a massive amount of computational power that we just don't have available yet. And so this is the reason that we sort of run into this problem is how do we model the atmosphere using the computational constraints that we have? And so one of the ways that we get around that is, okay, we have to run a coarse model, but then to solve the problem of representing variability within a data point in the model, you have to run something to try to estimate the processes that are happening.
Cool. All right, and host privilege, I'm going to ask this question. How has working for the Navy impacted your perspective on the importance of weather and climate research?
Yeah, so I guess I don't know how many DoD folks are speaking during this, but there's a saying in the meteorology and oceanography community in the Navy that everything starts with the weather, and that goes for planning any sort of, operations, whether it's a short time scale or, longer time scale where you're looking at CLIMO or anything in between where it's like, a few weeks out. So I think of the importance of weather and climate similar to many of my colleagues. I just have the perspective of, looking at things a little bit through the eyes of my students here as well. And seeing how, being able to predict, weather even at mid-range time scales, which borders on climate, is important for operations. It's important for base resilience. And, by that, I mean resilience of military installations. And, we spend a ton of money each year on defense in the US. So to make sure that we're, protecting our investment, it really does start with getting the weather forecast right so that we can make decisions that are well informed. So yeah, all these little topics that we're talking about, cloud processes, it feels like it's kind of more than an arm's length away from the actual operations, but that work that's going on down in the trenches, it really does have an impact for the operational, mindset. It's just, there's a bit of a gap between there. And, part of our job, I think, is to communicate, what's happening in that gap, to highlight the importance of the work that, all of us as individual researchers are doing to, make a big, impact for, military and other applications as well.
Awesome. Yeah, and that's a really important perspective to include here. So thanks for bringing that. So thanks to Scott for joining us this morning. Let's give him a little bit of love in the chat. So we have reached the half hour of our 72nd hour here. Let's just briefly recap why we're here today. For those of you just joining, my name is Matt Luongo. I am a climate scientist and oceanographer based in Seattle. So weather and climate forecasts are critical to everyone in this country. The US is a world leader in weather and climate prediction. As an oceanographer myself, while I'm hosting on the half hours, I'd like to briefly highlight an oceanographic scientific innovation that federal support from the American public has made possible. So in the 1950s, the idea that Earth's continents might move was pretty largely ridiculed. But after World War II, researchers had powerful new tools to map and probe the seafloor. One of these technologies was a small device called a flux gate magnetometer, which was invented because the Navy wanted to use these objects to map very small anomalies in the Earth's magnetic field. For instance, that might be caused by the presence of a metallic submarine. US oceanographers were able to use these flux gate magnetometers, and they refitted them so they could be towed behind research vessels and began to measure magnetic anomalies preserved in seafloor rocks. The maps revealed a really interesting zebra-striped magnetic pattern, alternating polarity of the magnetic field. And scientists hypothesized that this might be due to Earth's magnetic field reversing in time. These zebra stripes were symmetric on either side of long underwater mountain chains known as mid-ocean ridges, and they became a major piece of evidence for seafloor spreading. The idea that Earth's crust pulls apart at these ridges and magma wells up, and as it hardens, the minerals align magnetically with Earth's polarity at the time. This seafloor spreading evidence became one of the most important pieces of evidence for the theory of plate tectonics. And federal support that leads to these sorts of technologies and discoveries is at risk. We ask you to please use the link on your screen to contact your representatives and tell them to save our forecasts. Leave a voicemail over the weekend. And keep the lights on for weather and climate science so we can keep this miracle alive. Our next speaker will be Marissa Saenger. Marissa is a PhD student in climate science at Scripps. We were colleagues there, and she'll be talking about emulating natural temperature variability with a simple model. Marissa, morning.
Hi, Matt. Thanks so much for hosting this, and huge thanks to all the organizers and folks who have already presented. It's been fantastic, and yeah, I'm happy to be a part of this, sharing why this work is so important. So yeah, today I'll talk about some of the work that I've done as a part of my PhD work at Scripps Institution of Oceanography, and that's on emulating natural temperature variability for regional climate impact projections. So what is natural or internal climate variability? A lot of the speakers have been talking about it already. And it's really important to us as day-to-day people experiencing weather. So there are these fluctuations in temperature and precipitation and other weather characteristics due to interactions between the ocean and the atmosphere, or random atmospheric motions. And so just a few examples of modes of climate variability, which many of you are probably familiar with, are El Nino Southern Oscillation, or ENSO, and the North Atlantic Oscillation, or the NAO. And again, these are some of just many patterns of climate variability that change on different time scales. So just for example, these are images from climate.gov, where you can find more information. In the positive phase of the North Atlantic Oscillation, we tend to see warmer temperatures over the eastern United States and slightly cooler temperatures over the western United States. In a negative phase, we see cooler temperatures over the eastern US, slightly warmer over the western US. And oops, sorry, there are other patterns going on in other parts of the world. And then during a wintertime El Nino pattern, we'll see warmer temperatures over the northern US and different precipitation characteristics. So just a few examples of how natural variability can affect our weather. And what we experience on a day-to-day basis where we are is a combination of both the mean climate state and natural variability. So I went ahead and used the NOAA Climate at a Glance tool to look at a temperature time series in my hometown of Buffalo, New York, in the month of December, where for me as a kid, you know, white Christmases were just a standard feature of my life, and now they are quite rare and they're really a treat, but we don't see those anymore. And so you can see from this data collected by NOAA, this overall long-term trend from 1938 to the present day of about 0.6 degrees Fahrenheit of warming per decade. That's in the blue line. And then in the orange line, you see there are all these fluctuations up and down. And so you can think of that as a result of the natural variability, where it's these fluctuations on top of this mean trend, and both are influencing the weather that we feel where we are. And I encourage you to use that tool to check out temperature trends in your own hometown or where you live. It's a very cool tool. And so with climate change, a lot of the economic damages and fatalities that we see are caused by extreme events. And natural variability can compound these effects. We've seen this with El Nino, kind of exacerbating some of the extreme heat or precipitation changes that can be damaging in a lot of places around the world, influencing crop yields and public health and all kinds of important things for people. And so, you know, even though we're already seeing more frequent, intense, and long-lasting heat waves due to the mean warming of the climate from greenhouse gases, these events can also be further exacerbated by variability. So variability is something that we need to understand better to be able to make useful climate change or future climate predictions. And so just as a schematic on the right here, you know, in the bottom panel, we see this long-term warming trend from greenhouse gases, and that's something that is affecting all of our day-to-day weather. And then on top of that, over time, you know, like I showed with the buffalo plot, these little fluctuations that go on top of that mean response and have different patterns in different places and change over different time scales to give us the overall experience of, you know, a warming mean, but fluctuations on top of that mean, again, that has patterns associated with it. And this this little schematic has been made by my colleague at Scripps, Pascal Polonic, who is also supported by funding for climate science. So quantifying the impacts of natural variability requires a lot of simulations with Earth system models. And Earth system models are these incredible tools that a lot of folks on this live stream have already talked about. Many either contribute to the making of them or use them. And I won't go too much into detail because they're incredibly complicated, but Earth system models represent all of the physical processes that happen to transfer heat and moisture between different parts of the Earth system. So the ocean, the atmosphere, ice, and the land surface and vegetation. And this is a schematic, again, from climate.gov, where you can find more information on how climate models work and how we use them. So yeah, I just want to highlight that these are essential for predicting future climate change and societally relevant impacts. And these come from, you know, years and years of work by tons of climate scientists who are supported by federal funding. An example of is the Community Earth System Model, or CESM, which is developed by scientists at the National Center for Atmospheric Research. That tool has been indispensable to my research and the research of pretty much everyone I know in climate science. And that is something that we rely really heavily on to make predictions that support the safety of the American public. So for natural variability, because, you know, some of these fluctuations are predictable in the sense that, you know, a pattern of sea surface temperatures might contribute to a warming pattern over land. Some patterns of natural variability are inherently random. So these like faster fluctuations in movement of the atmosphere. So you need a lot of simulations to sample the full range of possible outcomes from natural variability in these Earth system models, because you can run them a bunch of different times and get sort of the same mean response. And what's usually done is what's called a large ensemble, where you just make slight changes in the initial conditions. So, you know, the temperature of some region of the ocean or atmosphere, you run it a bunch of times with the same external forcing, so something like CO2 emissions, and it'll take on the same trajectory but fluctuate in different ways. And that's how we can see, you know, what is possible given what we know about patterns of natural variability. And again, what we know about patterns of natural variability and how they're represented in climate models is, again, a result of many decades of work by scientists. So my work uses data from these Earth system model simulations to build what's called a statistical emulator that can represent natural variability at a lower computational cost. And so Earth system models are absolutely indispensable, but they are also computationally intensive. So the goal of my work is to reduce how limited we are in the number of future climate scenarios we can evaluate, because it takes a lot of resources to run these simulations. And if we could emulate natural variability in the same way that it's represented in Earth system models, but with less computational cost, then we can look at more scenarios and like understand future impacts for fewer resources. And so the idea is that the emulator output can be added to projections of any mean climate response to create a large ensemble without needing an Earth system model. And so on the top, I'm highlighting that this is what my emulator produces. It produces fluctuations from a mean state. And then a lot of existing climate emulators already represent the mean climate response to greenhouse gas forcing very well. It's been much harder to include natural variability because, as I'll show a little bit, it's quite complicated. But the idea is that you could add, you know, a bunch of versions of this variability to the mean response, and then sample, you know, the range of outcomes that you get to understand what's possible in different places. And this is on monthly timescales. So I call this emulator the internal variability emulator for regional temperature. And I don't want to get too far into the nitty gritty, but here's a schematic of how it works. I use Earth system model output. I use some statistical methods to generate output that is very similar, that can be used for future impact projections. And just to break this down into why funding is important, right? I'm using data from simulations from the National Center for Atmospheric Sciences Research's Earth system model. And then I'm using methods that have been used by many other climate scientists. So I'm drawing on a huge body of existing work. And then I'm trying a lot of new things. I tried and failed many times. It took a lot of effort to come up with a method that actually worked. And I'm ultimately creating a useful tool for future climate projections that reduces the resource cost for representing variability in future scenarios. So again, all of these funding resources are essential for this type of work. And I'm really standing on the shoulders of giants when I do stuff like this. And so just to get a little bit into how the model works, if you're curious, I'm using what's called empirical orthogonal functions, which describe the dominant spatial patterns of variability. So it breaks down, all this data of temperature fluctuations from a mean state into these spatial patterns called modes. And then on the right, associated with each mode is a time series of weights that describes how that pattern fluctuates in time. And all these patterns are independent from each other at each point in time. And when you add up the pattern and its evolution, you get the original time series. So that's what I'm breaking down all this Earth system data into, Earth system model data into, to use to make my emulator. And then I use what's called a vector autoregression model to represent how these EOF patterns evolve in time in a way that captures the characteristics of their evolution that we see in the climate model, but also adds its own kind of random ability to reproduce this evolution on its own. And so, the formula looks like this, which feels a lot like this. Again, I won't get too far into detail. It took a lot of trial and error to find a way to represent the evolution of these patterns that accounts for how past climate variability affects present climate variability. But ultimately, we came up with something that works really well. And users can customize the setup of this emulator to match their specific needs. I'm just showing how I set it up. So I used Lens 2 CESM2 large ensemble historical data. I used 100 EOF modes, which captures about 85% of the variability. And that's just to balance the computational cost with the accuracy of the model. And I'm incorporating how these patterns influence each other within, the past 12 months. So how does the amplitude of one pattern influence the amplitude of another pattern, even 12 months before that other pattern shows up. That's the way you can think about it. And for the global mean temperature variability, I'm testing how well my emulator performs against these Earth system models in terms of the statistical distributions of the temperature anomalies. In the green is the performance from my model, and in the yellow is the Earth system model data. You can see we have a very similarly shaped distribution with similar means and standard deviations. And then for the temporal evolution of the patterns, I'm using the power spectral density, which is essentially a measure of at what time scales do we see the variability? And again, you see a pretty good match between my model and the Earth system model. And then another way of looking at how the evolution of patterns over time works, I'm looking at lag autocorrelations. So how much does the value of a temperature anomaly at one point in time relate to the temperature anomaly at the previous point in time? And the structure of the lag autocorrelations is, again, very similar. So this works very well. We're quite happy with it on the global mean level. And then just to show a little bit about how it performs at the regional level, I'm looking at these same metrics from before, but at every grid cell on a map over land. And you can just think of this as darker colors means a little bit more error in how it performs. Overall, we don't see many dark colors. And so you can see that not only does my emulator capture variability at the global mean level, but it also captures it at the regional level. And that's what we really care about, because climate impacts affect people locally. And just because we see a little bit darker colors in the tropics here, although when you aggregate to the regional level, performance is quite close. Just want to highlight that even in places where it doesn't seem to perform as well, we still are capturing the general shape. We still are capturing the general shape of the statistics and the temporal components of the original data. And we found that if you add more modes to the model, so just for a little bit higher of a computational cost, you can also close gaps like, you can also close these gaps. And so that's something that users can control when they do this. And also just highlighting that in the tropics, we see weaker temperature variability overall. So on the right are these AR6 regions, just dividing areas on the map into regions. And I'm looking at the standard deviations of the temperature anomalies represented by my model and the Earth system model that I'm training it on. And in the places where we see larger relative differences in the statistics we're looking at, we also see that the standard deviations are quite small. So even a very small difference can be a large relative difference. And again, including more EOF modes closes this gap. And then the last thing that's interesting about this is that our vector autoregression model offers us new insights about interactions between modes, or these patterns of variability. So it solves for coefficients that tell us to what degree a given mode is influenced by another mode at a different time lag. So for the leading mode of variability, for example, at a lag of 1 month, it is influenced by the value of, or the strength of, the second leading mode of variability. And this just highlights kind of that we can see exactly what the model is learning from the training data. So you can kind of think of this as explainable AI in the sense that we're training a model to do something, but we know exactly what it's learning from the data we're giving it. And so that just gives us a little bit more confidence in how it works, and it lets us look under the hood. So there's nothing, there's no black box. And it also sheds light on the characteristics of temperature variability in climate models. So that's something that can be useful for future work as we continue to develop our understanding of how not just the mean climate is changing, but how patterns of variability are changing and how they're represented in our models so that we can continue to improve on that. And again, that's, you know, a whole village of work, and that my work is just a tiny part of that. So just in summary, we've kind of made the first user customizable emulator for spatially resolved monthly temperature variability. It captures global mean and regional temperature variability quite well, and it gives us some new insights about patterns of variability. And so this can expand the possibilities for predicting future climate impacts, but a lot more work is needed. And like I said, it's a tiny piece of a larger puzzle. So funding science helps protect American lives. And just a few organizations that provide funding for this type of work are the National Science Foundation, National Center for Atmospheric Research, and NOAA, as many other folks on this live stream have pointed out.
Awesome.
And just to show a few other things I do as a climate science PhD student, if the research was a little bit too in the weeds for you, I also go to local middle schools and I teach ocean and climate science lessons. So here I'm actually showing students the Keeling curve, which is what you've heard about, how we measure CO2 in the atmosphere. I'm also showing them an Argo float to demonstrate how we take the temperature of the ocean. And these are absolutely indispensable tools for monitoring the Earth system. And it is a ton of fun to share this science with local middle schoolers who are very much affected by climate change already and curious about how we can learn more and what we can do. I also help teach undergraduate science courses and mentor other graduate students. And I'll be teaching a course this summer on climate change and society, just as a way to try and serve younger people, empower people with the knowledge that we need to tackle these big challenges. And so it's not just scientific research, but also science education that I think really serves the American public and keeps us ahead of these really big challenges that all of us are facing. So just want to, again, as we've been saying all along, help us continue this work by contacting your representatives. And I've put a link here, but I know that the live stream is also providing a link. So just want to say thank you again to everyone who's put this together. And I hope that this was a helpful way to get a sense of what some climate scientists, PhD students have been working on. Thanks.
Great. Thanks, Marissa. So I think one of the questions that I think is kind of clear is, so you're statistically emulating natural variability. Can you maybe explain like why that's helpful here compared to like an ESM, like maybe in terms of computational power or time or something like that, just to give an idea of how much kind of simpler and kind of portable what you're doing is?
Yeah, definitely. Thanks. So I didn't get to talk about this much, but these Earth system models, like I said, are indispensable tools, and we will continue to need them. But it takes you probably know better than I do, Matt, hundreds of core hours on these huge supercomputers to run even a single simulation. And it's a lot of work to set it up and a lot of energy. So emulating natural temperature variability statistically takes only a few minutes to run a simulation. Granted, I train it on all of the data that we have from Earth system model simulations. But once that's set up, any user, this is an open source project that I intend to publish as a package for folks to use. So anyone can then run this emulator and generate new simulations of natural temperature variability just in minutes, even on a laptop. So that's, the idea is just to make this more accessible and doable for the research community, so as not to require so much computational intensity. Yeah.
Awesome. Yeah, it makes it super helpful. One of the questions was, someone heard you talking about modes and thought they were talking about nodes. So could you just really briefly talk about maybe what a climate mode of variability is?
Yeah, of course. So sorry, I went through it a bit quickly, but when I was saying modes, I was talking about spatial patterns of variability. So here on the left, I take all the data from the Earth system model simulations, and I use empirical orthogonal function decomposition, which breaks down all that variability into independent patterns that fluctuate on different time scales. So this first mode or this first pattern fluctuates kind of just like this. It's described by these coefficients called principal components. And then the second mode of variability changes in a way that looks like this. And then when you add up all of the patterns of variability and how they change over time, you get the full outcome of temperature variability. And so the reason for breaking it down into these patterns is so that you can then reconstruct something that has the same, statistical and temporal characteristics, but is doable separately from running this whole Earth system model. And the more modes you include, the more of the overall variability you'll get. And the reason I put a limit on the number of modes I use is just to, preserve some computational efficiency and speed, and get an outcome that is satisfactory in terms of matching what we're trying to represent, but without just expanding how much computational resource it would take to do that.
Cool. Another question, are places that experience less variability less likely to see climate-related disasters, even with global warming, or do you think it will actually make the heat worse? Probably an open question, but what do you think from
That's a great question. Yeah, so I think it's hard to say whether places with stronger or weaker variability are better off or worse off. What we're seeing is, for example, I showed how in the tropics, the variability over land, at least, is a bit weaker. They don't experience as strong of fluctuations. But in the tropics, we're also seeing some of the most extreme heat that is pushing the limits of human, survivability thresholds. And so what's important is that the mean change in climate due to warming is already putting more and more people at risk. And then these fluctuations can just exacerbate extreme events in different ways and in different places. And so we need a better understanding and way to predict what we might see everywhere due to both the mean response of climate change and the variability on top of that. Yeah.
Awesome. Okay, last question. What got you into this research? And I know you've done some outreach in the past, so maybe if you could briefly touch on that now, going to a PhD student.
Yeah, I think just growing up, I was lucky enough to have some access to nature. I remember there were just some woods near my school that I used to run around in and really love. And so I just always felt connected to nature and felt like it was important to me. And I think just when I first learned about how, all of our ecosystems were under threat due to climate change, I got really worried and just decided to learn more about it. And in my undergrad, I wasn't really sure what I wanted to do, but wanted to study environmental science in some form. And then that I just kind of got closer and closer to climate science because I was interested in how the atmosphere and climate system worked. And then I just couldn't stay away and decided to start a PhD in climate science. And so I think just everything is fascinating to me about how the natural world works and how our lives are shaped by it. And I think that the more knowledge we have, the better we will be able to just address future challenges and live well. Yeah.
Awesome. All right. Thanks, Marissa. Thanks for joining us this morning and showing us some of your cool work.
Thank you so much.
We are officially entering hour 73. So that means my 2-hour slot for hosting is up. I'll be back again tomorrow at 8 a.m. Pacific, 11 a.m. Eastern. But up next, I think we have Stella.
Yeah. Hey, hi, Matt.
Stella, also joining from Seattle, I think.
Yeah, nice to see you.
Yeah, nice to see you too.
We have met in real life, which is kind of fun to see each other on this fun virtual thing. Good morning, everyone. Happy to be here. If I saw you all at 2 a.m., happy to see you again bright and early later in the morning. So as Matt said, welcome to hour 73. We only have, that's 27 more hours to go. So just a truly great lineup of weather and climate science for you all in the next hour. But before we begin, I want to remind you why we're here again. So we know how important weather and climate forecasts are to you and everyone else in this country. And the US has long been a world leader in weather and climate prediction with the first computerized weather forecasts and the first computer models of climate impacts of carbon pollution. And we've created this unparalleled network of observations using everything from weather stations to satellites, planes, balloons, boats, and floats, including Argo floats, right? All of this cool data. And the resulting forecasting and observation systems is like this true scientific miracle. And we're really excited to get to share some of that with you all. And so this miracle has been made possible by decades of investment by you all, the American public, and the taxpayer dollars that go into funding federal science. But in recent weeks, federal cuts have put this at risk. And weather stations are so short-staffed that we have stopped launching weather balloons and are losing observational coverage, which is already hurting our forecasts. And laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for a basic understanding of the weather and climate is disappearing. And the administration's proposed budget, which was released yesterday and is being now considered by Congress, is far, far worse than anything that's happened so far. And it would cut the National Science Foundation and NASA's Earth Science budgets in half and completely eliminate NOAA's research arm and end foundational programs for young scientists like the NSF REU program, if any of you have ever done an REU, and the Graduate Research Fellowship, with a bunch of my friends were on. And it does not have to be this way. If you like what you see here and you value climate and weather science in this country, we ask you to please use the link on your screen to contact your reps and tell them to save our forecasts. So the link across the bottom of the screen that is floating, wclivestream.com/act. And so please keep spreading the word about the live stream as well. Either way, we really hope you learn about something. You learn something about weather and climate science. And please, remember to drop questions in the chat for our next speaker, which will be Abigale Wyatt, who is going to share a very cool presentation on ocean carbon dynamics and modeling. So take it away, Abigale.
Okay. Thank you, Stella. And before I start, I really want to say thank you to everybody who's organized this. It's a really, really cool endeavor. I'm really happy to be a part of it, and I hope it makes a difference. So a little bit about me. I was in the U.S. Navy before I became a oceanographer. And when I left, I really wanted to get into a field where I could still make a difference and feel useful, but help contribute to some of these solutions, climate solutions. So I did a PhD at Princeton, and I was funded there through the NASA Exports program, which you can see a picture of some of the guys I went out to sea with at the bottom there. And I was also funded by the NSF GRFP, which Stella just mentioned as well. Currently, I'm a postdoc at Seaworthy, which is a nonprofit research organization, and working on ocean models. So today I'm going to talk about ocean carbon in particular. And before we talk about the ocean specifically, I just wanted to give you that kind of large scale picture of the global carbon cycle. And so each of these arrows that you're seeing is representing a flux or a movement of carbon from one reservoir to another. And so in particular, you can see over here on the far left, that's our fossil fuel emissions, this big gray arrow. It's the biggest arrow on the figure. And you can see how that's balanced with these other arrows, which show some of the natural changes and some of the anthropogenic changes, like land use changes. And you can see how that all compares both the fluxes to the reservoirs themselves. So the reservoirs are these circles, which show how much carbon is contained in each of these regions. So for the land, you can see it's broken into several different places, whether it's in reserves or in the permafrost or the soil. But the ocean is kind of one big mixed place. And there's really only two ways that we store carbon there. It's either dissolved in organic carbon or it's organic carbon. And you can see that relative to the fluxes, the storage is really huge. And so the ocean represents a really important piece of this global carbon cycle. And that is what I have studied throughout my PhD and now into my postdoc. So in particular today, I'm going to highlight the organic carbon as a way of introducing you into modeling and why modeling is so important for understanding both the global carbon cycle and the ocean carbon cycle in particular. So what is organic carbon in the ocean? A lot of us are familiar with sort of ecosystem production on land. Well, in the ocean, it's very similar. You have nutrients and sunlight combined to produce ecosystem productivity. And so that's like everything from your phytoplankton up to your fish. So your whole food chain exists up in the surface of the ocean where we have sunlight. And we call this region the euphotic zone. In the deeper ocean, you don't have sunlight. And so having organic matter production is much, much more difficult. So we think of the ocean, most of our organic matter is in the surface, and a fraction of that gets recycled by bacteria. So you can see that we call this remineralization, and it breaks it back down into inorganic nutrients. And for the most part, all this organic material in the ocean is really recycled in that surface area. However, a fraction of it does escape. We call this organic matter export. And I'm showing here that the range of estimates on organic matter export are 5 to 15 petagrams of carbon per year. And if you compare that to the size of some of those arrows we saw in the last figure, it's relatively comparable in size. And what this kind of means is that we have these arrows, but that we have a wide range of uncertainty on how big they really are, even on this one very particular piece of the ocean carbon cycle, which is the organic matter export. And the issue is that these are really hard to constrain these numbers because of all the complex biological and physical processes that are involved. So here I'm showing a lot of the biological processes where the bacterial are remineralizing and the phytoplankton are photosynthesizing and fish are metabolizing. But on top of all of that, we have physical dynamics that are moving this carbon around, that are interacting with the atmosphere, where we have CO2 coming in. And it's very difficult to observe all those processes and understand what's happening with them. And so in a simplest sense, back in the 80s, Martin wrote his really infamous paper, where we now have the Martin curve, where we think of it as, again, the organic matter over here on the right largely is in the surface, or if you want to look over on the left, if you're more into like the GIF kind of version, all that productivity from the phytoplankton is really produced up in the surface. And then as you go deeper and deeper in the water column, the amount of organic matter really just drops off and the sinking flux drops off. And so you have a lot of remineralization in the surface. And as you go deeper, there's a little bit less and less. And yes, it's marine snow is one way we refer to it. So this is kind of our simplest model thinking of organic matter export, where really just the depth you are in the water column and the amount of stuff you had at the top when you started determines how much you have as you go deeper. So that's kind of our simplest model. But when we actually observe these fluxes, this movement of marine snow and organic matter of particles, when we observe what we see sinking through the water column, even in a place where we consider it to be a low variability region, which is what I'm showing here. This is data from Ocean Station Papa. So this is at a location in the Gulf of Alaska, where we tend not to think of there being like a high variability in productivity, although it is a productive region. And what we kind of see here is a variety of different observational techniques. Oh, and I see that the text here got a little bit mangled, but each of the different colors represents a different methodology for observing these fluxes at Ocean Station Papa. So the blue is showing thorium-derived fluxes, one of which I was actually there to take those data. So that's the blue triangles. I took those data. But there's some other data at that station, these blue squares and diamonds. This is a proxy that we've used. We've also have more direct methods, which we call floating traps and moored traps. So traps are, you can think of as like literal like buckets that are just catching all the particles as they fall in. It's a little more complicated than that, but that's the general idea. And you can even see that even across these same methods, that there's just a lot of variability. And it's really difficult to understand where that variability is coming from. Is it because we're using different methods to observe? Is it because a bucket, you have to set for a long period of time, and so it has a different time scale that you're looking at? Is it because of other types of biases? Like, for example, the sediment traps, you can have zooplankton that'll come and eat particles that are collected in there. They might get stuck in there, the zooplankton, so they're adding carbon when they die in or on the bucket's filters. So all this variability in our observations. And then I'm also showing a model, which is the green shaded region here, where the model gives us a whole range of variability and a whole range of potential fluxes that, again, differ from our observations. And it's really hard to interpret these results, to contextualize the results, and to understand where the differences are coming from. And the reason for that is that there's just a lot of complex processes. As I hinted at before, this is kind of a little schematic of some of the processes that I think about when I'm thinking about particle fluxes and organic matter in the ocean. So you have the amount of productivity, the amount of photosynthesis, you have the amount of remineralization by bacteria. Then you also have these zooplankton. They're actively eating some of the organic matter or producing organic matter as they poop in the water column. They're creating this. You have all the physical transport terms where you're moving water, you're advecting it, you're diffusing it, you're subducting water masses, you're mixing water masses throughout the year as the sun warms the surface water, or in the winter when it cools off. And then you have all the particle dynamics, including aggregation as particles clump together, or disaggregate as they break apart. And then the particle's size, shape, composition. It's a lot to try and think about at one time, and all these processes as driving the differences that we see in our export estimates. And so this is kind of just common across the field of oceanography, is that observations of the ocean are limited, they are difficult to understand, and that's partly because of the nature of the ocean itself and the way that we observe it. So I think there's kind of two main camps of observations, the first being remote. So satellites up in the sky, they can see kind of the whole ocean, which is really nice. They get this great scale. The ocean is very, very big, and it's very hard to get measures of the whole thing, but remote observations from satellites help us do that. However, some of the limitations there are that, you're only able to see the surface or some kind of integrated level at the surface. All those observations can be impacted by visibility and clouds, or, you can't see further in depth because of surface conditions of the water. And of course, there's only certain variables that we can see from space. Ocean color is a great example. That's what I'm showing here. So on the left is an image from NASA, from one of their satellites, where you can see the color of the ocean is impacted because chlorophyll from the phytoplankton, and they're swirling around in the surface, and so we can see that from space. But we can also see things like sea surface height and other kind of observable features from space. The other type of sampling we can do in the ocean is what we call in situ sampling, and that's usually done by ships, floats, or buoys. And basically, it really means going out, sitting in the ocean, and collecting measurements They tend to be discrete samples. You cannot really separate what is spatial changes from temporal changes because you're only getting one sample at a time. And again, we often use proxies for this. You can't always measure the variable that you want directly. So you might measure something else that's related. So an example of that is what I'm showing here with the chlorophyll and the nitrate. NO3 is nitrate. As I said, most productivity happens in the surface. So we have high chlorophyll. And then as you go deeper, it decreases. But you could, if you were unable to measure chlorophyll in situ, you could measure nitrate. And so this is showing that nitrate kind of has an inverse relationship with chlorophyll, where at the surface, the plants and stuff there are consuming all the nitrate, so it's very low at the surface. And then as you get deeper, the nitrate increases again. So that's what a proxy is. And when we're talking in situ sampling, that's often the types of data that we're working with. And basically that all was a long spiel to explain why I'm a modeler. Numerical ocean modeling creates an entire ocean, an entire world, or in the case of like Earth system models, which were mentioned previously in the last talk, you know, the entire atmosphere, ocean, land system. These models are, you know, twins, digital twins, little artificial planets where we can simulate everything that is happening to the best of our ability and explore what that looks like. And so in the last slide, I showed you a still image of what chlorophyll looks like on the surface and what a single profile of nitrate and chlorophyll might look like from an in situ measurement. But this is showing what a model result might look like, where we can see the chlorophyll changing in time. So on this top panel, you can see this bright patch of green. It will start again here. It will start in the top corner, and then it blooms as we're going into spring is what's happening here. That spring bloom propagates across the box, and you can see all this phytoplankton really growing in response to the changing seasonal conditions. And as that's happening, we can look in depth. So at the same time, with three-dimensional resolution, we can see that the nitrate is decreasing, or it's going from that blue color to a brown color. So we can see the connection between nitrate and chlorophyll. Visually, we get this really great context for it. And then if you want to dig into, you know, the equations and do some analysis, you have all that data available to you. So that gives us a really, like, models are very powerful in that sense. They give us so much context and really this four-dimensional image of what's happening. But what are they? I mean, really, they're just systems of equations. So all these equations here on the left, all these relationships in the biology and stuff here, what we do is we calculate them in every single grid point. And the size of our grid point really determines a lot of what we can or cannot represent. So for physical models, we are able to represent things like thermodynamics, fluid dynamics, or the way things move, tracer transport, so like where things go. Biogeochemical models will include our ecosystem interactions, so predator-prey relationships, the amount of photosynthesis, the way nutrients encourage or limit productivity, and then organic matter decomposition, remineralization. So these are all, every single thing that we're putting in these models, you can think of as its own equation that's based on observations and the best science that we have. Now, all that is again to say that, you know, these are models. They are created worlds based on the equations that we put into them. And the spatial and temporal resolution is a choice that we make when we set them up. And the complexity of the models can be limited by the amount of time we can run them, by the computational power that we have. And so these aren't the real world, but they are a very powerful tool. And so I'm going to give you an example of some of my work that used models to examine heat waves in the Northeast Pacific. So back in 2014, 15, 16, there was a warm blob, a marine heat wave that occurred here in the Gulf of Alaska region, where the low pressure system that exists in the atmosphere was smaller than average, and this weakened surface winds and a decreased southward transport of nutrients. And there was just really widespread changes throughout the Pacific Ocean caused by this heat wave, including low chlorophyll, low productivity in general, strandings of various fish species, and geographical redistributions of some species, harmful algal blooms, and more. So this is a really big event. And past work had delved into it. And one study in particular looked at Argo floats. And so this is Ocean Station Papa, which is what I had shown data from before. That's the black star here. and we're in the Gulf of Alaska. And then each of these colored lines is an Argo float trajectory. And what this one study did is that they assumed that all the nitrate, so again, nitrate's related to chlorophyll or phytoplankton productivity, that whenever you remove nitrate, so you have an amount in winter where it's maximum, you take some away, that the amount you've taken away is proportional to the amount of productivity. And so we can learn how productive the region is by doing this equation and applying this ratio. And if we look at it over time, if we have a time series of data, as we do from these Argo floats, where we have this continuous nitrate data, we can see a seasonal cycle of productivity. So it increases in the spring, it decreases in the winter, and then each year we kind of have this seasonal cycle. And we can look at this. And what they saw was that during the second year of the warm blob, 2015 to 2016, there was this really big decrease in this metric, net community production. And so they attributed this change to the warm blob. And they said that because this heat was persistent, the phytoplankton in the ecosystem were struggling to adapt. And after 2 years of a persistent heat wave, it basically collapsed. It turns out that you can reproduce this signal even if you sample a climatological world ocean atlas. So that's what I'm showing here. This black dotted line is using the same positions, locations, and timing of the floats, but sampling a climatological field, so one that does not change from year to year, the World Ocean Atlas. So it does not have a heat wave happening. You can get the same change in the year 2015. And what that really means is that this decrease that we see in 2015 is not because of the event that was happening, the timing of the heat wave, but is instead related to the location of the floats that we're sampling at that period. So what I've shown over here is that in 2015, there was one float active, the brown float, and it just happened to move in the wrong direction across the nitrate gradient. And so it looked like nitrate was increasing, because we're going from a low nitrate region to a high nitrate region. And so it looked like the ecosystem collapsed. In reality, this was just a spatial artifact of the data, but it was difficult to see that this was a spatial bias because of the way we were looking at the data. So using a model, I was able to see this really right away, and we could actually separate out the spatial change from the temporal change. So we could see that this was not just due to the trajectory, but 30% of it also was related to the heat wave. So this is just to show that the model can really, again, provide that context. It gives us another way of looking at and connecting the data to multiple variables at one time. And it really gives us this four-dimensional sort of view. So that led to some questions about, what does happen during marine heat waves? Is there a decrease in export production and primary production? The answer is yes, but it's nuanced. And then what's driving the changes? And it turns out it has to do with shallow depths and nutrients. And basically, I use the model to answer those questions. And if you're interested in more details, you can go check out my paper there. But I hope that this proves to you some of the value of using a model to give us that extra context. And so I just wanted to briefly touch on my latest work, which is using models to inform carbon dioxide removal. So carbon dioxide removal is a proposed method for mitigating climate change by removing carbon dioxide from the atmosphere, removing additional carbon dioxide from the atmosphere, and storing it away for long periods of times. So we already know from that first figure I showed you when we opened that the ocean does this naturally. And the idea now is that there are maybe ways that we can encourage natural cycles to be enhanced and do it more effectively, more efficiently, so that it can keep up with some of the changes we've already made to our planet. One of those this is showing up several of the approaches that you could use. There's ocean alkalinity enhancement. These are all marine-based CDR approaches. Direct ocean capture, iron fertilization or nutrient fertilization, algal cultivation, artificial downwelling, upwelling. There's several proposed ideas for how we might do this. It's all very in introductory stages. And my approach really is to use models to kind of explore some of these possibilities. Because again, a model gives us this kind of fake world where we can experiment in. And so I'm going to look at ocean alkalinity enhancement. This is a schematic just showing what that might look like. So this is all kind of hypothetical and proposed, where you can remove the acid from the ocean, leave a more alkaline area, and that will encourage more carbon dioxide to dissolve into the surface ocean. Basically, my place in this field is to do experiments inside the model so that we don't have to do the experiments in our real ocean. So the model gives us a space where we can test, we can set up, we can choose experiment designs and spatial coverage. We can choose the amount of alkalinity that's added. And then we can look at the experiment results and see like how much CO2 was taken up by the ocean. And this is a very difficult thing to do in the real ocean in situ because the ocean is big. And as I'll show in the next slide, that alkalinity moves. So here I'm showing a patch of alkalinity added off the tip of the Olympic Peninsula. In the middle panel, you can see what that change in alkalinity looks like. And you can see where that plume is going. So this model is representing all the physics, all the biogeochemistry, and it is reacting. And what we can see is where it goes, what areas might be affected if we release alkalinity in this area, how high are the changes. And then on the far right panel is where is the CO2 removed from. So we can see that largely the CO2 change from the atmosphere where it's being pushed into the ocean a bit more is really correlated tightly with where we're changing the alkalinity. And it's just really nice that we can see this very clearly, again, using a model. So this is just a hypothetical situation and just an example of what the model could do. And it'll be where most of my future work is directed, is trying to understand how different impacts or what the different impacts might be. So with that, I will just wrap up with this picture of Tsuki Manabe. I was at Princeton when he won the Nobel. He was one of the first modelers in the world. He developed some of our earliest climate models. It was a really big deal that he won the Nobel. And I think it says a lot about US institutions that he came here from Japan to work on these models. And that, you know, we really, this country has been a nexus for climate science for a very long time. We have a very rich history. We kind of started the history since he was the first Nobel laureate in climate science. And he was just down the road from me in Princeton. So I just wanted to finish with that. I'm over there on the left. A lot of great people here. Would also like to acknowledge that all these models are run across many different government systems, including NSF, NASA, NOAA, and even DOE is where I'm working right now. So with that, I'll take questions.
Thank you so much. That was a fantastic talk. Yeah, absolutely. This was super cool stuff. Thank you so much. Really, really appreciate you taking the time to talk to us today. Yeah, and cool picture, really cool picture. Yeah. All right. Well, thank you so much. I am going to go ahead and do a little reintroduction of where we are in our live stream. So we are at hour 73. Welcome to hour 73. If you're just tuning in, 27 hours to go. We have more great weather and climate science coming up for you all. But before I do that, I do just want to do a little reminder of why we're here. So first of all, everyone's speaking in their personal capacity, and their views may or may not represent those of other speakers. And then getting into it, we know that how important weather and climate forecasts are to you and everyone in this country. And very luckily, the US has been a world leader in weather and climate prediction for a very long time. As Abigale just showed, we developed some of the first climate models in the world and also some of the first computerized weather forecasts to help you guys know, to help the public know what they can expect in coming weeks and in coming decades. And to make these forecasts work, we have this really cool network of observations, as we've shown everything from weather stations to satellites, planes, balloons, boats, and Argo floats. And the resulting system we have is this huge scientific miracle, and we've been really excited and thrilled to share it with you guys for the last 73 hours. With that said, the miracle was made possible by decades of scientific investment and federal funding into science from taxpayer dollars in the American public. But in recent weeks, these funding cuts have put this at risk, and we have weather stations that cannot launch weather balloons anymore and are so short-staffed that we're losing our observational coverage, which is hurting our forecasts. And our labs that are dedicated to understanding future climate are being closed or shrunk, and funding for our basic understanding of the weather and climate is disappearing. And in addition to that, we have this new proposed budget from this new administration's proposed budget to Congress that's being considered, and it is far, far worse. And it would cut NSF and the NASA Earth science budget completely in half, and it would eliminate NOAA's research arm, which includes the federal laboratories like the one that Manabe worked at. It would end foundational programs for young scientists like the NSF REU program, which helps undergrads get into science, and the graduate research fellowships, which helps fund people through graduate school. And as a reminder, helping people early in their education is a really great way to ensure that we continue to have a robust scientific enterprise in this country that continues to support the public and continues to provide you all with useful information. And so it doesn't have to be this way. If you like what you've been seeing here, we ask that you please use the link that's scrolling across the bottom of the screen, wclivestream.com/act, to contact your representatives and tell them to save our forecast. If you haven't called yet today, now's the time to do so. Please help us keep the lights on for weather and climate science, and please spread the word about the live stream. Thank you so much. And without further ado, I will introduce our next speaker. Our next speaker is Jared Rennie, who is a research meteorologist and a private citizen, and he will be presenting a presentation called Show Me the Data. Take it away, Jared.
Well, thank you for having me today, Stella. We've been having a lot of great talks so far in this live stream about the science. But one of the, the first steps in the scientific methodology is to collect the data. So this talk is going to be a little bit different. We're going to talk about the data that goes into the science. This is the part where I have to be careful because I do work for NOAA, and I have to be very careful about what I say or don't say on these talks because, as a federal employee, gonna have to, hang on one second here. A little feedback here. Hang on. Hold on 1 second. Oh, I'm getting a call. NOAA Communications. Oh, that can't be good. Okay, hold on a second, y'all. Give me 1 second. I gotta take this call. Hello? Hi. Yeah, I'm on the live stream right now. Wait, wait, I can't do this talk? So I can't say anything bad about NOAA as a, oh, okay. Well, what if I'm a private citizen? Does that work? It does? Okay. I won't talk about that. Yeah, no, they don't want to hear that. Okay, all right. Okay, all right, gotta go, bye, all right. So change of plans. I am not a NOAA employee. I am a private citizen. Look right here, very carefully, private citizen. I am a private citizen here talking about data that is used in federal science, but I am not a federal employee today. Have to be very explicit about that. Okay, so the name of this talk is Show Me the Data. Yes, there will be audience participation, so bear with me. So hopefully we can do that later on. But let's talk a little bit about data. So I live in Asheville, North Carolina. I guess the job I work at, that I can't talk about it, but it just happens to be in this building. If you are in Asheville, North Carolina and see this building, it happens to host something called the National Centers for Environmental Information. So they, again, not we or I, they are part of NOAA, and they essentially do three things. They archive environmental data, they make pretty graphics, and they tell you the Earth's climate is bad. Very bad. Okay, I forgot that there might be kids on here. Okay, so no swearing. Okay, yeah. So they tell you the Earth's climate is bad, very bad. We'll get into that a little bit. So they are one of the world's archivers of all things weather and climate. So this is a weather and climate stream. So Stella talked about at the top of the hour about all the different data sets and the data that we all use. So we're talking about weather stations, satellite data, radar data, reanalysis data, model data. That is all pretty much archived in the building in Asheville, North Carolina. As a meteorologist, I have to remind myself that there's an O in NOAA, so that's the oceanic part. So we have a lot of ocean data as well, including the World Ocean Database, tsunami data, digital elevation models. And then there's also geophysical data. So if you ever done stuff in space weather or with the World Magnetic Model, we have that. And well, not we, again, I'm a private citizen today, but they have all that data. People ask how much data do they have? The number always fluctuates, but it's usually, right now it's about 80 petabytes, which is a lot of data. I mean, that's like, 150,000 laptops worth of data. That's a lot of data to process. And going down the road over the next few years, there's going to be more data because more satellites get launched with higher resolution capabilities. More model data comes out, more scientific data comes out, drone data, more ocean data, more space data. So it gets archived by NOAA and CEI. And they're not the only one. So if you ever done work with NASA, they have their DACS, also known as the Distributed Active Archive Center. They have data as well. But no, this NCEI kind of does the sort of the NOAA piece of the data. So, but that's not even the cool part about that building. If you're lucky enough to go see the basement, I kid you not, it looks like the last scene in Raiders of the Lost Ark, which is here. I'm not kidding. It actually looks like it. Here's a person here. His name is, wait, no, he's a Fed. I can't show him. Okay, so this random person just happens to oversee this floor of the building, and they hold all the paper records that is archived by NCEI. So that includes not just records for the US, but then it includes international records. So countries that don't have archival capabilities will send data to NCEI to be stored. And we have historical data in there as well. So for example, we have, records from American Revolutionary Days, Civil War days, some of the first observations on the South Pole. That's in this room. So if you ever get a chance as a private citizen to go see it, it's a really cool experience. I guarantee you that. And here's just an example. Here's a paper record that did get scanned and eventually digitized. This is monthly data for Asheville, North Carolina in 1890. There's one thing I should mention here is that in order for NCEI to archive this data well, there needs to be good handwriting. And there is some very good handwriting in the 1800s. That's all I'll say. But it's not just the data that NCEI does. They also do climate monitoring. So you may hear every month that, a certain month or a certain year is the warmest year on record or the wettest year on record. NASA does this as well. Our friends at NASA GISS, they do this as well. And every month they produce these reports, and they talk about other things like a tornado report, a drought report, a flood report. And then usually around the time the report goes out, they do a media briefing where they explain to the again. Okay, all right. I'll make this quick, and I promise I won't pick up the phone again. Hello? You don't do the media briefings anymore. Okay. All right. I'll mention that. All right. Gotta go. Bye. Okay. Yep. They don't do the media briefings anymore. But all the information is out there, and you can go to the website, publicly available and such. All right. Let me put my phone away so I don't get any more calls. So they also do billion-dollar disasters. So when a disaster hits, when they look at the insurance data and we don't do billion-dollar disasters anymore. Oh. Okay. All right. Okay. Never mind. Forget what I said. Billion-dollar disasters. They don't do it. The website's still there. There's a banner on the top. But moving forward, they don't do it. Okay. Let's move past that. Okay. All right. So keeping on the climate thing. So there are scientists in that building, really smart scientists that work with folks at the American Meteorological Society, the International Panel on Climate Change, and then also the National Climate Assessment folks to produce national climate assessment reports every few years. You didn't hear about us, Gerb? Did you? USGCRP. That's the we have to do our acronyms. It's the United States Global Change Research Program. Yeah. What about them? No. You're telling me they got defunded too, and that there's no more national climate assessment? Okay. All right. Let's move on. Let's stop talking about climate for a second. Let's talk about the data. Okay, so we still do the data. We still steward the data at least, and it's still there. So, all right. So here's my motivation for this talk is we have petabytes of data, and a lot of scientists on this live stream have probably gotten data from our website or their website, and they have probably gotten very frustrated at how hard it is to get the data. NCEI is working their way to making data more easily accessible to the public. But that's just the first step of the problem. What you're seeing here is not just gobbledygook. It's weather data for Asheville Airport I believe this is 2023. So I know what this is because I see this every day. But to the public, when they get this data, they may look at this and go, am I in the matrix? Like all I have to do is put some green text here and you're probably in the matrix. But so my motivation is to turn this data into something that's actionable, something visually appealing. So while my job is sort of a meteorologist by trade, a climatologist, I'm also a data scientist. 99% of my job is actually computer programming. And I think a lot of scientists on this live stream are also computer programmers to make all the cool graphics that you've seen during this 100-hour live stream. The other thing, and this is not just NOAA, NASA as well, they have repositories and different ways of getting data. But if you go to the NCI website and you're just trying to find, I just want weather station, I just want data for Asheville Airport, I may not necessarily know where I need to go here. By the way, it's surface weather observations, but not everybody may know that. They might end up at a climate data record or, some other place, climate monitoring. So it could be a little hard to navigate through the data. So my motivation is to get folks the data they need as quickly as they can so they can do the cool science stuff. So like I said, I'm a computer programmer, essentially. So what I've been trying to do is find ways to use the data that's in our building and in the cloud and get it to the folks to visualize it. But not just visualize it, but also tell a story, right? We're telling a story. We're telling a weather story. We're telling a climate story. And then what's important is that depending on who we're talking to, we have to make it local. A colleague of mine once said that nobody in Iowa cares about sea level rise. Okay, fine, but they might care about agriculture or they might care about energy. And you have to kind of make that relatable to them. And that's what we're trying to do at NCI, is trying to provide that story to the person. So what I've done is I do a lot of stuff in the Python programming language. A lot of the code, not all of it, but a lot of the code is made available to the public. It's in Python 3 for you computer programmers. It is hosted on the GitHub page. I got a link at the end of the talk here. And in some cases, there are easy Jupyter notebooks where you can kind of go and plug and play. And I'll show you some examples near the end. And it's also, for those that are really big on big data and cloud technologies, you can containerize it with like a Docker container and use it in AWS. And then the big thing is to make that visual story is not just static images can we produce in Python, but we can make applications that are sort of interactive in, like, let's say an ArcGIS environment. So I'll show a couple of examples of that. All right, it is audience participation time. Are you all ready? I know we're virtual, but I want to hear all of you, okay? I promise. I have all 700, 800 folks on my speaker here. So I'm going to go like this, and we're going to say, show me the data, okay? So let's do a quick test, okay? Just a quick test. Okay, ready? 3, 2, 1. Show me the data! Okay, all right, we're close. That's data, but not the right data. Okay, all right, one more time, a little bit louder, a little more emphasis. I know it's Saturday, not everybody's working, so let's put a little more enthusiasm into it, okay? Ready? Show me the data! All right, what did we get? So we have, so we have an animation, and it's snowfall accumulation. Okay, cool, that's pretty cool. But why is it snowing in the southeast? Okay, so this is what if it was, so this is a graphic I made that talks about if all rainfall in the US was snowfall. What if it was all snow? It's a great weather question we love asking. So yeah, okay, so it wasn't exactly what I was looking for, but I think we're on the right track to actually showing you the data to get you the story that you need. All right, so let's do it. So the future graphs that you'll see are all made in Python, all in some sort of Jupyter notebook. And at the end of this talk, you can go play with the data yourself. So, all right, so let's talk about, here's a real example. Okay, annual temperature graph. So if you ever see those New York Times style graphs that show temperature over the year with, climate data, weather data, we can do that. And actually that matrix code you saw earlier was the original data. So we can turn that matrix code into something better, okay? Ready? Here we go. Show me the data. Okay, great. All right, so now we've got, again, matrix code converted to this. So this is temperatures for Asheville Airport, which is not far from where I live here. And you can actually see a good weather versus climate sort of story here. And that climate is sort of that smooth, temperature distribution throughout the year. And that's essentially, in the weather versus climate realm, climate is what you expect, weather is what you get. So, what you expect in a given year is that distribution, but then the red and blue lines are essentially what you get. So a lot of jagged lines of red and blue. This is daytime temperature in red, nighttime temperature in blue. And you can actually see these dots here. Those are record temperatures that that either tied or broken a previous value. So a lot of warming here, so a climate signal here. I believe there are more yellow dots here than there are red dots. That means there's warm overnight temperatures. And that is consistent with the science that is saying that overnight temperatures are warming faster in the southeast. Okay, cool. That's temperature. What about, what if we want to do accumulation graphs of precipitation or snowfall, let's say. So let's show me the data. Okay, here we go. Awesome. So again, this is also from that text file earlier that looked like matrix code. So in just like 100 lines of Python code, we can turn matrix-esque code into this. And so this is precipitation accumulation for every year at the airport going back to 1946. And it's looking at a couple of things. It's looking at the wettest year on record, which was in 2018, and it's looking at the normal, again, what you expect in a given year, which is the yellow line. So again, this is in a Jupyter notebook that you'll see at the end of the talk. And it says, instead of AVL for Asheville Airport, you can input any station that you want. So if you live in Boston, you can put in BOS, or if you live in, Miami, you can do MIA. Pretty much any airport code should work. And this should work internationally as well. So let's see, what else? Okay, so it's not just, so those are just weather stations on the ground. But as you know, we launched weather balloons. So we've been doing that for decades. So and again, we're an archiver, so we can, get data from past events. So this is historical upper data for OUN. Okay, so that's Norman, Oklahoma. Okay, so this has got to be a big tornado event. Okay, all right, here we go. Let's hope that's the case. All right. Show me the data. Okay, awesome, great. So this is May 3rd, 1999. Right, okay, so this is the big tornado event that happened in Norman, Oklahoma, and Moore, Oklahoma in May of 1999. For the weather nerds out here, this is sort of this is the weather balloon that was launched, which shows the skew T on the left, the photograph on the right. Long story short, conditions were very ripe for tornado activity on this day. Okay, cool. But this is historical data. So let's look at current data. So what about current data for OEX? What's that one? That's Omaha, Nebraska. Yes. All right. Let's do Omaha, Nebraska. Ready? Show me the data. No? Wait, why not? Why can't we show you that data? Check the map. What map? That map. Oh, right. Omaha is one of the stations that stopped doing weather balloon launches. So yeah, so here's a map showing the location of current observations for weather balloons in the U.S. and the ones that are either doing limited operations or none at all. And Omaha is one of them. Okay, so I can't show you the data for that. Okay, all right, let's move on. Model data. Okay, this one's easy. Surely model data is out there. All right, show me the data. Let's see what we ended up getting here. Where Jared is miserable. Oh, right. This is a very important variable. This is called the Jared is miserable index. It's not peer reviewed. We're writing the paper right now. But this is essentially showing cases in which the dew point's really high. So ergo, the hypothesis is that when dew point is high, Jared is miserable. So essentially, that little star there is where I'm located. And then right now it looks like I'm not miserable. Okay, great. So yeah, that paper's coming soon. If you do another live stream down the road, I can talk about that science. This is about HRRR data for you weather nerds, by the way. And this data is available in an AWS bucket. So you don't need, the way this notebook works is that you don't actually have to download the data. You can just do it all in the cloud and produce a graphic like this. And you can look at real weather data as well. Day-night satellite data. Okay, awesome. I love these. All right, ready? Show me the data. Okay, awesome. So we've got, okay, so this is GOES 16. Oh, this is Hurricane Helene or Tropical Storm Helene for us folks in Asheville that, well, that's all I have to say about that. So, okay, so this is Helene, and we've got, so daytime, true color, nighttime infrared over with city lights. Yeah, so this is a notebook out there in which you can go look at satellite data. This is the GOES specific one, GOES 19, which just became operational a couple weeks ago. This is all in an AWS bucket, and you can produce a plot like this in just a few hundred lines of code. Coastal water temperatures, right. So I have to remind myself again that there's an O in NOAA. So there's a lot of ocean data, and so like I said, NCI has a lot of ocean data. So let's try to get some coastal water temperatures. All right, here we go. Show me the data. You decommissioned that data set? Okay, I guess that happens. Sometimes data sets get decommissioned over time when they run out of funding or if they're not staffed or anything. Okay, but surely that's the only data set that's been decommissioned. A bunch of others too? What? Okay, so I guess All right, so if you go to this link, you can see all the data sets that have been decommissioned. Okay, all right, let's move past that. Okay, fine, I'm gonna get in trouble anyway, so let's talk about climate change, all right? Show me the data! All right, oh, stripes, okay, this is a good one. So we all know Ed Hawkins and, talks about climate stripes or the climate spiral. So it's a good communication tool that's very simplified, but to show climate. So the showyourstripes.info is the link, I believe. This particular one shows counties for the US. You can go to every single county in the United States and get your temperature and precipitation stripe. This was in partnership with climate.gov, which is funded by OAR, which I believe in FY26, they are going to get $0 in fund. Okay, anyway. And then also the person that I collaborated with on this site just told me yesterday she got fired because of no funding. Okay, all right. So this is up for now, but we'll see what happens there. Okay, great. Climate vulnerability. Let's do this. This is the last one, I believe. Hope this works. Show me the data. All right. So this is, what am I looking at? This is 2024 average temperature range. Okay, so this is an NCI product that tells you it's one of the top 10 years on record, 2024. We have a way to take the climate data and sort of smash it with vulnerability data from the Social Vulnerability Index. And we can look for sort of counties in the US that have high vulnerability and high climate. What? Stop saying climate and vulnerability. Those are bad words. Okay, all right. I'm sorry, Noah Combs. No, that's not true. They're not bad words. Well, first of all, in my performance plan, climate's mentioned 36 times and vulnerability is mentioned twice. So it's still work that I'm passionate about. But also, I still think people care about the climate and how it's affecting their vulnerability locally. It doesn't have to be temperature. It could be climate disasters, like let's say Hurricane Helene in Asheville, North Carolina, for example. So they're not bad words. I'm sorry. Okay. So anyways, if you want to play with this data, I have a GitHub link right here. We can provide it in a chat as well. And it is all public repositories that you can go get access to right now. And what it essentially does is it loads what we call the Jupyter Notebook, and it's plug and play. So it's already preset, it's got stuff already installed, but you can play with it to look at data in your particular area. It's basically a sandbox, and it's one of the many ways in which we're trying to get access to the data that's archived at NCEI. And we want you to use this data. We feel this data is very important for you to do the science. Here's some examples of repositories you can play with right now. Pretty much all the graphics that was shown in this talk you can get. You can also get some data if you need it for whatever reason. You can get some of those climate statistics that come out of NCEI. You can get the GOES data that's, again, archived in AWS. There's also some flooding data. I just pushed that out there a few weeks ago, so you can go play with that for particular flooding events. That actually uses both NOAA and USGS. And we have data from NASA as well in some of these repositories. If you are ambitious and want to play with it, every repository has a README that looks like this. At the very bottom of the READMEs is this little button called Launch. And it's a really cool tool where you just click on it. It takes a minute to load, but what it does is essentially installs all the packages that you need. So one of the things about Python is that you have to install packages and worry about dependencies. You don't have to here. So it's basically plug and play. So once you get in, then you can go play with the data and plot whatever you need. All right, well, thank you very much. I think I'm almost done with my time. Here are my social info. Okay, that's enough. I'm gonna just throw my phone away. But yeah, thank you for listening today. Here's all my social information. I will hang out for a bit if there's questions, and I can hang out after on the live stream as well if anybody needs help getting access to our data. But thank you very much, and I will take any serious questions you might have.
Thank you so much. That was, one of my favorite presentations I've seen throughout the live stream, although I don't know if I'm allowed to be biased as a host, but oh well. I mean, we have a lot of show me the datas in the chat. So we did have to filter through that to find some questions. Lots of thanking you in your role as a private citizen. I think maybe one question that could be useful to touch on is just like, could you give a sense of like how this loss of weather balloon information from certain stations might impact the forecast that's available to the American public?
No, that's a good question. I don't have any actual like full numbers in front of you right now to show you. The short answer is not great. Especially here, let me actually go back through all of my stuff and see if I can find that map. It's somewhere. Here we go. Yeah. So, I mean, a lot of the 3 stations up in New England, that's gonna, it might affect some of the model output there, and not just there, because when the weather balloons get launched, they go with the upper level wind, so they actually will go up and over the ocean, and it can affect that as well. And then a lot of those upper Midwest stations, Omaha, Nebraska, up there, and even Alaska. I mean, so I don't have official numbers. I've seen stuff through NCEP, which is the National Center for Environmental Prediction, that do some verification statistics. It so far doesn't look great, but again, I don't have actual numbers to show.
Yeah, totally fair. Makes sense. But yeah, thanks for pulling this map up back again. This is a really important thing, I think. Someone asks about, since you are a sort of data expert, like about how historical data is stored and if there's still some in unaccessible forms like microfilm stored by the NCEI.
Yeah, there are some in that basement. There's a specific room that folks can't even get into, but there is some old radar data that's in there that's on it's either microfilm or microfiche, I can't remember. But it's from radars that are over 50 years old, and they don't have, and this was before everything that's been going on, but they don't have the capability to scan those in and digitize them. But they get degraded over time, so they have to come up with a contingency plan to deal with that. So it's not just paper they have in there, but there is some microfilm and microfiche.
Yeah, cool. Okay, thank you so much for that. Someone asks, is a decommissioned data set just completely removed and discarded, or is it stored somewhere? I think that'd be useful to kind of outline.
That's a good question. The link, I don't have the link that, let's see if I can find it quickly here. So here's the link. So the link is up here. You just do a search for NESDIS decommission sites. It will tell you there. Most of the time, it's actually data that ended up somewhere else. So I believe the coastal water temperature still exists somewhere else. I believe it's in the Gulf Atlas data, but there's on the website. It gives you more information. It also tells you things like a certain website might be taken down, but then the data is getting pushed somewhere else. So, but that link will tell you everything you need to know. It is in most of the cases, no data is removed. It stays where it needs to. It just, is it getting updated? So like for the example, the $1 billion disasters, it's not getting updated, but the data is still there for you to play with up to 2024. But yeah, the website will tell you everything you need to know.
Okay, yeah, that's really helpful to hear. I guess maybe what's one, this is like, I'll reword this slightly, but like, since we're not necessarily losing data sets, but data sets are stopping being updated, is there like one data set that you're really like most concerned about, like not being updated anymore?
The data, it's not, yeah, I'll have to rephrase that. So that, right. Data that's in the archive is not going away. I'm more worried about data that's not being continually updated. Right. Like the weather balloon launches, for example. I mean, those are very important in weather modeling. The atmosphere is a 3-dimensional fluid, so it's not, we can't just get the information at the surface. We need to know information all the way up to 1 millibar, essentially. So that I worry. It's not that I'm worried about losing data. I'm worried about data that is not going to be updated, and I'm also worried about the people. Yes, this is, and now I am talking a little personal here. I am worried about the folks that are, that are overworked and tired, and staff shortages, and it can, even that can degrade things, and tough decisions have to be made, like the weather balloon launches. So I'm just worried about that.
Absolutely, yeah, me too. Thank you so much. Since we are out of time, but I know the chat thinks you should do a TED Talk. And and run a YouTube channel. And I know you posted your socials, but yeah, people are big fans. So thank you so much for an absolutely fantastic talk. I know everyone really appreciated that. I think that was a great way of showing the impacts of some of the things happening at the federal level, as well as a bunch of cool data. So really appreciate that.
Thank you.
Thank you. All right, y'all. Okay, so gonna do my spiel again because we are still in hour 73. I do want to thank y'all for joining the Weather and Climate live stream. If you're just tuning in, we have hour 74, sorry. We have 26 more hours to go. Very exciting, getting down to almost just a day. But before I launch into the next speaker, who has been one of our chat mods and background operators, it'll be very exciting to hear her talk. We want to talk about how important weather and climate forecasts are to everyone in this country. I think that was just outlined really well by the talk we just saw, how important all of this data is for the American people and to make good weather forecasts that keep people safe. As a reminder, the US has been a world leader in weather and climate prediction for a very long time. And a lot of this is because of this unparalleled network of observations that we have, including everything from weather stations, satellites, planes, weather balloons, boats, Argo floats, right? And so our system that we have from our excellent modeling capabilities and our great data is a scientific miracle. And we're really grateful that we've been sharing all of that with you. And as a reminder, a lot of this is publicly funded by the federal government, but in recent weeks, funding cuts have put this all at risk. And as Jared talked about, weather stations are so short-staffed that we're losing observational coverage, which is already hurting forecasts. Our federal research laboratories are being closed and shrunk, and funding for our basic understanding of the weather and climate is disappearing. I'm going to go ahead and put this banner back up, perhaps, if I can find the media asset. I don't know if I can find it. Fantastic. Thank you to whoever did that. As I talked about in my last little spiel, the administration's proposed budget, which is now being considered by Congress as of yesterday, is far worse. And we have this up here just to give you all the actual evidence of what we're talking about, which is that the NSF, the National Science Foundation, and NASA's Earth Science budgets are being proposed to be cut entirely in half. And it is also proposed that we completely eliminate, we being Congress, completely eliminate NOAA's research arm, the Office of Oceanic and Atmospheric Research, which funds a bunch of the federal laboratories that we've been talking about. And there's also proposals to end foundational research programs for young scientists like the NSF REU program, and also graduate research fellowships, which help create a future generation of scientists that create weather and climate predictions for you all. So once again, does not have to be this way. Please call your representatives. The banner's flowing across the bottom of the screen. Tried really hard to keep my face straight during that last talk because hearing all of that laid out like that is really exhausting and really sad. And we are here to try to change it. So yes, please call your representatives, tell your friends about this, get people on the stream, and we hope you're learning about weather and climate. So without further ado, let's welcome our next speaker. They, like I said, chat host, so you guys might recognize the name, Paulina Czarnecki, and she is a PhD student and will be talking about how do we know how much the sun heats Earth's atmosphere. So take it away, Paulina.
Thanks, Stella. Hi, it's really great to be here. My name is Paulina Czarnecki. I am finishing up my PhD at Columbia University, and I'll be talking about a topic we've heard a little bit about during the live stream, which is atmospheric radiation, or how much energy does the sun impart onto the atmosphere. And one very famous example of where we might have heard about atmospheric radiation before is, of course, Suki Manabe's Nobel Prize-winning work, where he considered how the radiation in the atmosphere and the changes to the temperature structure due to that radiation have to be balanced by changes to temperature due to convection. So I'll be discussing some methods of how we can understand this in models and my first PhD project, which was developing a new method to do this calculation. So very briefly, the sun is a really powerful driver of weather on Earth. So the sun shines, it transfers electromagnetic energy or radiation to the atmosphere this energy flows through the atmosphere and hits the ground. This causes uneven warming throughout the atmosphere, and as that warm, hot air rises, this can cause weather events. So for example, this can cause clouds to condense, and it can also cause larger overturning circulations that create larger weather patterns. So in order to be able to predict these weather patterns and to be able to understand our climate and our weather, we need to be able to calculate how much of this heat is happening in the atmosphere at very high accuracy, and we also need to be very efficient. This is not an easy problem. So radiation or sunlight is colorful. So here I am plotting the amount of energy that is flowing from the sun for all of these colors. We're probably familiar all with the visible part of the spectrum. That's the light that you see when you look outside. But we also have ultraviolet radiation over here that the sun is imparting, and this really wide range of infrared radiation. So in this curve, I'm showing the energy at the top of the atmosphere after it has traveled through space to our Earth. But not all of that energy makes it to the surface. So now overlaid, I have the part of the energy for each color that actually makes it to the surface. And you might notice that this is not a uniform attenuation of this energy. There's different parts of these colors that actually make it to the surface, and some of them are blocked. And this is because there's different things in the atmosphere, right? There's different particles, there's gases, there's clouds, of course, that attenuate this radiation. They absorb it, or they scatter it, or they reflect it in different ways. And the way that this happens depends on color. So now I'm adding in the gases that are active in each of these colors. So we might be familiar, for example, with ozone. The ozone layer protects us from receiving all of the ultraviolet radiation from the sun at the surface. And you can see that in this ultraviolet part of the spectrum, the radiation that we get at the surface is a lot smaller than that we get at the top of the atmosphere. So not only is this a colorful problem, not only do we have the spectral dimension, we also have this vertical dimension. As the radiation is passing through the atmosphere and it is hitting different gases that are in different places in the atmosphere, this spectrum looks very different in this vertical dimension. So in this little schematic here, I've selected just one atmospheric column and showed you how different this spectrum of energy looks at each of these points. And so this turns into an uneven heating of the atmosphere, which of course contributes to these weather patterns that we see. And then not only is this a vertical problem and a colorful problem, it's also a spatial problem. So we have one of these atmospheric columns at each place on Earth, and the uneven distribution of all these gases means that all of these spectra are different at these places. So as we've heard in some of these other talks, it's really warm and wet in the tropics, so you will have more of this absorption by water vapor, for example. And in the poles, it's drier, so these spectra will look different as we look at different parts of the Earth. So this is a huge problem. You have the spatial dimension, you have the colorful dimension, and you have the vertical dimension. And radiation is only one part of this huge piece of code that is the climate model. So in this schematic from the Department of Energy, you have all of the pieces that go into a weather prediction or a climate model. And we're really just concerned with the atmospheric part in this talk, and really just the radiation part. So this huge problem has to be solved incredibly fast and incredibly accurately, and not take away any power available to the other parts of the climate model. So it's a really difficult problem. So given this spectrum of energy, how do we know how much energy is actually being provided? If we want to know the total amount of energy at each of these colors, we just have to add them all up. So in other words, the total energy is just the area under this curve. And usually when we want to understand what the area under a complicated curve is, we do something called numerical integration or quadrature. So we split this really complicated shape into shapes that we do understand. So in this little animation, I'm showing this curve being split into rectangles, and we really know how to take the area of a rectangle. Maybe you remember from grade school that the area of a rectangle is just the base of the rectangle. times the height. And in fact, if I want the exact answer to how much area is under the curve, I just have to split this into millions of rectangles. And the answer that you get from that is very accurate. However, millions of rectangles are incredibly computationally expensive, and we cannot afford to do this in a climate model or a weather model. So the question is, what is the smallest number of rectangles that we can get away with? How can we optimize the number of rectangles? And so, of course, I'm not the first person to have thought of this. There's a standard procedure that has been developed, among other places, at NASA GISS, which unfortunately we watched the last day of on Wednesday. And what we do in this procedure is we sort this electromagnetic spectrum. We sort it from the least energy to the most, and we get this smooth curve here. And then that curve is really easy to split into very few rectangles. So why do we need a new method if we have this great method that works? The state-of-the-art approach, the paper that I cited there, was developed in 1990. So this approach is quite old. It's been around for a while. It's difficult to understand and develop, and there's very few experts at each modeling center that are working on these codes. And it's developed for very specific conditions. So if you're interested in going really far back in time for paleoclimate scenarios, where, for example, the CO2 was a lot higher than it is now, or if you're interested in looking at other planets, such as Mars, then this code is really difficult to adapt. And so I'm actually a mathematician by training. I'm in an applied math program, and I wanted to use this math training to address this problem because mathematically, it's also a very interesting problem, and it's a useful problem that can be applied in models. And so our goal with this method was to create an approach that is at least as good as the state of the art. Of course, we want to be as accurate and as efficient as what already exists, but we wanted to improve on the adaptability and the understandability of the method. So here is a brief overview of our approach. If we want to split this spectrum into boxes, we can ask the computer, what is the best way to split this rectangle into boxes? So in this animation, I'm showing a bunch of different boxes that the computer is trying. And it's going to randomly try a selection of boxes. It's going to calculate, according to those boxes, what the area under that curve should be. And then it's going to ask, is this better than any set of boxes I've seen before? And as it tries all these sets of boxes and it evaluates whether this set of boxes appropriately estimates the full area under the curve, that full million box estimate, then it can approach a better and better answer. And so, of course, like I have been mentioning, this is a really multi-dimensional problem, and we want all these boxes to be the same across all of these different pressure levels and across all of the different places on Earth. So the height of the box is going to be determined by which gas is absorbing there, and that is the information that the scheme is going to receive from the climate model. Sorry, there's some New York background noise. So the height of the box is going to be determined by which gases are absorbing where, and the width of the box is going to be determined by my algorithm. So when this is actually implemented in a climate model, the climate model just has to tell me what are the gases, the temperature, and the pressure of this point, and I will tell it with about 30 of these boxes what the total amount of energy should be. And then if we know how much energy is going down through the system and we know how much energy is going up through the system, we can understand how much the atmosphere is warming due to that flow of energy. And so I can show you here in this black line, this is the warming rate throughout the atmosphere. It's on the same axis as this animation. So up here is the top of the atmosphere and here is the surface. And the black is this million box calculation that shows how much energy is flowing through the system. And in red, I'm showing an estimate for some of the boxes. And like I mentioned, the computer is trying all these boxes and it's evaluating how well the boxes are estimating this total energy. And So if I move this forward in time, as this optimization happens, you can see that the red curve is going to converge really well to the black curve. So really briefly, I'm just going to show a results slide of how this works. So here again in atmospheric science, we like to plot things in the vertical. This is the top of the atmosphere and this is the surface. And on the x-axis, I'm showing the rate of error in this warming in percent. So the state-of-the-art method is straddling this 10% line pretty well. And if you remember from the previous slide, the heating rate in the atmosphere is about 2 degrees. So 10% of 2 degrees is a very small error. And all of these different spaghetti lines here are just different atmospheric conditions. So as I mentioned, we really want this method to be flexible to different concentrations of different gases. And then if I add onto this R method for just present day conditions, so the narrowest set of possible conditions, for example, for implementation in a weather model, our method is closer to the 1% error line, so that's really exciting. And of course, we want to look at this method for all of the different atmospheric conditions, and so that is what these colors are. This is as I change different gases by really large amounts, how our method does. And so you can see that we are at least as good as the state-of-the-art method, and we are more flexible and easier to develop than the state-of-the-art. So this is great. And this is something that we are continuing to work on and to develop and to take into being ready to implement in climate and weather models. So just really briefly, before I wrap up, I'm going to discuss the impact of federal funding on my own work and my own career. Like many of our other speakers, I did a research experience for undergraduates, which was funded by the NSF when I was an undergrad. And that was really impactful and really brought me into science as a field. And as we've maybe heard on this stream, these programs are in danger of being shuttered. They are considered diversity, equity, and inclusion grants often because they are inviting and bringing and training new scientists into the field. So it is critical that these programs remain open so that we can continue training new generations of scientists. During my PhD, my whole work has been funded by the federal government. And this kind of funding allows us to develop and implement these innovative approaches. And this is something that we have to try and develop through trial and error. And we can't always know that something is going to work ahead of time. And so funding from the federal government really allows us to explore these new potential innovations without being able to guarantee that it's going to work. And this is something that private funding just unfortunately cannot support. And finally, just like very fundamentally, we're earth scientists and we really want to just learn to understand the earth better. And this funding allows us to do our science. And so I'll just finish with my conclusions. Weather and climate models need to quickly and accurately compute how much energy is passing through the atmosphere. And we've developed this new method to do this. Our method is fast, it's generally pretty easy to understand, it can flexibly handle different atmospheric conditions, and federal funding is crucial to improving our weather and climate forecasts and developing these new methods. So with that, I am happy to take any questions.
Thank you so much. That was fantastic. I think people in the chat really liked your animations.
Thanks.
Yeah, there was a lot of love for that. And I think maybe one of the quick follow-up questions from folks in the chat was about like whether or not the animations that you created to show how your method was working are open source in any way. Someone asked if there's a GitHub. Someone asks if they could use it for their students.
Oh, that's an amazing question. I did not put them on GitHub. This is actually just like random boxes because it's just an illustration. But I could put them on GitHub. Yeah, that's a great question. Yeah,
Cool.
actually, I should actually also plug that the code to actually do this is a Python package, and it is open source, and it is on the internet. So that's probably not what this person was asking necessarily, but yeah, I can put the animation up on GitHub as well.
Cool. What's the Python package called?
Oh, it's called Data-Driven Quadrature.
Cool. Okay.
Yeah.
Fantastic. So hopefully that's answering some of the questions in the chat for that. Let's see. I guess how much computer time do you need compared with current methods?
Great question. So the computer time or the computational power that is generally counted in these methods is in the number of these boxes that we draw. So this state-of-the-art method here is, I believe this is 128 boxes, and ours that I'm showing here is 64. So that's an order of magnitude decrease. There is a few that are like very highly optimized. There's one out of ECMWF, the British Weather Service, that has just 27 boxes, which is a really incredible optimization. So ours is at least as good as the state of the art, better than some, and commensurate with others.
Cool. That was a very diplomatic answer. Fantastic. Let's see. Andrew asks, how did you get into climate research from your math background?
Oh, great question. So yeah, I'm actually still in an applied math program. I was really interested in working on problems where I could like see the phenomenon and like be able to intuitively understand it. So that was kind of my gateway. And there's just a lot of really fun problems in the climate field, I think, that are really addressable with a math background. There's a lot you can do to kind of help the methods and to do the calculations that are really important to weather and climate prediction.
Yeah, absolutely. I think, yeah, to the person in the chat, or I guess, well, that Andrew's the person in the chat. Andrew knows all of these things. Never mind. Andrew doesn't need additional explanation. But yeah, like for people, I guess lots of folks come to weather and climate from applied math or applied physics backgrounds because we're interested in things like seeing real world applications and working with phenomenon that we can observe or that are part of our system. So yeah,
Absolutely.
super cool. Let's see. Okay. I guess like this is just kind of we're like little like yeah, a little bit of a theoretical question, but like, so you talked about like how our original method is kind of old, and like how old is too old in weather and climate science? Like how far back do we think we have methods that we trust?
Yeah, I mean, I guess it's not even about really like being old or too old. Like, of course, like many of our state of the art methods were developed quite a while ago, and they work very well, and they are great, and we're very grateful to have them. But it's just about like, we should continue being able to innovate and continue being able to revisit these questions and see if we can do it differently or better, and to be able to make these updates. And so I guess I don't know if I have an objective answer for how old is too old. It's just like exciting to be able to revisit things that are considered maybe more solved problems and see if we can do it a different way.
Yeah, absolutely. I guess maybe let's see. I think we're gonna vamp a little bit here, so I'm just gonna ask you some more questions if that's cool.
Sounds great.
Yeah. I guess maybe like, what is your next step with this research? Like, where are you in your program? What are you doing next?
Yeah, that's a great question. That's a little bit topical, I think. So I am finishing my PhD over the summer, and I actually applied to a lot of US postdocs at national labs to be able to implement this method in climate models. And I've written a bunch of proposals to be able to do this work. And unfortunately, a lot of these programs simply do not exist anymore. And so we're really hoping to get this into models and to be able to spread the use of these kinds of methods. And unfortunately, with the state of the funding, it doesn't seem like that's going to happen right now. So that's pretty disappointing. And so, yeah, I am going to see how it goes in the future. Yeah.
Yeah, that makes sense. I guess maybe, yeah, like a follow-up question is like, will your method eventually become the next state-of-the-art calculation? So like, yeah, is that the ultimate goal with this?
Yeah, I mean, that's always like kind of a dream, right? That something that you develop can be like used in climate models and in weather prediction and like widely appreciated. So that's definitely something that we are striving for, and we've written up this method in a paper. We're working on a follow-up to do like all this really rigorous testing in different scenarios. I think there's some efforts with some of our collaborators who are hoping to push this towards being implemented in a climate model. So if it becomes the next state-of-the-art calculation, that would be amazing. And if someone comes along in 30 years or less and comes up with something better, that would also be amazing.
Absolutely, yeah. Yeah, how scientific progress gets made, right? Yeah. Totally. People are asking if your method for heating would work in other planetary atmospheres.
That is a wonderful question. Yeah, so the idea is, of course, in all the figures that I've shown, this is trained on Earth-like atmospheres. So that means that we're looking at concentrations of gases that occur here or have occurred here on Earth. If you wanted to take this to a different atmosphere, such as Mars or Venus, which I know there's people who are hoping to do simulations of, then we would have to retrain the method. So we would have to find better boxes that are centered where those gases probably are more active, because the spectra are just not the same. But that is a hopefully pretty easy process at this point. Hopefully it's fully automated. Of course, you would have to choose in your data what you consider to be representative, or like what kind of data that you're feeding into the training. But then we've got the Python package, and we've got several helper packages and papers that hopefully make that process quite easy. So that is definitely something on the longer end of our to-do list, or if anybody else is interested in that, I would be really excited to see how that goes.
Yeah, absolutely. That was a great answer. Yeah, thanks so much. Okay, cool. I think that, let's see if we have one more question. I'll throw it at you. Let me see if I can find one from the chat. Lots of people saying cool things about your animations.
Oh, thank you.
And your colors.
Oh yeah, I think Bjorn Stevens probably coined that one, so I should give credit where that's due.
The colorful problem.
Yeah. He has like a paper about how, with Lucas Kluft, about how radiation is colorful.
Nice. Okay. Yes. All right. Well, cool. I think we are at time, so we're going to go ahead and move on. But thank you so much. And you'll see her in the chat probably over the remaining hours of the.
Yeah. Thank you. I'll be around.
Yes. All right. Cool. And so I'm going to go ahead and take her off screen. And yeah. Welcome, if you're just tuning in, to hour 74. Before I launch into my host spiel, I'm just going to pop this question up on the screen, which was how many calls do you have and how many more to cross the 10K finish line? And so we are at about 6,700 calls so far. And we do have, for those in the chat, like an unofficial goal. I guess we could have an unofficial goal of crossing the 10K finish line. Let's make it a goal. Why not? And so, yeah. 10K would be a fantastic goal. So that's like giving us what? I'm really trying to do math in a world where I have very little brain cells, but 3,300 calls left to hit 10K. So yeah, I'll get that banner up across the screen in case you've forgotten. I know I've said it to you many times today, but wclivestream.com/act. All right, okay. Let me run through my host spiel real quick, and then I'll introduce our next speaker. So as a reminder, I'm Stella. I'm your host right now. I'm a PhD student at the University of Washington. And Before I begin, I want to remind you that everyone is speaking in their personal capacity, and the views represent themselves and may or may not represent the views of other speakers. And then I'm going to go through my SAG spiel, which is that weather and climate forecasts are super important to you and to everyone in this country. We know this, and we also know that the U.S. has been a world leader in weather and climate prediction for a long time. We've heard about Tsukuminabe. We've heard about the first computerized weather forecasts and the first climate models, so that we can know what to expect and tell you all what to expect in weeks and decades to come. And to make these forecasts work, we've had an unparalleled network of observations, including weather stations, satellites, planes, balloons, boats, and floats. We've heard about all of these things and all of the cool data they collect. And the resulting systems that we have to make forecasts and observations is truly a scientific miracle. And it's been really cool to share all of that work with you all. But this was made possible, all of this, by decades of investment from the American public and taxpayer-funded federally funded science. And so in recent weeks, the federal cuts have put all of this at risk, and our weather stations are very short-staffed. We're losing observational coverage, which was talked about a few speakers ago. Our laboratories are being closed or shrunk, like Paulina mentioned, and funding for a basic understanding of the weather and climate is disappearing. And in addition to that, the administration's proposed budget, which is now being considered by Congress as of yesterday, is far, far worse, and it would cut the NSF, the National Science Foundation, and the NASA's Earth Science budgets in half. So you can check out the specific details of that using the QR codes on the screen here. The proposal would also completely eliminate NOAA's research arm, including many of the national labs that we've heard talked about, and end programs for young scientists like the National Science Foundation Research Experience for Undergrad, or REU, as well as the Graduate Research Fellowship. So those programs are really essential to building the next generation of scientists that can help create forecasts that protect American lives. And so it doesn't have to be like this. And if you like what you see here, we ask you to please use the links on your screen that's scrolling across the bottom, wclivestream.com/act, to contact your representatives. Let's get up to 10K calls and tell them to save our forecasts. And also, please keep spreading the word for our last 26 hours. Yeah, cool. Okay, so without further ado, I'm going to introduce our next speaker, which is going to be Dr. Cecilia Bitz. Cece is a climate scientist at the University of Washington. She's one of my professors. Super excited to have her on screen today. Hi, Cece. And she's going to be talking about polar climate change.
Hi,
and
Stella.
So take it away.
Oh, thank you so much. This is such a privilege, and thanks to all of the organizers. It's really been just extraordinary efforts, and I've just had a blast watching the talks. I bet you have too, Stella. Just incredible. And yeah, it's a real privilege also, since I had Stella in class. And you know, the changes that are being threatened right now would really have the biggest impact on our early career scientists. So it's people like Stella and a lot of the research that I'm going to highlight today that I'm really concerned most about. But let's just get into the science, because that's what we do and that's what we're most excited about here. So I'm going to talk about polar climate change and why you should be concerned about it and what's happening today. And let's see, forward. You know, ice in the climate system is really what the poles are all about. There's sea ice, there's ice on land, and snow, all of them being highly reflective. And they keep our planet cooler than it would be without it, because they're reflective and they insulate, for example, keeping the heat in the ocean and not in the atmosphere. And there's lots of people in the Arctic. You know, I think we often think of it as this remote place, but there are millions of people who live there. It's not remote to them. And many of them are in Alaska. 600,000 or more people are in Alaska's Arctic. And, you know, they're threatened by climate change. The loss of sea ice is really important to their livelihoods. You know, sea ice is something they use for transportation and for hunting, many subsistence food. Folks who live there are, you know, just they're unable to hunt for the kinds of foods that actually they live on. And this is an example of an Arctic village. This is Kivalina, and it's taken by a villager there. And you can see the sea ice is just right up against their village, right? And the sea ice, when it disappears, it lets them be completely vulnerable to the waves and winds that rush in over the ocean. And, you know, that had never happened before. In the season when the storms are the largest, which is in the fall. And so they used to have sea ice coming in September, and now it's like a month later when these storms are already really amped up. And this is what this village looks like in the summer. So you can see it's just surrounded by ocean. So they're like on all sides, and they depend on this seawall to keep the waves and erosion from protecting them. And in the past, the erosion was just constantly crumbling their village. The seawall is all they have now, and it's doing its job, but it's not clear it will always be there to take on the full brunt of the waves. So if we look back at the global picture here of what climate change has looked like over the past 60 years or so, what we see is that the largest warming has been in the Arctic. It's something like 3 times higher than the global mean. In contrast, the Antarctic is doing something a little surprising. It has a mixed response, even in this 60-year long trend. So I want to try to talk about both. How could these places that have ice and snow be doing such different things? And we think there's a lot of reasons why we should see land and sea ice both decreasing under global warming, because when sun is out and there's ice and snow present, it's really reflective. And so a lot of the incoming energy from the sun is just reflected back to space. But when the sea ice is gone or the land ice is gone, what we see is all this absorption. And so that amplifies the cause of the sea ice loss in the first place. So it amplifies the warming. But that's not it. There's also just the fact that it's warming at the surface. It changes the atmospheric stability. And that in turn amplifies the warming. So we have kind of 2 major climate feedbacks that both reinforce the warming where we see ice loss, either kind, land or sea ice. But the sea ice is the one that we've been seeing the biggest change because it's naturally quite thin and really vulnerable. And so when we look at the things that cause the amplification in the Arctic of climate change, and we try to itemize which ones are the biggest factors, what we see is this adjustment of the atmospheric temperature profile, what we call the lapse rate feedback, is up there, as well as the albedo, the reflectivity related feedback. And then in contrast, all the other major things that influence the climate kind of have a neutral effect in terms of whether they warm the Arctic more or the tropics more. Now, I've been using these terms land ice and sea ice. Both of them can float on the ocean, but in the case of land ice, it's in the form of icebergs. And those are the really gigantic chunks of ice. And in contrast, sea ice, it's quite vulnerable. It's only about the height of a person. There's a person there for scale, and you can see it's very flat compared to the big chunks of iceberg ice that has fallen off the land. And when it comes to sea level rise, it's the land ice that matters, right? Because that wasn't floating in the ocean. So when it falls into the ocean in either form of ice as an iceberg or meltwater, it raises sea level. But when we're talking about ice that's already floating, like sea ice or the giant ice shelves that fall off the land and survive on the ocean for many centuries, those are floating already. So when they melt, they just fill in the hole that they displaced. And so they don't cause sea level rise, but they're still in the close proximity to the ice that can cause sea level rise. So we don't want any of it to disappear. And another really important thing about ice is that it influences our weather. Where there's ice compared to no ice, the temperature gradient is quite large. And those temperature gradients are what fuels our storminess. And so when you look at where the storms are, they're right along the ice edge in the high latitudes. And then when the ice retreats into the Arctic in summer, the storms follow the ice edge. And so then the storms are in the central Arctic in the summer, but they're in the subpolar Arctic along the ice edge in winter. And this is some of the work from a student in our department, Robin Clancy, and he finished his PhD a few years ago. So he's moved on to greater things, but his paper really illustrated the interaction between ice and storms. So, we should be really concerned about where ice is on our planet. And what we're seeing is in the annual mean, this is just a way to plot both the Arctic and the Antarctic easily together. They've both decreased tremendously lately, but the Antarctic, as I said earlier, when we saw about a 60-year change in temperature, there were patches around the Antarctic that actually were cooling. We saw this interesting pattern in the sea ice as well, where it was expanding prior to 2015. And yet since then, it's just, it's tremendous, the decrease we've seen in just 10 years. And now actually caught up with the Arctic. And even now we've seen a more reduction in the Antarctic in that, a lower value in the last years in the Antarctic, where we thought things had been comfortably increasing. Now, the sea ice interacts dramatically with the ocean, and the ocean also responds to the sea ice. So all of the places where we see sinking in the world's ocean is right at the edge of the sea ice, or between the Antarctic continent and the sea ice, where there's winds blowing the ice off the coast, and there's large growth rates. So there's this close connection between where sea ice lies and where the ocean sinks. So when we look at the world ocean in a profile view here, depth versus latitude, as I said, the sinking occurs, I think you can see my mouse, right? Maybe not. Actually, I'll just describe it instead. The sinking occurs right at the ice edge in both hemispheres. And that heat, I should say, is also bringing heat across the hemispheres, away from the Antarctic and towards the Arctic. So any kind of global warming that occurs, if it's starting at the surface and takes a long time to reach depth, we'll see it kind of conveyed from, as it passes along the Earth's surface, acquiring more and more of that increased heat from human influence, and then bringing that into the Arctic. So it's an additional factor for why the Arctic is decreasing more rapidly and more early in response to global warming. So weakening this circulation, though, would be beneficial, and that is thought to be a consequence of global warming, as it's driven by both the sinking in the North Atlantic and kind of the suction in the South Atlantic and around Antarctica. But when there's additional meltwater coming from Greenland and from the increased precipitation, this circulation can decrease. So that would be a good thing, and it might be beneficial to the portions of the world that are just downstream from where that Atlantic ribbon of heat comes up into the northern North Atlantic, so like Norway and England. Though we don't think it's enough to actually change this, change it from a warming to a cooling. It would just be less warming. Now, the Southern Ocean is something I want to spend a little bit more time with, because it's pretty complicated in contrast in some ways to the interaction between ice and the Arctic. And that's because of this upwelling I mentioned, that the overturning circulation in the ocean, the major upper cell largely upwells in the Antarctic. And even though it's relative to like our current mid-latitude climate, it's very cold relative to what would happen if there weren't any upwelling. That water brings up a little bit of warm water. So it's just a few tenths of a degree below freezing, but it's still, compared to what would be at the bottom of the ice, at the ice-ocean interface, freezing temperatures, it's substantial. So this big reservoir of warm water is just below the surface of the ice in the Antarctic, and it's easiest to see if we look at a temperature profile. So we'll do that in a moment. But just to say, what does all this mean for how sea ice grows? In the Arctic, we have this very cold halocline layer under the ice, and that's because as the sea ice grows, it rejects salt. And that salt in turn is very dense, as well as the cold of the ocean when it freezes, right? It's losing heat, and seawater, unlike freshwater, sinks. So this forms this very special cold halocline that exists in the Arctic, but it actually doesn't exist in the Antarctic. But it's a good thing because you can see it's actually covering this warmer Atlantic layer. And that in turn leaves us with sea ice formation that's kind of throughout the Arctic. We actually don't have very much upwelling of heat, so we actually instead can grow sea ice throughout the Arctic, but not at the very edge of the North Atlantic, where it does meet those hot, warmer North Atlantic current waters. In contrast, like I said, in the Antarctic, we have warm water, but it's pretty well protected below the surface under normal conditions. And this is a section of temperature in the Antarctic. And you can see that this few tenths of a degree warmer water is sitting there below where there's sea ice on the surface above. So we think this circumpolar deep water is there and always slowly diffusing heat upward. But normally that if it isn't available to reach the surface in great numbers, we don't expect to see the sea ice really disappear rapidly. But unusually, kind of, I think what is a surprise to most people is it's enough heat that's generally in the background level diffusing upward, but there's very little sea ice growth in the Southern Ocean. Instead, it does something really unusual, which is being under the large westerly flow of storms around the Antarctic. There's just tons of snow that falls, and it's accumulating on the sea ice, flooding the sea ice because it's so deep, and it turns the snow into sea ice. So that sea ice kind of grows from the top in the Antarctic in contrast to growing from the bottom in the Arctic. So there's lots of interesting differences between the two hemispheres. And now the question is this the reason why we've suddenly seen a big change in the Antarctic? Is that circumpolar deep water suddenly now available to melt the sea ice? And the answer is it looks like that. But before I go there, I want to get back a little bit more into like why we had an expansion of sea ice in the past. And, the ozone depletion that was occurring in the last 50, 60 years, although largely we're not continuing to deplete it any longer, the consequences of it have remained. And that is a westerly wind strengthening and a shift towards the south. And that westerly wind has changed somewhat the location of that warm circumpolar deep water. We think it was more available to melting the shelves, which are naturally a little bit lower than the sea ice. So we've been seeing some of this meltwater kind of flooding this surface, which is good because it stabilizes and keeps the heat. Well, it's good for the sea ice, not good for the shelves, because it kind of keeps the heat at the shelf level and not at the sea ice. And there's evidence, plenty of evidence from elevation changes of Antarctica that a lot of it is occurring at the shelves. And then if we go further into land where we have data that shows us the land ice changes, it's been decreasing as the shelves decrease and the ice actually moves off the land with greater speed. But all of this would have consequences in terms of water running off into the ocean and potentially stabilizing. And so this is something, though, that our Earth system models haven't taken into account because they don't generally have ice sheet models. And so we added it in an Earth system model simulation. And when we did that, we didn't know exactly how much to add because we're not simulating this ice sheet, but we made estimates based on the amount of precipitation that has fallen on Antarctica historically, as well as what we think has increased over the last few decades. And then that is part of this increased meltwater, as well as the fact that there's this upwelling heat available. So anyway, we added these big amounts of additional fresh water to simulations, and when we did, we got freshening and a cooling at the surface. But because of increasing the stability, right, we trapped more heat below the surface. And that heat is available because it's just at the right height of these ice shelves to continue to melt the ice shelves. So it was kind of a positive reinforcing mechanism. So we think that is a part of the explanation for why we saw expanding sea ice and cooling around Antarctica for so long. But in the last few years, really, what we think is occurring is that the westerlies are returning a little bit more towards normal as the ozone is no longer continuing to deplete. Actually, it's just not really clear exactly why, but I'm reasonably sure that it's a result of the circulation changes around Antarctica. But this is data that shows that temperature at the surface was cooler prior to about 2015, protecting the sea ice, allowing the temperatures to remain cold around Antarctica. And then suddenly, look at this, they're warmer in around the year 2015. So this is our best estimate of what's been happening in Antarctic. And I'll just wrap up with a little story about my group's efforts, which has been to try to see if we could predict these a couple of years that were just extremely low in sea ice. And the truth is, yes, we're actually able to predict them almost entirely, and even in advance, with wind that has been prescribed in our climate models. If we actually alter the wind so they're exactly what we observed, then we can reproduce these really big anomalies. So I'll conclude with just a summary that the Arctic has warmed about 3 times faster than the global mean in the last 60 years, and Arctic sea ice has declined by about 40% in late summer months. In contrast, and this has really big implications for Arctic communities. In contrast, the Antarctic sea ice was increasing before 2015, and it's not completely understood, but we think it's largely influenced by the winds and the consequences of the winds on the ocean. But in addition to that, we think we saw this trapping of heat more at depth and more meltwater along the shelf cavities. So the shelves were contributing to kind of maintaining this colder sea surface temperatures and more expanded sea ice. And now we think the wind circulations has changed enough so that that heat has actually become available to the surface kind of suddenly. And now we're seeing these big losses, and year after year with internal variability in the system, we can actually predict when they're at the record level. So I'll end there and take questions.
Thank you so much, Cece. This was great. Always love hearing about ice at the poles. Yeah, we have a lot of great questions in the chat. I guess maybe one quick one that I'm trying to find. How far back does the data go for observations of sea ice?
Well, that's a great question. We have continuous sea ice records since 1979. At first, they were every other day to save a little energy, and then somewhere around, I think it was 1988, they became daily. So it's a tremendous record and so valuable because it's a there aren't that many ways we can directly visualize climate change, right? Often we visualize impacts, but this is a direct, visible impact. And then we have some snapshots prior to that from things like shipping and whaling, and also when they were testing those satellites in the 70s, they weren't continuous, but we have some snapshots.
Cool. Yeah, thank you. So it sounds like, about the same time that a bunch of our big atmospheric data sets
started, around that.
That's right. With a huge investment from the American public. Thank you so much for making this data available, right?
Absolutely. Yeah. Another question about the data is, how do we measure the properties of water underneath the sea ice?
Right. That's harder for sure, because our typical mode of measuring the world's ocean is shipping from ships. So we can put in moorings under the sea ice, and then when we want to return to get them, they release they have an automatic release, and the mooring gets trapped under the sea ice, and then divers go in and get it. Obviously, you can guess that's pretty costly. So the more modern methods have been to use autonomous vehicles, and those are amazing records, as well as seals in the Antarctic. So they actually fix an instrumental in the head of the seals, and they're happy as can be. In fact, they seem to have even a better social life with these instruments attached to their heads. Who would have thought?
You heard it here first, folks. We have scientist seals, that are popular. Okay, cool. That's a great answer. Thank you so much. What is the difference between ice calving and ice thinning? Does one cause the other?
Well, that's also wonderful. And I am, a sea ice expert, but I definitely study and talk to a lot of ice sheet experts. So I think you're talking about land ice thinning. There's a couple methods, right? It can just simply melt or sublimate, and then the calving is another loss off of land, and they all either way cause the mass to decrease. And interestingly enough, in Antarctica, there's very little melt at the surface because it's so cold. But it's clear that it has been losing mass, right? We have excellent satellite data from GRACE. It measures gravity, and the land ice has lost mass, but it's because of increased melt at the shelves. So less resistance from the shelves as they've thinned through melting at the bottom. And now the land ice is moving faster off the land, and that's calving more. So it's complicated.
Yeah, absolutely. Thanks for trying to answer that complicated question. I guess maybe we are it's noon here in Pacific time. I guess maybe 3 p.m. out on the East Coast. So we're gonna have to move along. But thank you so much to everyone in the chat for some really fantastic questions about sea ice and climate at the poles. And thank you to Cece for a really great presentation. Really great to have you here. And I guess I'm going to turn it over to Cece as our next host. So you're not getting rid of her. She's going to be around on screen. Thank you so much for volunteering your afternoon. And so, I will hop off the screen and take it from here, Cece. Thanks so much again.
You're welcome. Have a great weekend. I'm really pleased to be the host now, and it's now my privilege to introduce the next speaker. But first, I have a little message to give you, and mine won't be as professional as Stella's because she's been one of the organizers and really involved deeply in getting this whole program going. But I just wanted to say hello to everyone who's just joining, and thank you for joining us. And we're almost down to our last 24 hours. But, we actually have, this is the start of the 75th hour, so 25 hours left to go. And, this has just been a really tremendous effort for us to, highlight the great work that climate and weather scientists do in our country. And I want to also, recognize that the American public has been funding us to do this research, and we think of ourselves as, servants to the American public. We're doing this to improve the lives of our society, and keep our communities safe from hazardous weather and hazardous climate change. We take prediction very seriously. That's a big part of our work. And that's what is important for protecting communities. We have many things to celebrate among our scientific contributions. We've been leaders in computing and computing impacts of climate change and Pollution, atmospheric chemistry is another big area of research that keeps humans healthy and safe. So I just want to, again, recognize that this is through the investment of the American public, but that investment is being threatened right now. We've already seen major cuts that have impacted many government workers, especially the early career government workers, which concerns me the most because you've heard probably many of these live stream presentations given by early career scientists, and they're so talented, so committed and devoted and hardworking, and they're important to helping humanity, and yet they're not getting to use their talents, and the American people are losing that resource that could be really beneficial. So it doesn't have to be this way. A great country has great science, and we want to ask you to call your representatives, contact them with letters, anything that works for you, and let them know that you value weather and climate research. So with that, I'm really pleased to introduce the next speaker, and Galen, I got the wrong message. I was told it was Liz Moyer, so I'm going to wing it. I fortunately know Galen. I'm really thrilled to be saying welcome, Galen. And Galen, I met you first, I don't know, maybe 20 years ago. And I remember vividly having just this fantastic conversation. I learned so much about the carbon cycle and ocean biology from you. So take it away, and I'm really thrilled to hear what you have to say and share with us today.
Yeah, thanks. Cece, thanks for your talk too. That was really great warm up to watch before getting into this. I want to talk about the ocean and how the ocean helps with climate change by removing a lot of the carbon that we put in the atmosphere. And I want to talk about the ways we use different approaches using data and using numerical models, many developed at NOAA, NASA, and the National Science Foundation in order to understand how the ocean carbon sink is working now and how it's going to change in the future. So my name is Galen McKinley. I'm a professor of Earth Environmental Sciences at Columbia University and Lamont Doherty Earth Observatory. And really happy to be here today. So I'm pretty sure everyone here is aware that the atmospheric CO2 is rising due to the emissions of carbon by human activity. But you might not be aware that not all of the emissions that we put in the atmosphere remain in the atmosphere. In fact, the ocean and the terrestrial biosphere together absorb about 50% of all the emissions we put in of CO2 that we put in the atmosphere every year. So those two sinks act as a real sponge to sop up about half of our CO2 pollution. And therefore, together, they really mitigate the effects of climate change to the tune of about 50%. So understanding how these sinks work, understand how they are currently changing, how they might evolve in the future is really a critical piece of understanding how our emissions are going to translate into climate change at the large scale. And so that's what I work on, particularly this ocean part. The land part is also super important. I hope someone else will talk about that on the live stream at some point, but I'm going to focus on this third box over here, the ocean. How do we understand that the ocean takes up about 3 petagrams of carbon per year, about 30% of our annual emissions? So here's another look at the global carbon budget. Because these emissions are so important, and this partitioning of the carbon between the land, the ocean, the atmosphere is so important. Every year, scientists around the world get together to come up with the best estimate of where the carbon has come from, how big were those emissions, how much came out of the land due to land use clearing, and where were the sinks. So that's the sort of summary plot is shown here, where the gray on the top is the emissions due to fossil fuel use. The orange on the top is the net emissions due to land use change, so deforestation today mostly happening in the tropics. And then on the bottom are the sinks. Where does that carbon end up? And because it's a closed system, the carbon isn't escaping to space, it's staying in the atmosphere ocean system. The sources and sinks have to balance every year. And so if we look at what the sinks are, the first green section below the zero line is the ocean sink, the second green section is the land sink, and then the blue is the atmosphere. And there's also a dashed red line, which is really just the mirror image of the total sources. And the extent to which we can really close the carbon budget is really indicated by the extent to which that the sum of those three bottom bits adds up to that red dashed line. And you can see that, the first order, they add up. It's a pretty good match. And in science, particularly when we're thinking about the very large and complex Earth system, we have to accept that there remains some uncertainty. Of course, things don't add up perfectly, but we have, essentially the shoe fitting to first order, that we know where the carbon's coming from and we know where it's going. But there is some remaining uncertainty. And that remaining uncertainty is actually really quite important, because we want to be able to detect change in the atmosphere due to changes in emissions, either because we have slowed down deforestation or because we have slowed down our emissions of CO2. And as I'll show in the next slide here, that is one of the key drivers of the research we're doing, is trying to reduce the difference between the blue line, the bottom of the sum of the sinks, and the red, the sum of the sources. So here is another way of looking at this plot, where we have in the black the observed growth rate of CO2 in the atmosphere, and we have the gray, which is essentially the emissions minus the land minus the ocean. And so it's a similar way, the same data as shown in the previous, just plotted in a different way. And if we had a perfect closure of the global carbon budget, the sum of our emissions minus land minus ocean would exactly equal the observed atmospheric growth rate. And you can see that the gray line and the black line, they're pretty close to each other. Again, we have a pretty good first order understanding, but there remains some difference between those two. And those differences, if we propagate them forward, are effectively going to make it difficult to detect change in the atmospheric growth rate due to cuts in emissions. So how long would it take for us to see a cut of our emissions down to 0% growth per year? Well, because of that variability in the land and the oceans, as well as our inability to fully quantify emissions, it's going to take several decades for us to be able to quantitatively detect change in the atmosphere due to changes in emissions. And so the more we can reduce the difference between these two lines, the more we can bring down that uncertainty, the better we're going to be able to detect how the atmosphere is changing because of our actions. And so that's really a key driver of what we're trying to do in my research group and in my research community. On the ocean side, and the land folks are trying to do the same thing similarly on the land side. So it's not that we don't understand the first order balance, but we're trying to get to the next level of understanding in order to really be able to tell the people of the world, did those cuts make a difference? Okay, so now getting into the ocean sink. Here is an animation from the NASA Echo Darwin model that shown at hourly resolution. And here blue is where the ocean is taking up carbon, red is where the ocean is emitting carbon, and the gray are wind vectors. And what you can see is that there's a large scale distribution of these fluxes, where the lower latitudes tend to emit carbon, the higher latitudes tend to take it up. But you can also see there's a lot of time variability. When a big wind event goes across the ocean, you can get some big fluxes occurring. And so there's a lot of complexity out there, a lot of time variability, and that's what we're trying to see through to understand these integrated effects on the atmospheric carbon concentration. So this is sort of, looking at all the points in space and time and trying to get a feel of that variability. And now I want to show you a plot that sort of averages everything up to the globe to look at the mechanisms of how this works. What are the underlying drivers of these fluxes? So here's a plot that separates the total carbon cycle of the ocean into two key components, the natural carbon cycle and the anthropogenic carbon cycle. So the natural part is the part that existed even before humans started emitting carbon to the atmosphere. And if you look closely on you can see that there's some numbers on these global mean profile plots. You can see that the numbers for the natural cycle are about 2,000 millimoles per meter cubed at the surface. And those are the much larger component of the total shown in the white here. So the vast majority of the carbon in the ocean is there naturally due to processes that have been happening long before humans started the Anthropocene. In terms of the natural carbon cycle, we have some biological effects that I'll explain. We have some ocean circulation effects that I'll explain. And then I'll also talk about the anthropogenic carbon cycle, which is really a perturbation on top of this natural cycle. Before I get into it, one thing you can note is that the natural carbon cycle has less carbon at the surface and more at depth, while the anthropogenic carbon component has more carbon at the surface and less at depth. So they have different signs of the vertical profile. Okay, so let's talk about natural carbon a bit more. So the way, the main control on air-sea CO2 flux, actually whether it's natural or anthropogenic, really is the partial pressure of CO2 in the surface ocean. When the partial pressure of CO2 in the ocean is greater than that in the atmosphere, carbon comes out of the ocean. And when the partial pressure of CO2 in the ocean is less than that of the atmosphere, the carbon goes in. So it sets the sign of the gradient and therefore the sign of the flux. So in the green map, that's the PCO2 with the mean atmospheric level shown in this bar over here. And so you can see that there are regions such as in the higher latitudes where the PCO2 is kind of low, and in the equatorial Pacific where it's kind of high. And you can see that on the flux map below, the CO2 flux map, where the PCO2 is low, that's where fluxes are going in, and where the PCO2 is high, that's where the carbon is coming out. So what are the processes that determine the PCO2 of the ocean? That's really what we need to understand, and one of the things we're going to need to have data for if we want to map it and understand how this is evolving in time. Okay, so actually I think, yeah, okay, I'll just very quickly note that the carbon in the ocean does not just dissolve, but it dissociates into these ions. And it is because of this dissociation into bicarbonate and carbonate ions that the ocean can hold so much carbon, because in fact, the vast majority of the ions of the carbon in the ocean is in these ions and not in the dissolved phase. Okay, so, but what sets the solubility of carbon in the ocean is actually this first step in this image here, the dissolution of carbon into the ocean over here, and that is set by the solubility. Which is something that is just simply the partial pressure is simply the concentration in the ocean divided by a constant. And that constant is something set by just the underlying molecular structures and kind of the chemical interactions between and molecular interactions between water and the molecules. But we can quantify this K naught, this solubility, and we can see over here in the little graph that the solubility is higher when temperatures are low, and it is lower when temperatures are high. And this is just the same way that if you have a Coke and you chill it off, the CO2 is going to stay in that Coke longer than if you warm it up, right? So if you have a Coke sitting in your car and it's a cold day, you might risk opening it when you get in the car. But if it's a hot day, you would be very poorly advised to open that hot Coke, because it's going to explode all over you. So just like that, CO2 in the ocean, in the warm tropical regions, the solubility is lower as shown in the map, and in the high latitude colder regions, the solubility is much higher. And so because of this, when we have processes in the ocean, such as the Gulf Stream, moving waters from south to north, those waters cool off, the solubility goes up as shown in the black and white map, and therefore the CO2 can be taken up because that water is cooling off, its capacity to hold carbon is going up, and so carbon is fluxed in. So that's one of the key processes of the ocean carbon cycle. We also have biology in the ocean. So the ocean is teeming with life. And in fact, 1 of every 2 oxygen molecules you breathe has been produced by biology in the ocean. And of course, the biology of the ocean is also feeding all the fish in the ocean and all of the marine life. And so, but this biology that is happening in the surface ocean in the presence of sunlight, so we need the plants in the ocean need sunlight to photosynthesize and grow. There is a small amount of the material that is organic material that's produced in the surface ocean that escapes sort of the ecosystem circulation that happens there. And a small amount escapes down to the deep ocean, about 5 to 10 petagrams of carbon per year. So on the same order of magnitude as our emissions of CO2 each year, a similar amount of organic matter sinks away into the deep ocean and enriches the deep ocean with carbon. It's a global mean number. So this is what the primary productivity of the ocean looked like from space, from the CWIF satellite. In this image, in dark blue, that's very low chlorophyll, very low productivity. In green, we have moderate chlorophyll, and in red, we have very high chlorophyll. And this is a long-term average over about 8 years of the CWIF's record. So we can see that on the long term, we have these very low productive subtropical waters, for example, and highly productive subpolar waters. And if you know a little bit about fishing in the ocean, you might know that it's in the equatorial Pacific, for example, and the Peruvian coast and coastal Alaska, where a lot of fisheries are located. And that is because there's a lot of plant material for the fish to eat. This is the base of the ocean food web. Okay, so this is the kind of productivity that we have in the ocean. Here's just another schematic of the processes that happen when the phytoplankton grow. They take up carbon and nutrients. They might get eaten by zooplankton. Some of the zooplankton makes fecal matter or excretes material. A lot of that returns to the surface ocean again as carbon and nutrients to re-enter the cycle. But some small part of this sinks into the deep ocean and carries some carbon and nutrients into the deep ocean, enriching the deep ocean with carbon. And then at the same time, as the carbon and nutrients is taken up, we also have oxygen being released. That's the oxygen we're gonna breathe when we breathe here on land. And then also there's this loss of material into the deep ocean. Regeneration of the organic matter happens by microbes that eat it up and returns carbon and nutrients and takes up oxygen in the deep ocean. There's another process on this plot that is important to understand, which is the circulation of the ocean that is now working to bring some of this carbon and nutrients back to the surface ocean. And so if we look at just a really brief primer on ocean circulation, if I take this productivity map that I showed you before, just in the North Atlantic, and I put on here sort of the mean currents. And then on the right-hand side is a schematic of the circulation in the ocean, sort of an idealized schematic, where we have a clockwise gyre and a counterclockwise gyre in the north. So those are the currents. It turns out that because of the winds over the ocean and the Coriolis force, it pulls mass into the centers of the subtropical gyres, and it removes mass from the centers of the subpolar gyres, and this causes highs and lows in the sea surface height, and this leads to these circulations. And now, if I'm going to take a section through these gyres and look with depth, so now I'm looking north, south, and vertically in the bottom here, I see I have again this high in sea surface height at the subtropics, this low of sea surface height in the high latitudes, and this bringing together of water at the surface also leads to downward motion, pumping nutrients away from the surface in the subtropics and sucking nutrients up to the surface in the high latitudes. And it's actually these nutrients that then go back and support the productivity. So the circulation redistributes the nutrients, also redistributes carbon. And so that's another part of the cycling of carbon in the surface ocean that we need to understand. Okay. Okay, and then there's also in the ocean physical transport and mixing from top to bottom. So we also have circulations of, now I think of the whole deep ocean, 0 to 6,000 meters. This is a section through the Atlantic of real observations. I can see that, again, I put the main kind of flow pathways here, that the carbon, the nutrients, and the oxygen are all following these flow pathways. Okay, I'm kind of getting a little short on time, so I'm going to move forward to talk about the anthropogenic carbon cycle here. Okay, so why is the ocean taking up excess carbon? How is it that the ocean is absorbing more carbon as we put more carbon into the atmosphere? And really, this is what's going on here is effectively what maybe you know as Henry's law, where when we add a gas to the headspace above a body of water, that body of water is going to come towards equilibrium with the headspace above. And essentially, we're pumping more carbon into the atmosphere, and the ocean is trying to keep up by raising its partial pressure to meet that of the atmosphere. And that's the main driver of this additional carbon uptake. And you can see that because of that, we have more anthropogenic carbon in the surface ocean. That's where the surface waters have seen the high CO2 concentration of the atmosphere. And then the circulation of the ocean is in fact driving this perturbation down into the deep ocean. So how do we understand this anthropogenic carbon sinks, and where do we get the data? So I want to talk about that and connect it back to some of the great work that people at NASA, NOAA, and the National Science Foundation do to understand this work, and also support research of academics like myself. So we have interior observations and the products that derive from them. People go out on research ships and put a lot of instruments over the side of the ship to collect really high quality data down and transect here from Iceland to Antarctica. Collecting a transect of these kinds of data would take several months on the ship, working 24/7 to collect the data and do the analyses for carbon and many other nutrients and other important things that help us understand the cycling of biogeochemistry and circulation in the ocean. So if we put these data together, they're quite sparse because this is a lot of very expensive work to do. If we look on top, in the top map, we have from the data that was collected in the 2000s of these kinds of observations. You can see it's quite sparse. Again, more or less the same survey was done in the 2010s, but still you can see there's large regions of the ocean with no data. But we believe this is adequate to make an estimate of the global ocean. And shown here in the going down the Atlantic, then through the southern oceans in the Indian sector, and then north in the Pacific, these plots here show the accumulation of anthropogenic carbon over the decade of the 94 to 04 and 04 to 2014. And you can see from this data-based estimate where the anthropogenic carbon is absorbed in the ocean, and it's mostly in the upper ocean, in fact. And we can learn a lot about the sort of large-scale processes of the ocean carbon cycle from this, but we can only do these kinds of global estimates approximately every decade. We can't get annual information. These data are available freely to you and me, all academics, and everyone in the globe from places like NOAA and CEI. We also have numerical simulations. These are like weather models of the ocean into which we can put our understanding of how biology and carbon work, put in mathematical equations that describe those processes and estimate their CO2 fluxes. So basically, we have circulation, the weather model, we add carbon processes, and we can get our estimate of ocean air sea fluxes. So models are certainly, our best sort of synthetic understanding of how physics and biology all work together to create these processes. They're certainly imperfect. They're not the real world, but we try to make them as close to the real world as possible. The other great thing about models is we can get all the pieces out of the model. We can get the biology and separate it from the freshwater fluxes, and we can understand processes with models. So that's one of the really great things about models is because all the data is there in the computer, we can extract the information and try to understand how these complex processes are working together. Ocean models of this type are developed by NOAA, NASA, NSF, and many academics working with them. And this is really an important part of U.S. leadership in global ocean science, is our great leadership in the modeling effort. Okay, the other way we understand the ocean carbon sink, I just have a few slides left, is to use, on the right-hand side, is to use ship-based data of the PCO2 of the ocean, and then use machine learning to interpolate that and to make estimates of where the PCO2 is high and where it's low, and to estimate fluxes from that. So these are the kinds of data that we have based on both research ships observations and container ships and other supply ships, for example, that go out with instruments that automatically measure the partial pressure of CO2 and report that back. Much of the surface PCO2 data collected in the global ocean, about 50%, are done by NOAA, and it's collated with data from other nations by NOAA, and it's served by NOAA. And so this is a really key thing, that service that NOAA provides is this kind of information for estimating the ocean carbon sink. So a lot of work's gone on, but still the data is quite sparse. So I showed you all the data before, and then this is just a month of data. About 2% of the 1 by 1 degree squares in the global ocean are covered by data. So how do we build understanding of the global monthly field from this? Clearly, you can't just interpolate it. You don't have enough information. But we do have machine learning, and machine learning has shown very great promise in being able to train up algorithms that connect variables for which we do have full coverage to make PCO2 maps that are full coverage, and then to calculate the flux from the PCO2. So we're doing this every year as the data is released, and creating the global carbon budget with that. So I guess my last slide here is to show that these independent estimates of the ocean sink agree to first order. In green, I have the models. In blue, I have the products. And in orange, I have the interior data. So, you know, again, there remains uncertainty. There remains some disagreements here and uncertain spread in the estimates. But to first order, despite the data being sparse, despite the lack of coverage, despite all the things that we still don't know, we have independent estimates that agree. And this tells us that we really do understand where the ocean is taking up carbon and holding it. We want to reduce that uncertainty, as I said at the beginning, but we do understand the balance here. The other thing you'll note here is that the ocean sink is continuing to change. And so we need to continue to understand how this is evolving in order to balance that global carbon budget and understand the progress of climate change. So there's still much uncertainty, much work remains to be done. And I just added a few more links here. If anybody wants to read more on the ocean carbon cycle from NOAA, or on the global carbon cycle from a website I put together. And I'll end by thanking you for your attention, and I'm happy to take any questions if we have time.
Thank you, Galen. That was fantastic. I really enjoyed those animations and just such clear explanations. We have a lot of questions, so I want to at least get one in, and then we'll see how much time we have. But I think this is a really great question from, I think it's Rion, and they ask, is the deep ocean then a carbon sink, or does the carbon get cycled through it quickly?
Well, no, the ocean is, so in the long term, if we look over the Holocene from the end of the last kind of a glacial period, the atmospheric CO2 concentration was pretty steady. And that means that even though the ocean in a natural state was emitting carbon and taking it up, those large fluxes were largely balanced before humans started adding this carbon to the atmosphere, right? So even though carbon is being brought to the surface, there's other places where it's being taken up, in the deep ocean. If we think about the future of human emissions, in fact, even if humans do manage to put several thousand petagrams of additional carbon in the atmosphere, the ocean will be able to absorb it. But the challenge is that the circulation of the ocean, this large-scale overturning circulation top to bottom, is kind of slow. It takes about 1,000 years for the ocean to overturn once, and it's going to have to do that a couple times to fully sop up all of our excess emissions. On 10,000 year timescales, the ocean will take up about 85% of our emissions. And so, but it's just that that's inconvenient for humans because we're putting carbon in a lot faster than the ocean can take it up. But the ocean is definitely a net sink and will be for the long term, whether we put a lot of carbon in the atmosphere or less. But it's going to be more efficient and able to help us out more the slower we go with our emissions.
Great. One more question. You have to answer it quickly, though.
Okay, sorry.
So we can get close to being on time. But there's so many, and this one I really like. Is there anything to be said about like harvesting the CO2 that's like going into the sinks in the ocean, so that we could reduce our concentrations in the atmosphere?
So there's a lot of effort right now with the idea of marine carbon dioxide removal. Can we engineer the ocean to take up more carbon? There are some pilot studies that suggest that we can, but the question really is, can we scale it up and do so in a net zero without putting more carbon in the atmosphere by doing so? I think there's a lot of research that needs to be done. It's not proven yet that it actually will work and be effective, but I think it's important research to do. But we have to also not just assume it's going to work. We don't want to pay people to do what the ocean would have done for us already. And we want it actually to be shown effective before we start paying people to put more carbon in the ocean. So, yeah.
Really great. Thanks. Those are great, sage responses to a challenging and thorny question. Thank you again, Galen. It's really been terrific. I can't wait to see you again, and hope it's soon.
Thank you, and thanks everyone for being here.
Yeah. We have a short reset that we need to take here. So we'll just be going quiet for a moment.
Yeah, just to say that we'll have everyone, if you go to, we're about to reset the stream. So if you go to this link, wclivestream.com/watch, you can rejoin the stream in a minute. So we're just going to reset it now. And we will see all 857 of you in a couple of minutes. Better come back. Better come back.